we're happy to have Michael Zlotnikov for the second talk of the morning session on day 2 of the workshop portion of the celestial holography workshop, talking about Poincare constraints on massless and massive celestial amplitudes. And I'll let you take it away, Michael.
Thank you, Sabrina, for organizing this wonderful workshop and for the opportunity to speak here. So as you mentioned, I will be talking just about the Poincare, the global Poincare constraints on the massive and massless amplitude structures that we get on a celestial sphere, which could be used as an ansatz for more general symmetry situations, because we always get the same. So we get the momentum conservation and the Lorentz subgroup in every case, in any case. So this is work that was done together with Albert Law in these 3 papers. Let me see. For some reason, it's changing the slides. Okay. So first, I will recall the definition of the map to the celestial sphere and the conformal primary wave functions, which we've seen in a couple of talks already. I will still go through the motions for the sake of repetition. And I will also mention how this map generalizes for the case of massive spinning bosons as external states for celestial amplitudes. After that, we'll also recall how Poincare generators act on conformal primary wave functions on the celestial sphere, as well as how the momentum generator acts on the massive spinning case, which will be a bit different from what we've seen so far. After that, we'll use the particular representations of those generators on the celestial sphere to set up the conventional set of symmetry constraints in the for Poincare symmetry for massless and massive 2, 3, and 4 point celestial amplitude structures, and we'll be able to solve some of those constraints in terms of generic functions that satisfy them. And finally, I will mention how the solution that we'll obtain for the 4-point massless external leg 4-point structure can be used to set up the relativistic partial wave formalism for those kind of amplitudes on the celestial sphere. So for conformal primary wave functions, consider to start a plane wave solution of a massive scalar in the bulk of Minkowski space and parameterize the momentum vector in this particular fashion, where the variables y, z, and z bar live on the space H3, which is half of an elliptic hyperboloid, basically parameterizing the mass shell of the massive particle. So the convenient, this particular space H3 has this particular metric, and the convenient feature of it is that under Lorentz transformations in the bulk, it transforms as the isometry of the H3 given by these particular transformations. And if we go to the boundary of H3 at y equals 0, we end up with the celestial sphere or the Riemann sphere on which the Lorentz transformations act as Möbius transformations. So using that, we can start with the plane wave solution in the bulk, dress it with the bulk to boundary propagator in the space H3, and perform this integral transform to map it to map the mass shell essentially to a single insertion point on the celestial sphere. And the resulting function we call conformal primary wave function, because under Lorentz transformations, it has the particular primary transformation weight that we would have for a primary state. Analogously, we can transform the amplitudes in the same fashion when we have amplitudes of massive scalars, and we end up with a correlator-like structure on the celestial sphere that transforms as a conformal primary correlator. Here, the quantity Q is a light-like vector that points to a specific insertion point on the celestial sphere. The same story can be repeated for massless external states. So Pasterski and Shao showed for various helicities and that the map to the celestial sphere is given by starting with the particular plane wave solution in the bulk and performing a Mellin transform in the energy scale variable. And again, we end up with a function on the celestial sphere that transforms as a conformal primary. And similarly, we can transform the amplitude of such states with such external states to the celestial sphere in the same fashion. So now the next question one can ask is, how does this generalize for the case of spinning massive bosons? And a natural generalization looks as follows. We still start with the plane wave solution in the bulk and perform an integration over the mass shell. However, here the integration weight matrix, so integration weight becomes a matrix, which is essentially by matrix multiplication dotted into the spin component index of the polarization tensor that labels the spin along the axis of propagation, a spin component along the axis of propagation of the particle. And the reason for doing that is that a single spin component is not Lorentz invariant. And if we want to actually consider something that's Lorentz invariant, we should transform the entire multiplet to the celestial sphere in one go and not a single spin component. And so here the requirement is that this matrix G should be set up in such a way that the resulting function transforms as a conformal primary as well under Lorentz transformations. As you might have guessed, of course, we can use the same procedure to map amplitudes of those kind of states to the celestial sphere as well. And if you prefer to work with symmetric traceless tensors on the celestial sphere, you can do that as well. It's just the bookkeeping, different type of bookkeeping, the number of degrees of freedom stays the same, of course. So let's be a bit more explicit and show two examples of how this works. So for spin 1 and 2, for instance, for spin 1, we can parameterize the massive polarization vectors in this particular way, involving this vector p hat that we've defined on one of the previous slides. And we can show that, of course, these polarization vectors satisfy all the required polarization properties. Similarly, in the spin 2 case, we can take symmetric traceless combinations of those vectors and parameterize the spin 2 polarization tensors in this way. And they also obey all the required properties, so we know that they're chosen correctly. Now, another ingredient we need is the explicit form of the Lorentz transformation matrix in the bulk of Minkowski space, parameterized by the same parameters that we've seen in the Möbius transformation on the celestial sphere. And now what we do is, since we require this particular transformation weight, we can consider a transformation that's infinitesimally close to the identity by choosing the transformation in this particular fashion and setting alpha, beta, gamma to be infinitesimal, and similarly for the BART parameters. And that what that gives us, since the integration measure and the plane wave part of the integral representation of the conformal primary wave function are invariant on those transformations, what we obtain is a set of coupled first-order differential equations for the integration weight matrix G in the integrand, which we can solve easily solve iteratively. And the results we obtain look as follows in those. So in the spin 0 case, we recover, of course, the known result that we had before. And then in the spin 1 and 2, we get a denominator, and there is a explicit matrix of 2s plus 1 by 2s plus 1 spin components. And these matrices, as you can see here, are pretty simple. Just involve simple rational dependence on the insertion points and the bulk coordinates. So this is, of course, just for the bosonic case. If you're interested in how this works in the fermionic case, there have been two very nice papers about that, which I would recommend to you. So here I'm just going to be concentrating on bosons. So we've seen the examples for spin 1 and 2, and of course, the question arises, how does this work for arbitrary spin? And here we are in luck, because in the scalar case, we've already seen that the integration weight was the bulk to boundary propagator on H3. And so if we recall this nice work by Costa, Gonzalez, and Penidones, who parameterized an arbitrary spin formulation of the bulk to boundary propagator on the relevant space in terms of symmetric traceless polynomials. So here, this quantity y that we dot into the Minkowski space indices on the polarization tensor is just a convenient device that Penidones and friends introduce in order to talk about this object in simpler terms, just projecting out certain trace terms that just obstruct the view. Here, those auxiliary vectors have the property that they square to 0 and that they are perpendicular to the p hat variable. And of course, no information is lost by multiplying it this way, because we can take this particular object that we obtain in this fashion and apply and consider an S-fold application of this particular special operator that Benedonus and friends also discuss in their paper on the subject to completely recover the original tensor structure. And so in this particular polynomial formulation, auxiliary polynomial formulation of the subject, we can write a arbitrary bosonic spin conformal primary wave function integral representation on this particular form. So we still have the plane wave exponential, and then this term here encompasses both the integration rate matrix as well as the spin, the polarization tensor. So another convenient result of this particular paper is that they actually also discuss an integral transform and a particular integral acting on such functions, which we can directly use to take the conformal primary wave function of arbitrary spin back to the Minkowski space plane wave basis. And that tells us that since the map is invertible and no information is lost, that tells us that since these functions form a complete basis, so must the other ones as well, since we can map them one-to-one. And so that shows to us that the conformal primary wave functions also span a complete basis. We can use them to parameterize our theory. So we've just discussed the mapping prescription for various particles, various spin to the celestial sphere, and there have been various examples studied in the literature how scalars, gluons, strings, or gravitons have been mapped to the celestial sphere. Explicit examples known in Minkowski space. But here I would like to take a step back and consider the case where we don't consider any known result in Minkowski space, but just consider the symmetries that we must impose on the celestial sphere, just the Poincare part of the symmetries, and find out what kind of constraints that imposes on generic amplitude structures, which start out as generic functions. So to do that, we have to define how the Poincare symmetry generators act on those particular fields or solutions, conformal primary wave functions. And that was pointed out by Stieberger and Taylor in 2018. So the massless momentum operator acts as a multiplication by this vector q that is light-like and points to an insertion point on the celestial sphere, only depends on quantities that live on the celestial sphere, as well as the shift in conformal dimension that also only lives on the celestial sphere. So there is no reference to bulk quantities here, even though we're using a Minkowski index just to count the number of generators we get. Similarly, they also point out that the Lorentz generators are given by these expressions. And of course, we can check that those operators form a valid representation because they close the algebra appropriately. Of course, the next question is, okay, so here we've defined the momentum operator for the massless case. How does it look like in a massive case? And the defining equation for that operator is that when it acts on this integrand weight in the transformation to the celestial sphere, it must give us the correct eigenvalue, and it must also square to minus m squared. And here I allow for the possibility that this operator actually depends on spin on the celestial sphere. And we here take a matrix multiplication and spin multiplet space for the particular massive particle multiplet. And of course, we have to recover the original eigenvector back. As it turns out, a particular representation for this operator that does this is given by this. So this is quite a busy expression. So let me just mention the important features here. We do find that there are some off-diagonal terms in the multiplet space for the polarizations. We also find derivatives with respect to insertion points on the celestial sphere up to second order. And we also find shifts in the conformal dimension on the celestial sphere. And of course, again, even though we're counting the number of generators we get by using the convenient Minkowski space index, we have to keep in mind that the operator itself acts entirely on the celestial sphere. So when we'll consider symmetry restrictions, it will be entirely on the celestial sphere without reference to the ball. And of course, the proof that this particular expression parameterizes the momentum operator for arbitrary integer spin comes from the fact that when we use this expression, we can analytically show that it does close the Poincare algebra for arbitrary spin S. We can show that analytically, and that proves that this representation is indeed correct. So the constraints we will be using are very simple. It's just the worded entities, Poincare worded entities. So Lorentz symmetry, or on the celestial sphere, it will be equivalent to conformal worded entities. We just act with all the Lorentz generators on the celestial amplitude, and we demand that it vanishes. And similarly, we demand that there is momentum conservation based on the translation generators. And since we have seen that the representation of momentum for massless and massive particles is quite different, we expect to find different constraints in those cases. So how do the constraints look like in the 2, 3, and 4 point massless case? So first of all, it's quite interesting to notice that in the massless case, we get a special situation when when the number of scattering particles is 4 or less. Because in the massless case, we can write the momentum conservation constraint in terms of a linear set of equations, where in the matrix formulation, we get the matrix Q that just has the quantities small q, which are the Minkowski vectors pointing to insertion points on the celestial sphere, while x is given by the amplitude times the shift. So whenever we have such a set of equations where the matrix Q is taller than it is wide, we are dealing with an overdetermined set of linear equations, and that tells us immediately that in order to have non-trivial solutions for such quantities x, the matrix, all the maximal minors of the matrix Q, the determinants of them must vanish. It's just linear algebra telling us that. And that tells us in turn that the amplitude A for n equals 2, 3, and 4 must contain Dirac deltas that will constrain the values of the insertion points that this matrix Q only depends on to some subregions, which will satisfy the vanishing of the maximal minor determinant. So that tells us, that's how we learn that necessarily, if we want momentum conservation on the celestial sphere, necessarily 2, 3, and 4 point structures must be distribution valued. There's no other way around it. And so let's take a look at how this looks like in particular. So in the 2 point structure case, minor determinant constraints tell us that there must be these two delta functions that set the insertion points to be equal. Then Lorentz invariance constraints, just acting with all the M generators and demanding vanishing, fix those particular powers to these particular values when we take the ansatz of differences of insertion points. And of course, as in usual CFT and the 2 point case, we learned that the conformal weights must be equal for both insertion points. And here I introduced this funny finite valued delta function, which is however not required if you don't feel particularly strongly about keeping the 2 point structure finite for the, when the two conformal weights coincide. Then you can just replace this by the usual Dirac and Kronecker deltas, and that would work just as well. So now what remains to be done is to consider what further constraints on the 2 point function coefficient we can learn from actually imposing momentum conservation. And it turns out, so since we are actually just acting with like P1 plus P2 on this, with certain signs in front for incoming or outgoing, since they shift those delta functions in 2 different directions, those 2 terms can never cancel each other. And that tells us that the only way to satisfy momentum conservation is actually to demand that the 2 point function coefficient is 0 in this case. And that aligns with our expectation, because when we would map the structure back to Minkowski space, we wouldn't expect to find a non-trivial 2 point amplitude. And so this is how we learn on the celestial sphere that the non-trivial part actually vanishes. So maybe a bit more interesting in this the 3-point case. So here, minor determinant constraints tell us that necessarily we must have this particular set of delta functions in the structure. Then Lorentz invariance, again, we take the ansatz of the differences of all the insertion points to some power, and the Lorentz invariance fixes those powers to these particular values as a usual CFT. And again, what remains to be determined is how momentum conservation actually constrains the 3-point function coefficient. And as it turns out, it's this particular expression. So here, what I should have mentioned also is that, well, from Minkowski space point of view, we expect on-shell 3-point amplitude for massless particles to vanish. And you can check that when you actually plug in the explicit expressions for those conformal weights, you will find that on the support of those delta functions, the overall coefficient has a positive power and vanishes. So that means even on the celestial sphere, we still recover that indeed, when we fix the insertion points to the locus supported by the delta functions, we still find 0. So that's consistent. However, since it's a parameterized 0, we can still argue that the 3-point function coefficient has to satisfy this particular equation, which was previously found from OPE expansions in a slightly different context. So here we can consider a particular example. So we take a gluon 3-point amplitude just as it's defined in Minkowski space, which would of course vanish on shell, but we can still perform the map to the celestial sphere, and we find that the delta function structure is exactly as we expect. And this particular coefficient here that we see evaluated on the delta functions that we find, taking these delta functions and that one into account as well, reduces to the same expression as this complete combination of terms that we've found previously. So those two agree on the support of the delta functions. And what we also observe is that we get this particular 3-point function coefficient, and it does in fact satisfy this requirement that we've observed. So that's nice and consistent. All right, so moving on to the 4-point case, which I think is the most interesting one. Here, minor determinant constraints, we'll only get one particular constraint here because here the big Q matrix is 4 by 4. So the only minor determinant we have to consider is the determinant of Q itself. And demanding that it vanishes so that we have a non-trivial solution immediately tells us that we must have this particular delta function here that sets the conformal cross ratios to be real. The conformal cross ratio in the 4-point case to be real. There's no other way. If we want to have momentum conservation, then this must be there. This particular prefactor that you see here is a standard prefactor used, for instance, by Dolan and Osborne in the consideration of conformal partial waves, for instance. It just ensures that the 4-point structure has the appropriate conformal primary transformation weights on their Lorentz transformations. And so that satisfies the Lorentz invariance constraint here. And finally, we are left with this free function of conformal cross ratios that we can still further fix in some way, further constrain, such that the structure satisfies momentum conservation. As it turns out, momentum conservation actually implies that when we rescale this function by this particular prefactor, the resulting function here must satisfy a particular relation, which is shift of one of the dimensions is equal, it must be equal to shift of any of the other dimensions. So it's trivial when it's the same dimension, but if it's different dimensions that are being shifted, it's a non-trivial constraint. And as it turns out, generic sets of functions that satisfy this requirement have the dependence on deltas such that it either depends on the sum of all deltas collectively, or if there are individual dependencies on individual delta i's, then that particular dependence must be periodic with period 1. How do we see that? So here, let's consider like generic constraint on such functions. Here we just have z1 through n, and we want to consider shifts of zi and cj on both sides by 1, and we set them equal. So let's think of what happens when we consider the first constraint. So we shift Z1 by 1 and equate it to the shift of Z2 by 1. Now we replace, when we consider this constraint, we can replace this function by an equivalent function that actually has the dependence Z1 plus Z2 in the first argument and only Z2 in the second argument. And we can always find such a function trivially by just adding and subtracting Z2 to the first argument, and then absorbing the minus Z2 of the first argument into the Z2 dependence of the second argument. So it's a trivial statement that we can always rewrite such a function as an equivalent function that looks like this. Now, when we consider the first constraint for this particular function, we see that the first argument doesn't give us any restriction, but the second argument gives us the constraint that whenever we see an appearance of Z2 that is not of the combined form Z1 plus Z2, it must be periodic with period 1. So that's nice, and we can repeat this step n-1 more times, and eventually end up with a formulation of an equivalent function where the first argument depends on the sum of all these. And analogously to the first step, all the remaining z's, Z2 through the n, whenever we have dependence individually on them, they have to be periodic with period 1, or the dependence is on all z's together, and then there's no periodicity condition. So, of course, singling out the first argument to do this procedure was an arbitrary but fixed choice. So we can just choose a different zi and repeat the steps, and then find as well that when z1 appears not in combination of the sum of all z's, then it must be periodic with period 1 as well. So that's nice. However, there are also some subtleties that we have to keep in mind whenever we have such periodicities. So in essence, there can be convergence issues if we consider the inverse transform. So if we impose the condition that whatever amplitude structure we have on the celestial sphere, if we impose the fact that we must be able to transform it back to Minkowski space, then of course we have to demand that the inverse Mellin transform in all the deltas that we have floating around from -infinity to +infinity in this lambda parameter, it must converge. And it converges if the function we're transforming is analytic in the complex strip around the integration path, and also tends to 0 as lambda goes to ±infinity. So as it turns out, a periodic holomorphic function of finite order, which we assume on physical grounds, is unbounded on any such complex vertical line, and that leads to convergence issues. And how do we see that? So let's assume the function is bounded on some single vertical line that we carefully pick out, let's say. Then by periodicity, this line will repeat, of course, an infinite amount of times. And so we can focus on two such lines in parallel. And so we see that the function is bounded on the boundary of a finite width strip in the complex plane. And when that happens, we can apply the Fragment Lindelof method in complex analysis that shows that whenever such a function is bounded on the boundary of the strip, it must also be bounded on the entire strip. And then by periodicity, it will be bounded on the complex plane. And when that happens, of course, by Liouville theorem, we know that a function that's bounded on the entire complex plane is, of course, constant. And so if we want a non-trivial function that is not constant, but is still periodic, then we must have unboundedness on any complex vertical line. And so we will run into a divergence as we attempt the inverse transform. So that tells us that either the dependence of this function f should really just be dependent on this combination of all the deltas, or if we do obtain some periodic dependence on the individual deltas, then this initial dependence on the sum of deltas should be carefully fine-tuned to remedy the unboundedness that we would get. In practice, all the examples that we encounter actually never have a periodic dependence. So I would say it's safe to assume that generically, just the dependence on the sum of all deltas should be sufficient to parameterize what we're interested in. All right, so that concludes the massless part, and the 4-point structure that we've just discussed will be useful at the end when we discuss how the conformal primary relativistic partial waves on the celestial sphere can be set up. We will use it as a building block, as a starting point there. But now let's consider the same kind of constraints for the massive 2, 3, and 4-point structures. So here, since we have a massive momentum operator, at least one of them present in the momentum conservation constraint, there are, of course, no more minor determinant constraints. There's no set of overdetermined linear sets of equations. And so just the Lorentz subgroup of the symmetry group fixes the generic structure of the starting point that we can choose, fixes it to the same expressions that we would expect just from the CFT point of view. And now, starting from the starting point, we will use momentum conservation constraints to find further constraints for the 2-point function coefficient, 3-point function coefficient, and the function of conformal cross ratios in the 4-point case. So how does it look like in the 2-point case? So here, let's say we have a momentum conservation for 2 particles of mass 1 and 2, and of course we will find that what we find are two independent recurrence relations that can be reconciled only if we choose the masses to be equal. And the 2 recurrence relations can be actually solved on the celestial sphere, which might be a bit surprising, and we get this particular expression where there's still some freedom, unfixed freedom. This function just has to have periodicity with respect to x, and we could just choose it to be constant if we don't like periodicities, as we just discussed. So it seems like, well, in the massive case, we would also not necessarily not expect a non-trivial 2-point amplitude in the Minkowski space. And the way we can see that this happens here as well is when we attempt to map this particular structure, the 2-point structure with this particular 2-point function coefficient back to Minkowski space, we run into a divergence that sits exactly on the integration contour that inverts the expression back to Minkowski space. So even though by symmetry, we could find this solution on the celestial sphere, there is no well-defined inverse transform, and so we don't find a non-trivial 2-point amplitude in Minkowski space. Now, when we go to the 3-point case, where we start out with a single massive scalar, we can see that the 2 massless particles, there are only non-trivial constraints when we so we find that there are only non-trivial solutions to the constraints when we set the helicities of the 2 massless particles to be equal. And that's consistent with previous results that were considered in Minkowski space, of course. So here we see we have the constraints that they reduce to 3 2-term recurrence relations that can also be solved in this particular fashion, where here again we still have some freedom that we can fix to be constant if we don't like periodicities, since we don't like periodicities. And as it turns out, this particular expression actually matches exactly when we fix this freedom to be a constant and consider the scalar case for the massless particles as well. Then we completely from symmetry recover the result that was obtained for the 3-point function coefficient by Lam and Shao in that paper. So that's nice. That is encouraging. That means we're doing something right because we find consistency. Now, when we allow the massive particle to also be spinning, not just a scalar, then we get more complicated 4 3-term recurrence relations that are hard to solve. However, in this case, we can still make progress by starting at the highest weight of the spin multiplet of the massive particle. So if we set the multiplet, the particular spin value to the highest weight first, then the recurrence relations simplify, and we can similarly, as in the previous cases, find this particular solution. And then there are further recurrence relations remaining that relate 3-point function coefficients with the spin value lowered by an integer to the 3-point function coefficients where the spin value is the highest weight, let's say. So we can use this relation to iteratively lower the spin value on the massive particle, and then recover the entire multiplet in that fashion. So what we expect, of course, is that once we go from plus S1 to minus S1, we want this iteration to truncate because we don't want to generate terms with spin of S minus 1 minus S1 minus S1 minus 1 and so forth. But what we notice is that the truncation is not automatic. And in fact, the last step generates terms that are proportionate to this particular product. which tells us that a necessary condition for the truncation of this iteration process is that the difference, the absolute value of the difference of the helicities of the massless particles participating in the scattering process must be at most equal to or less than the highest spin value that can be accommodated by the multiplet of the massive particle. And that also is consistent with previous considerations from the bulk point of view, of course. So, and that particular property will also be important when we talk about the parameterization of relativistic partial waves on the celestial sphere. Now, when we allow the two particles to be massive and the third particle to be massless, that leads to 4 5-term recurrence relations, which are hard to solve, so I don't have anything to say about that. However, when the massive particles are scalars, this simplifies and leads to different constraints. And it's different in the cases when the massless particle has spin or is a scalar. So in the case when the massless particle is a scalar as well, we have 3-coupled 3-term recurrence relations that are very reminiscent of recurrence relations that hold for 2 F1 hypergeometric functions. That's why one could argue that probably the solution for the 3-point function coefficient would actually be given in terms of such 2 F1 hypergeometrics. So, but in the case when the helicity of the massless particle is not a scalar, then we find again different recurrence relations that can only be solved if we enforce the condition that the masses of the two scalars are equal, and that can be solved by this particular expression right here again. However, here it's important to note that the remaining freedom that we have is required. This function that we have as a remaining freedom is required to be antiperiodic under such shifts, and that comes out directly out of the recurrence relations. So antiperiodic functions are similarly unbounded under inverse transformation to Minkowski space as periodic ones by the same argument, essentially. And so if we want to rule out the antiperiodic dependence here, and let's say set the constant to be set the function c to be constant, then the only constant that's actually antiperiodic is 0. So that tells us that this 3-point function coefficient actually should vanish if we plan to map it back to Minkowski space. And that's consistent with the fact that such an amplitude doesn't actually exist in Minkowski space, because when we force the masses of the two scalars of participating in the scattering to be equal in Minkowski space, then the momentum of the spinning massless particle will be forced to go to 0. So there's no non-trivial 3-point amplitude in that case in Minkowski space that we would expect, just by kinematics. Okay, so if we press on and consider cases where we have a 3-point structure that has 3 massive particles, and the massive particles are scalars, let's say, then the only thing I can show you is the recurrence relation. So we have 3 4-term recurrence relations that we at least don't know how to solve, but presumably solutions might as well involve hypergeometric functions 3f2 because those functions satisfy similar 4-term recurrence relations. So that's just an assumption. It's not guaranteed that that's actually the case. And if we allow the massive particles to be also spinning in the most general case, then what we get is 3 8 and 1 9-term recurrence relations, which again we don't know how to solve. So we do get them explicitly. So if there are, for instance, some example amplitudes that we want to map to the celestial sphere, we can use those constraints that we obtained to verify that the mapping was done correctly, like that it was a correct procedure, because any amplitude mapped to the celestial sphere will have to satisfy these as long as Poincare symmetry is satisfied. But yeah, we were not able to solve them. Similarly, in the 4-point case, the only thing I can mention to you is what kind of constraints we get. We didn't solve them explicitly. So here, the constraints are acting on just the 4-point, the function of the conformal cross ratios. And the constraints we get, they depend, they just produce 4 equations that are entirely in the cross ratio space, so no explicit dependence on single insertion points on the celestial sphere. There are shifts in F and conformal weights of all 4 particles. There are also cross ratio derivatives of single order and second order. And so what we have are 4 coupled second order two-dimensional differential equations, which are simultaneously coupled first-order recurrence relations. And of course, again, we didn't solve them explicitly, but they are likely strongly constraining, and we can use them to verify that whatever structure we're talking about on the celestial sphere is indeed Poincare invariant if it does satisfy these constraints. All right, so let me move on to the relativistic partial wave discussion. So here, when we're talking about relativistic partial waves, we have the Poincare group in mind, and when we attempt to decompose something in terms of relativistic partial waves are labeled by the quantum numbers in the like the spectrum of states will be labeled by quantum numbers of irreducible representations of Poincare group. So for the cases when we have a non-zero mass, we have the quantum numbers mass and s, and for the case when mass is 0, we have the quantum number helicity as well. And we can recover these quantum numbers by applying the Casimir operators, which are momentum squared, of course, and for the Poincare group, and the Pauli-Lubansky pseudo-vector defined here squared. So here we have the mass of the particle and the spins. In case of if the particle is massless, we can extract the helicity quantum number by this particular combination from the Pauli-Lubansky pseudo-vector. Now, when we consider a relativistic partial wave, what we actually have in mind is that we're not applying those operators to a single particle. We're actually interested in considering two particles. So we want a direct product representation of two particles which are incoming, and producing a state that's labeled by some of those by the respective Poincare quantum numbers. And then, I mean, the other side splits again into some outgoing states, but we want the action of the Casimirs acting not on just one leg, but on two legs, which is the usual thing to do when we consider partial waves. And so here, the direct product of two particle representations is so the action of the momentum operator is just momentum of particle I plus momentum of particle J, and similarly for the Lorentz generators. And so the Pauli-Lubansky pseudo-vector is then also composed out of those composite operators. And here we get the quadratic and quartic Casimirs of Poincare symmetry, where where the mass and the spin on the right-hand side we see here are the mass and spin quantum numbers of the mode produced in the interaction of particles I and J. So let me delete this. Okay. All right. And so what that tells us, since we know the representation of momenta and the Lorentz generators that we've discussed on the previous slides, what it tells us is that when we act with this particular Casimir on the 4-point structure that we've also constrained on the previous slides, that will give us a shift and differential equations that further constrain this 4-point function function of the cross ratio that we had determined previously, that will assume to be dependent on just the sum of the deltas. So and that will constrain it further and actually give us the functional result for what a conformal, what a relativistic partial wave looks like on the celestial sphere, because what this relation gives us is something that has this exchanged mode of definite mass value and definite spin value, and that's exactly what we expect from a partial wave. It will not be a superposition of several modes. It will involve just a single orthogonal mode exchange, and that's precisely why we expect the solution to these equations to give us a partial wave. Now, what we also should recall is this constraint that we've seen in the 3-point case when we had one massive external leg and two massless external legs, that the exchanged spin of the mode, when the exchange mode is massive, has to be greater or equal to the absolute value of the differences of the helicities of the external particles. And when we make this assumption, then we can solve the Casimir equations we've seen on the previous slide. They are pretty simple shift and differential equations. And the solutions that we obtain are given by this. So that's just a solution for the 4-point function of the conformal cross ratios. Here, the quantity delta is the sum of all deltas as we determined from the momentum conservation constraint. And there is no periodic dependence on deltas in here. And the functions p here are the Jacobi polynomials, which again is consistent with the bulk perspective in the bulk formalism. Doing the same exercise also, of course, leads to Jacobi polynomials as partial waves. Now, just having the partial wave is not sufficient. We also would like to define an inner product in the space of relativistic functions living on the celestial sphere. And for that purpose, we just select directly, not the 4-point structure in its entirety, but just a non-trivial, relativistically non-trivial function f that lives, that we can extract from any 4-point amplitude. And we define the inner product directly in the space of those relativistically non-trivial functions. So here we have a complex conjugate of one of the functions times another function. We have a certain integration weight that we fix by the requirement that the two Casimir operators of Poincare symmetry are Hermitian. And after determining the inner product in this particular fashion, we can immediately show, using the particular results for the relativistic partial waves we've seen on the previous slide, we can show that two different partial waves indeed are properly orthogonal. It's very simple to show because we, of course, know the orthogonality relation for Jacobi polynomials, which enters here. And then based on that, it's straightforward to write down the completeness relation, which is given by this. And using the completeness relation, we then finally obtain the expansion, the relativistic partial wave expansion for any 4-point structure on the celestial sphere that has Poincare symmetry. Again, I emphasize it's just the Poincare structures with 4 massless external legs. So here we have the inner product of the structure with a partial wave that determines the weight. Then we sum over the quantum numbers of Poincare, so masses and spins, and we recover the original result. And so in our paper, we actually did some examples, explicit examples for scalars and gluons, gravitons, and showed that for gluons and gravitons, we showed that indeed we can expand it on this basis, and then we sum it again and recover the original function in the particular channel of interest. Yeah, and so that actually goes in the direction of the discussions that I was listening to that we had in the few days before. Namely, the question: well, what should we take as the spectrum of excitations on the celestial sphere for the particular theory that we're studying there? And from this point of view, it seems that as long as we have Poincare invariance, so if we say the bulk has Poincare invariance, and so must the dual theory on the celestial sphere, then the question to ask is, okay, if we have Poincare invariance, and let's just focus on the simple example where we don't introduce extra symmetries like BMS, we just concentrate on this very simple example, then the question is, okay, if the theory is Poincare invariant, what are the quantum numbers, what are the modes that we should use to parameterize it? And the answer to that is, well, do we know the representation, the particular representation of all the Poincare generators acting on the field that we have in that theory? And since we take the map to the celestial sphere seriously, we claim that the conformal primary wave function on the celestial sphere parameterizes some sort of field solution for some celestial CFT on that space. And we know how all the Poincare generators act on that particular field solution. We can extract the appropriate quantum number by just considering the Casimir operator that we've seen on the previous slide. So since we know the symmetry and we know the Casimirs, we can extract the appropriate quantum numbers that we should use to parameterize the spectrum of modes. And perhaps unsurprisingly, that since the momentum and Lorentz generators are inherited from Minkowski space, we find that the appropriate quantum numbers are actually the good old mass and spin. So In that sense, it goes a little bit orthogonal to attempting to parameterize orthogonal modes in terms of conformal dimensions and operators, because that would be like a point of view trying to maybe describe, I guess, a irreducible representation of the Poincare group in terms of an infinite sequence of the Lorentz subgroup representations, which is a bit tedious, I would say. So in that sense, maybe it's an unpopular opinion, but I would argue that the simplest way to determine the spectrum would be to always consider what's the underlying symmetry of the theory, consider what are the irreducible representations based on the given symmetry, and span the sequence of span the spectrum of modes based on the irreducible representations. So that's all I wanted to say, and I would like to hear your opinion on my friend at the end. So thank you for your attention.
Thank you very much, Michael. And that's part of the reason why I paired you and Shamik together in a session, because I think you both have had at some point like ideas that pointed towards like maybe expanding from the celestial sphere to null infinity or various versions of that. So I'll let have questions of this first best suitive.
Yeah, thank you for your talk. So this might be a little bit tangential, but if you're just talking about the irreducible representations of the Poincare group, then, well, massless particles with helicity are not, I mean, they're redundant representation of the little group for massless particles. You would also have to include in principle something like the continuous spin representations, which, I mean, they don't really appear anywhere in our field theory. So is there anything you can say from just thinking by looking at the celestial sphere, like, is there any room for these?
Right. I guess the question is, why wouldn't we attempt to include continuous spin representations in the spectrum of states that we sum over? So I guess I wouldn't know how to see that directly from the celestial sphere, but at least from the perspective of Minkowski space, it's the reason for not considering those is because they don't have normalizable wave functions. They lead to non-normalizable wave functions, and so there are no particles observed in nature that have such properties, and so that's why they're not included.
But can I add?
Yeah.
Oh no, I thought you were done talking. I'll let you finish talking. Then
Yeah. So maybe one thing I should mention also, why do we particularly only consider? So we only involve in the construction of the relativistic partial wave. We've only involved like this particular constraint, and only considered like a combination of massive exchanges and not like a massless exchange. In that case, it's actually also clear because the massless on-shell 3-point amplitude in Minkowski space vanishes. So we could formally write down that it does contribute, but it contributes 0. So the only non-trivial modes that are exchanged are actually massive in this case.
So I want to add a comment to that, though, especially along the lines of your question. I think there was a paper some time ago from, I forget the names of the people, so maybe someone can remember this paper. There was a paper that was talking about looking at the little group and how little group transformations corresponded to doing large gauge transformations. And I'm pretty sure that if you just like went through that paper from, I think it was a group from China, they showed that the generators that would correspond to the doing a, what's it called, like the continuous spin representation, like the 0 that you get normally in like Weinberg's textbook, like would be mapped onto the highest weight condition, I think. So I think the fact that the Mellon states are highest weight is like the annihilation under like the ISO, the other part of the ISO too.
Right.
And I think there's a paper, and I feel terrible, I don't remember like the archive number, but I'll try to find it and I can maybe add it to.
Thanks.
Yeah, thank you.
Appreciate it. Thank you, Sabrina. Thank you, Michael.
Great. Tomas?
Yes. At the tree level, Young-Mills has also conformal symmetry, and special conformal generators are involve second derivatives. Do you get something new by applying it to the amplitudes, to celestial amplitudes?
Yeah, that's a very interesting point. I think if we consider amplitudes in Minkowski space that are conformal in Minkowski space, then the appropriate basis of functions to consider would not be relativistic partial waves, but actually conformal partial waves in Minkowski space, which would involve an additional set of generators and a difference in the Casimirs that we consider. However, in the case of tree-level Minkowski space amplitudes for gluons, I believe if we introduce the I epsilon prescription to regularize the Feynman propagators, then that breaks the conformal symmetry a little bit. And as soon as it's broken a little bit, we can use the relativistic formulas. I believe that's the case.
Thanks.
I see Atul has a question, or
I have a couple of questions, but I can ask in the discussion session if you want to end this.
sure, up to you.
Yeah.
Yeah, Shamik?
Shami?
I think you're muted. You're muted. You should activate your.
Okay. Yeah. So I am thinking that if you have any thoughts about the OP of these massive fields, because you could perhaps constrain more things. Well, in some ways, I mean. So when you say OPE, immediately that implies that we would make the choice of trying to parameterize a single, let's say, irreducible representation of Poincare group in terms of an infinite sequence of irreducible representations of the Lorentz subgroup, let's say, in this particular case where we just have the Poincare group. So I think that's a very confusing way to think about it. Could
I don't know.
Local transformations. I mean, not just the Poincare transformation, right? Like,
okay, right. So when you introduce also local transformations, that would correspond to have like super rotations.
Yeah. So those kinds of things. I mean, have you thought about it?
Yeah. So I guess I can the comment I have on that is essentially the same, regardless of what symmetry group we have. I think the procedure is always, well, we consider what's the symmetry group of the theory. Then we determine all irreducible representations of that symmetry group and all the Casimir operators. And then we read off from the Casimir operators what are the appropriate quantum numbers to parameterize orthogonal modes in that theory. And I'm not completely certain that the most natural choice of quantum numbers would involve such a conformal dimension. That as in the case of this Poincare case that we've just seen, the appropriate quantum number is still mass and spin. So you could, of course, still choose to decompose the spectrum further into irreducible representations of some of the subgroups, and that would be very tedious. And I don't have any intuition for that answer. But I think that the simplest approach would be to figure out the reducible representations and just stick to the appropriate quantum numbers. That would be the simplest way to figure out what the spectrum of the theory is. That's just my opinion.
Okay, thanks.
Thank you. So if that was the questions that seem to be just for the talk, and then we can go into discussion, I'll stop recording now. Thank you again, Michael. So I'm happy to start the afternoon session for today with Anna Maria Raclariu, who will tell us about universal aspects of celestial 4-point scattering. Take it away, Anna.
Okay, thank you very much, Sabrina, for organizing this very inspiring workshop and for inviting me to give a talk here. So I'm going to be talking about some work in progress with Alex Atanasov, Walker Melton, and Andy Strominger, which is mostly going to be complementary to Andy's talk yesterday and Nima's talk, which is to follow. But of course, I'm gonna refer to some of the ideas we've heard and we'll hear about in the talk, in Nima's talk and in Andy's talks. Okay, so I should mention, so there is also Monica and Adam and Nima, who I'm gonna cite that work when it's gonna when the time will come, basically. Okay, so at this point we're basically, I think, halfway through the workshop, and I think I'm not wrong to say that every talk we heard so far has had the word celestial in the title. So perhaps I shouldn't be spending too much time trying to motivate why we should be interested in celestial field theories. But nevertheless, let me start by repeating some of the things that have been said before and that will be relevant for this talk. So what we want to do is to find a formulation of scattering in four-dimensional asymptotically flat spacetimes in terms of some kind of theory living on the boundary. And since the Lorentz group acts nicely on the sphere at null infinity, also called the celestial sphere, it's natural to look for some sort of observables which also transform covariantly under the Lorentz group. Now, S matrices are not such observables because they're usually computed in momentum eigenstates. So these momentum eigenstates are typically parametrized by momenta of the incoming and outgoing particles. So this epsilon is a sign, this omega is an energy, and the z and z bar are stereographic coordinates on the celestial sphere. So these have been introduced in many of the previous talks before. So the map, which actually gives us these observables we're interested in looking at, which live on the celestial sphere, is a Mellin transform in the case of massless particles. So I should say that this is the parametrization of a massless particle, and it's just given, right, it's just given by this integral transform, which roughly speaking, implements a change of basis from a basis of momentum eigenstates to a basis of boost eigenstates, namely boosts in the direction of each of the particles. So the direction in which these particles point towards the celestial sphere. So then the natural observables one can define are Mellin transforms with respect to all of these external legs of the momentum space scattering amplitude, and this is what computes a celestial amplitude. Okay, and again, just to emphasize that what we're doing here is that in this parametrization, everything is already naturally labeled in terms of points on the sphere. But what we're doing by taking this transformation is we're trading these energies for boost weights, for some kind of conformal weights. So this allows us to think about these objects as some kind of observables which look very much like conformal correlators in a conformal field theory. So what I mean by that is that by construction, they will be SL2C covariant. Now, more interestingly, and this is a property which is not obeyed by conventional conformal field theories, and we've seen this also in Stefan's talk and in Shamik's talk and in Michael's talk. So in a lot of talks, this has been mentioned by now that translations, so just simple extension of the Lorentz group into Poincare actually impose non-trivial constraints on celestial amplitudes. So namely what they do is that they relate celestial amplitudes with shifted weights. And Michael has very nicely shown how one can use these constraints to constrain the form of various 2 and 3 and 4 point functions. Okay, in addition to this, we've also seen a lot of examples by now that soft theorems are also quite powerful in the sense that they constrain, at least as far as we know right now, leading and subleading OP coefficients in gravity and gauge theory. And again, I'm not going to dwell on this too much because we've heard a very nice talk by Shamik this morning. And finally, well, actually finally, the list here should be long, but one other interesting thing which will be discussed later on by Nima is the fact that 2-to-2 scattering amplitudes actually impose additional non-trivial constraints on the structure of 2-to-2 celestial amplitudes. In particular, these constraints, and I'm going to review some of them also briefly in a moment, actually imply some nice analytic structure in the complex boost weight plane celestial amplitude should have. Okay, now, okay, so most talks we've heard so far are about building up a dictionary between kind of momentum space scattering amplitude and amplitudes and celestial amplitudes, and trying to actually understand all of the properties the latter have to obey. But ultimately, I think all of us here, and I think Andy also emphasized this yesterday from perhaps a different point of view, is that we'd like to use the celestial theory to learn something new, something we didn't know about gravity, and perhaps even gauge theory in asymptotically flat space. So I would say that one basic thing which would be remarkable would be, and it's been suggested again by Stefan's talk and Shamik's talk, is that it would be pretty remarkable if at least some subsector of the celestial theory was characterized by some complete set of operators, which obeyed some algebra, and ultimately would allow us to say something about scattering amplitudes in flat space. Perhaps not reconstruct the full amplitudes, but say some amplitudes in some limit, or perhaps some subclass of amplitudes, for example, MHV amplitudes, as we saw this morning. So all of these ideas, I think, are very interesting. And one simple way in which one can approach this, and again, we've seen this in Michael's talk from a slightly different point of view, is that one can try to consider a celestial amplitude and try to do a conformal block decomposition. So this morning, Michael talked about relativistic conformal partial waves. Here, we're trying to do something even more basic, namely just start with a celestial amplitude and ask the question whether it has a conformal block decomposition. So in other words, we're trying to just decompose it into representations of SL2C rather than the full Poincare group. So this is my outline. So I'm going to start off just to see where we're going with this. I'm going to start off by reviewing the general structure of celestial 4-point amplitudes, as will be relevant for what I'm going to be saying later. Then I'm going to briefly describe these conformal partial wave decompositions and in part repeat what Michael said this morning, but just restricting to SL2C rather than the full Poincare group. Then I'm going to show that a certain class of 3-level massless 4-point amplitudes of scalars on the celestial sphere actually do have, or at least there is a sense in which one can interpret them as having a conformal block decomposition. So hopefully in a sense which will become clear soon. And in particular, what we find from this calculation is that there is a tower of scalar exchanges at positive integer dimensions. And these dimensions are actually discrete and they're related by integers. And then there is also a continuum of delta equal to 1 and complex J modes, which one can perhaps interpret as some sort of light ray transforms of these other exchanges. And finally, okay, so this is, again, to emphasize, it's work in progress. We have a formula, which we are pretty sure about that it's correct. We're still trying to understand the details, and I'm going to try to comment on what the puzzles are at the very end. And I very much be looking forward to see what people think about this. And yeah. Okay, so to start off, just to introduce some notation, we'll be restricting to the case of 4-point scattering, which in momentum space is described by some scattering amplitude, which is a function of the external momenta. In particular, Lorentz, actually Poincare invariance constrains this function in the case of scalars to take the simple form. So it's a function of the two independent Mandelstam invariants, say S and T, and it's multiplied by some momentum conserving delta function. So we are working in a parametrization where we're taking particles 1 and 2, be incoming, and 3 and 4 be outgoing. So it's natural to define the center of mass of energy as P1 plus P2 squared, and the momentum transfer as P1 plus P3 squared. So remember, these P's are actually secretly carry a sign, which tells us whether the particles are incoming or outgoing. So in this case, P3 would actually come with a minus sign, but that's inbuilt in the definition. And it will also be useful to actually label or relabel these S and T variables in terms of these parameters, omega squared and Z, which it will become obvious in a moment why I want to do this. So first of all, this Z parameter, and we've seen in Stefan's talk as well, if you take the ratio of T and S, it's related to the scattering angle. But on the celestial sphere, it plays the role of a conformally invariant cross ratio. So in this particular parametrization, you can find that if you take the ratio of T and S, you find an expression of this form. And moreover, it's going to be useful to define this beta parameter. And again, it's important because I'm going to keep mentioning this beta later on as the sum of all of the external dimensions minus 4. So, okay, so we have these 2-to-2 scattering amplitudes, and we'd like to put them on the celestial sphere. So as we said before, the way to do that is to take, in this case, 4 Mellin transforms with respect to the 4 external energies. And one simplification which occurs in this example is coming from this momentum conserving delta function. So it imposes actually 4 constraints, and roughly speaking, 3 of them actually imply that all of the external energies are proportional to one another, up to some functions of differences of Z. And this also imposes this constraint that this cross ratio is real. And so using these 3 constraints, then one can immediately evaluate 3 of the 4 Mellin integrals to just give rise to, which then gives rise to some function of Z and Z bar, which is sitting out front. And then what's left over, and in particular, this function would also include a delta function in Z minus Z bar. I'm going to show in a moment an explicit expression of what this is. And so we are just left over with just 1 Mellin transform with respect to this energy variable omega, but where now this parameter is not neither of the external weights, but it's a sum of all of them. In particular, it's exactly given by this expression here. Okay, so this is giving us basically a map between this 2-to-2 scattering amplitude and the celestial amplitude. So just to be very explicit, this calculation I just described gives you an expression for this function out front. So the reason I actually split it into 2 pieces like this, so I'm calling K this piece, and it turns out that actually one could have guessed, and of course I'm just repeating what Michael has said before, one could have guessed the form of this function just using SL2C covariance. So this is nothing but the prefactor which sits in front of any conformal correlator, for example, in 2-dimensional conformal field theory. But now we have this additional constraint which comes from momentum conservation in the bulk. Now, more interestingly, as Michael described, the fact that momentum is conserved in the bulk imposes a non-trivial constraint on the celestial amplitude. And in this notation, so I'm using a slightly different, I'm going to make contact to the notation Michael used before a bit later. But the point is that in this notation, what this translation invariance implies is that whatever's left over after stripping off this prefactor is just a function of the cross ratio and beta. And I want to draw your attention to the fact that this is very much, I mean, the Z dependence, the fact that whatever's left over just depends on Z, and Z bar is the same as in conformal field theory, but the fact that this dependence, the dependence on external weights actually appears in this form of a sum is very special to celestial theories, and again follows from Poincare invariance. Okay, so this was, I said some words about this prefactor. Now, the interesting information, of course, is contained in this Mellin transform of the momentum space scattering amplitude. And we've seen recently in work with Nima Arkani-Hamed, Monica Pate, and Andy Strominger, and we're also going to hear about this, I'm sure, a lot in Nima's talk, that just the simple, this simple Mellin transform and the structure of the momentum space scattering amplitudes tells us something about the beta dependence of the celestial amplitudes. And it's actually, the story is pretty nice. And here is just a teaser for what's going to follow later. One of the nice properties celestial amplitudes can be shown to have is that they have poles at even integers on the real axis pretty generically. And in particular, the poles on the negative real axis correspond to low energy expansion in the amplitude, and the residues are associated with coefficients in the low energy effective field theory. Now, generically, in just quantum field theory, there's also going to be poles coming from a high energy expansion, or rather an expansion around omega goes to infinity, which are going to be basically everywhere on the real beta axis. But what's nice is that one can actually, that celestial amplitudes actually provide us with a simple probe of distinguishing between just quantum field theory amplitudes and quantum gravity amplitudes, in the sense that quantum gravity amplitudes can be shown to have no poles on the positive real beta axis. And this actually follows from the expected exponentially soft behavior, in this case at high energy. Now, another thing one can show is that, so here, this would be just an expansion in parts of omega, but generically any scattering, any low energy expansion of the scattering amplitude would also involve loops and hence log churns in omega, and these imply higher poles in beta. And there's actually some interesting structure also as one goes to large beta values, and we've already seen something like this in Stefan's talk, and I'm sure Nima is gonna discuss this later. But this is just to say that there is quite a rich structure in the complex in this complex boost weight plane. Now, in this talk, what the goal of this talk would be is to actually understand the complementary kind of dependence of this of the resulting celestial amplitude, and namely this its dependence as a function of this invariant conformal cross ratio. And so just to say a few words about where we're going. So of course, once given a celestial amplitude, so this function of beta in the Z, one should be able to reconstruct this momentum space amplitude, right? I just gave you a precise map. So one should be able to just perform the inverse Mellin transform and then decide whether the, what kind of momentum space scattering amplitude you get and whether that one makes any sense. But so again, if you're given, for example, the analytic structure in the complex beta plane, namely poles and residues and behavior at infinity and ... so like basically everything about the celestial amplitude, you should be able to reconstruct everything about the momentum space scattering amplitude, but this is not a very strong statement. What would be a lot more interesting would be to ask the question, what is the minimal set of data needed to determine the amplitude, the momentum space amplitude? And so, for example, well, similar questions have been posed, right, in the CFT community, for example, where we know, and Scott, I think, pointed this out in a discussion session, that in that case, we know that the spectrum and the OP coefficients, roughly speaking, determine the whole theory. Now, of course, this is very far from where we are right now for celestial theories, but nevertheless, I think we've seen some evidence in the interesting talks we heard so far that one may hope that something like this, or at least this philosophy, may apply to celestial theories as well. And so one more modest question would be, for example, whether one can find some set of operators, which again, as I said at the beginning, obey perhaps some algebra, which could compute, which then, you know, if you knew just their algebra in the form of, for example, some sort of OP expansion, would allow you to just compute the z dependence of these amplitudes. And then given also this pose in the location of the pose in beta, then you would be able to reconstruct the full celestial amplitude just from this. So just to, again, recap, something which has also been discussed this morning is that there is some indication that the celestial theory does have some kind of OP structure. And a simple way to see this, which was, I think, first pointed out a while ago by just taking direct Mellin transforms of collinear limits of momentum space scattering amplitudes, is that, for example, gluons on the celestial sphere, so here O delta 1 plus and O delta 2 plus A and B are positive helicity gluons. Just purely collinear factorization in momentum space implies this sort of OP structure on the celestial sphere. And interestingly, these OP coefficients, the leading OP coefficients, were by explicit computation shown to be given by simple functions of these Euler gamma functions. So this is also known as the beta function. And the fact that the beta functions actually are fully determined by recursion relations inspired us to try to actually derive these coefficients just entirely within the celestial theory. And so in this work, we saw that actually just imposing pretty much the subleading soft gluon theorem is sufficient to actually determine these coefficients. So this recursion relation can be shown to imply translation invariance, which is also a recursion relation. But essentially, these two equations completely fix this function up to some number. But this number can in turn be fixed by the celestial soft theorems. So this is nice, and as Shamik very nicely told us this morning, one can generalize this to gravity and also to subleading orders. And the natural question would be whether one can hope for something more like in celestial, in usual conventional conformal field theory. So here is a usual OP expansion one starts from in a conformal field theory. This is implied, this is a very rich structure, and it's very particular to conformal field theories. And it's actually a very, very powerful constraint, which allows you to actually construct 4-point functions, just using conformal invariance and by knowing these coefficients and the operator spectrum, one can build, can actually construct these conformal correlation functions in conformal field theory. And so this just follows by just starting in usual conformal field theory. What one would do is to just replace O1 and O2 by their OPEs. And then what's left over is some 3-point function involving all of these primaries OK and O3 and O4. So this is where this other OP coefficients comes from. And what this K does, so this is also known as a conformal block. So in this case would be an SL2C conformal block. What it does is a resumming the contributions from a primary of fixed dimension K and all of its descendants. So I should point out that this structure, again, so the structure is very special to conformal field theory. Like naively, one can expect any function with SL2C covariance or any SL2C invariant function to have a decomposition of this form. But as far as I understand, the fact that these coefficients factorize are actually a signature of the fact that the OP exists. In general, one would get, in principle, a mess, and these coefficients here would not obviously factorize into anything nice. And so one natural question, so I mean, and now you might complain that, of course, it's not obvious that celestial theories are characterized by such a complete set of operators obeying such an algebra. And the simplest observation would be that we just saw from Michael's talk that 2- and 3-point structures of massless particles, for example, are very singular. And so naively, you could just say, oh, but this obviously cannot hold because I can just take O1 to be a positive helicity gluon and O2 to be a negative helicity gluon, and then just plug this into the usual 2-point, just take expectation value, and then we'd find that this 2-point function, just this 2-point celestial amplitude is just 0, basically. But we know that that's not actually, or actually not 0, but it takes the form, rather from the contribution of the identity here, you would find the more traditional kind of like 2-point function you'd expect in conventional conformal field theory. But we know that that's not actually the case. We know that this 2-point function is actually given by a delta function in Z12. So, and similar kind of arguments, you can try to do this for 3-point functions, and you run in all sorts of puzzles, and perhaps some of the stuff has been hinted at before, so you may have to change basis and perhaps consider shadows, and we don't fully understand what the best set of, say, even conformal primary wave function one should use to have the celestial theory be as close to a conformal field theory as possible. I think Andy has a question.
Yeah, I mean, we have operator product expansions in 4 dimensions, right? That's where
we do.
That's
yes.
where Wilson first started talking about that. And wouldn't one expect, or is it possible that there's an argument where you just start from the operator product expansion in 4 dimensions and rewrite the operators in a celestial basis, and it turns into an operator product expansion? And I thought that's kind of what people were doing when they were redoing the collinear singularities, that those were.
Yeah, I mean, I think, wait, sorry, are you referring to like in QCD, right? People are using these OPEs to say things about
well, not just QCD. I mean, in all of quantum field theory, one thinks about an operator expansion, and I imagine, though I don't think anybody's ever tried to make it precise, that there might be some argument that you take the 4-dimensional operator product expansion and you rewrite the operators in this basis, and it turns into the 2-dimensional operator.
I agree with you, but I think I've gotten complaints while giving some other talks about the fact that in usual quantum field theory, the operator product expansion doesn't exist. So maybe for reasons I don't completely understand, but perhaps it's not convergent because we don't have a state operator map. And so, like, I'm not sure if I'd love to hear about that. But in any case, I'm not trying to advocate that there is not. Actually, I'm going to try to say that I think that there is some kind of structure like this, which we can see, and we can actually perhaps find by, I'm trying to advocate for the point of view that perhaps just studying celestial 4-point functions or perhaps higher point functions would allow us to deduce what the structure would be. But I agree that, okay, I wouldn't know how to do it by starting from 4-dimensional. I just don't know which theories would admit like such an algebra, basically.
You might be able to do it at
I think it's always better to work it out in detail than to give a general argument. But I always imagined that there might be some general argument.
Yeah.
But this is a short distance expansion. It's an X space.
So we like.
It's a different story because you're more in momentum space. Yes, you go from momentum space to celestial basis. But
here's an idea.
In 4 dimensions, just short distance expansion. So
you can do
relation.
Like, so let's get back to Anna's talk, but I do want to say one thing on that point. I think that both of you guys are right, but there is an extrapolate dictionary for light ray operators at null infinity. So once you interpret each of these like states that we're creating for these operators as being light ray integrals along null infinity, you could probably do the position space there at like 2 light rays along null infinity. And then it's a free, or it should be a free theory. So things might be simpler as far as what Anna was bringing up.
Sure.
I think we should take this to discussion because we want to let Anna talk.
No, I agree with that, but I think even light ray operators are very special kinds of things, right? They're just like soft, in some sense, they're kind of like soft mode.
No. If you have all delta, you should be able to capture everything. Should be like a light ray operator along null
Okay,
infinity.
that would be great. I agree. That would be great, but I think we don't. I'd love. Yes, I think.
I think like we started something like.
I'm hopeful that may be the case, but anyways, I think that yes, that would be really great.
Anna, your call. Do we want to like take Shuhan's question now, or if this discussion is getting too long?
Yeah, no, sure, we can. Sorry. And by the way, I just have 2 screens, so I'm actually looking at you when I'm not looking at my screen.
Great, Shuhan.
Yeah. So I have a question about the previous slide, the OPE.
Yes.
Oh, maybe the.
Sorry. Yes. This.
Oh, maybe the one before. Sorry.
Okay.
Yeah, this one. The first equation.
Yes.
Is it obvious that this OPE is associative?
So actually, this is a great question. And when we worked this out, there is an alternative. And I think perhaps we even discussed this briefly at this point, at some point in the past. But one can also get these coefficients by using associativity of the OPE. I think it's quite remarkable. So we haven't discussed it in the paper, but you can take O delta 1, delta 2, O delta 3, and then use associativity. And that actually gives you order by order, like basically like quadratic constraint on these P's. And that quadratic constraint is also non-trivial. And it seems like just by trial and error, I wouldn't know how to solve that one, but by trial and error, its only solution seemed to be this structure at leading order. But it is very interesting to look at sublead. And yeah, it's very important to use the full OP expansion when one does that thing.
And because this is a question that seems super relevant, I noticed there's one in the chat. Is it also associative if helicities are different? Prahar is asking.
Oh, so it's subtle, so I don't fully understand the case of different helicities. I don't remember now what. I think in the large class of examples, at least to leading order, associativity was able to, basically for all coefficients we derived in this paper, you would be able to check them in parallel. I think it would be a complementary way to check these formulas, just using associativity, and you find the same answer. Or at least that associativity, in some sense, we don't know, at least I don't know why this should be associative, but associativity conditions rather are obeyed by these functions, which I think we know to be true from just collinear soft limits in momentum space, at least for once. So I think there is some interesting structure there. So, but we had issue, like here, there were also subtleties when you had positive and negative helicity gluons. So one wasn't able to use, I think this is also perhaps related to Shamik's talk this morning, that one was only able to use one of the constraints from the subleading soft gluon theorem to derive this coefficient. In any case, yeah, so I think the short answer to Prahar's question is, like, if you look in this paper and all the solutions you find here, you can reproduce them using associativity. But whatever we didn't find there, perhaps have been worked out. I mean, of course, you've seen that a lot of work has been done since, and people have been studying like subleading coefficients. And I would expect that everything that can be derived from symmetries probably has also some interpretations coming from associativity.
And is there any reason that there's no level term, like k over z squared?
I think this is a tree level. This is tree level expression. I think at loop level, there would be.
Okay.
But that
Now,
wouldn't it take you outside the? Wouldn't it take you outside the principal series? It would take you outside the principal series. It was other powers of z.
I would have thought that you'd have a term that's like a delta function identity term. I mean, depending on whether it's in or out, I guess the helicities from like a particle just going through if you had the full amplitude and not M.
There is some momentum space argument where you can fix, I mean, the larger singularity you can have here. Like you couldn't have arbitrary high powers of 1 over Z12 because of like the way propagators, like from the Lagrangian, you can deduce that the leading piece would go as 1 over Z12, I think. Yes, I think you can see that. Yeah, that there couldn't be, if you map everything back to momentum space, at least at tree level, I think there couldn't be a 1 over Z12 squared term.
But maybe, okay, but maybe for some special value of delta 1.
Yes. So like when you have you remember like in the paper where you have these the Katsumuri level, if you created the operator, so if you might have to shadow or something and get that on the left-hand side, there should be like those two give identity times like the level.
Sure. I mean, with the shadows, I agree that there is perhaps a lot of, yeah, I don't understand the shadow story. Okay, there's more questions. Yes, I'm happy to take them now, but hopefully I'll get the time to finish.
I feel bad that I might have let this get a little bit. If I think the hands went down, so let's do this all after the talk. So we let.
Oh, okay, great. Okay, so right, so I had this point, and yeah, of course we don't know, but it's plausible that it's true. There is some evidence for it, and now. Another thing people have complained about, and you know, this has been brought up in many discussions prior to this, is that all 4-point celestial amplitudes are multiplied by this delta function in z minus z bar, and this is pretty ugly thing. So it prevents factorization into holomorphic and anti-holomorphic parts of the 4-point celestial amplitude, and you may think that this is also a problem. And indeed, in some other works, in particular also in Michael's, it's been advocated that perhaps one should just strip it off and decompose everything else. In any case, a simple question, so just irrespective of all of this, a simple question one can still ask is whether the celestial 4-point function has decomposition into SL2C representations. So in other words, can we decompose a celestial 4-point function into complete basis of the 2-particle conformal Casimir? So again, this is an analogy with Michael's talk, but there he was using the full Poincare Casimir. Here we're asking even a simpler question, or something which seems like a simpler question, namely whether we can do ultimately a conformal block decomposition of the 4-point function. And again, this is not new, and this has been also studied in a previous paper very extensively in some particular kinematic regime, and it's been written in the form of a conformal partial wave decomposition. But as we'll see in a moment, to get from the partial wave decomposition to a conformal block decomposition, one has to do a contour integral. And this contour integral is pretty subtle because there are a lot of poles and zeros, both coming from the partial wave themselves and from the coefficients. And one has to be careful to take everything into account to arrive at an expression which may or may not look like something like this. Right, but in any case, I think it's a well-defined question, and one can ask it, and it has been asked before. Okay, so just to review a little bit. So what I was going to say, the idea is very simple. We want, and again, this particular method has been used in the CFT literature a lot at this point. So it's the idea of finding a complete and orthogonal set of solutions to the SL2C quadratic Casimir acting on two particles. And I'm going to spare you the details, but what happens at the end of the day is that one can recast this equation as a differential equation, which acts on some functions. So I'm also suppressing dependence here on the 4 external dimensions. And also in these dz bar are differential operators, which you can look up in CFT textbook, and they actually combine into something which is a hypergeometric equation, which admits two solutions. So one of the solutions which we're familiar with is the conformal block. So it takes a very explicit form in terms of a hypergeometric function, as you'd expect. And in the limit as z goes to 0, it should scale as z to the h, which indicates at the end of the day that the operator being exchanged in some channel. So here I haven't specified. You can do this. You can write down an equation for any channel, but anyways, so some operator exchanged in this particular channel given by this equation would have dimension h or weights h and h bar respectively. So this is how the solution looks like, but of course, any second order differential equation is actually has two solutions, and the other solution is so-called shadow block. And then the question is whether we can find the linear combination of these two solutions, which is orthogonal and complete. So the conformal blocks themselves are known not to be complete and orthogonal. Nevertheless, again, this stuff has been done before. There exists a particular linear combination, which I'm not going to write down because then the formulas are going to get out of control. But one can construct such a complete orthogonal set of solutions to this equation. And then one can ask the question, well, if we have such a set of solutions and they form a basis, so then in principle, we should be able to decompose celestial 4-point amplitudes in this basis. Now, one perhaps annoyance is the fact that actually physical celestial 4-point functions have this cross ratio be constrained in one of these three intervals, depending on the kinematics, basically depending on which particles you're taking to be incoming or outgoing. So here we're going to be interested in the simplest example where this cross ratio is constrained to lie in the 0-1 interval. I'm going to describe this particular configuration in a moment. And so it would be really nice if there was a basis which was actually complete on this interval. I mean, most of the literature so far involves conformal partial waves over the full complex plane. But somehow, if you just think a little bit of analogies with Fourier transforms, you would see that things may be easier if one actually had to decompose an amplitude which is only defined, which is a 0 outside this interval. It would be very convenient to actually have a basis which was orthogonal on this interval itself rather than on the full complex plane. But fortunately for us, this problem has been recently at least addressed in some paper here. Where the main assumption, which maybe is not such a weird assumption because Shamik also made it this morning, that if we treat the z and z bar independently, then there exists a complete basis, which is just the product of basically SL2R conformal partial waves. So you may complain that now we're changing the problem. We're not studying the Lorentz group, but we're looking at SL2R cross SL2R representations instead. But nevertheless, it turns out to simplify things a lot. And we've also seen some nice and perhaps related ideas in Andy's talk yesterday. And so this would correspond to going to 2-2 signature in the bulk. So now the spaces then can be shown to be orthogonal and complete. And the orthogonality and completeness relation actually can be expressed just using these holomorphic and anti-holomorphic factors. So you have an inner product of each of these factors, which takes this form, and also a completeness relation, which takes this form. And I should draw attention to this particular z dependence here, which actually is going to turn out to also show up in the amplitudes you're trying to decompose. And the reason why, we'll see that there are some simplifications which happen when you're trying to decompose celestial amplitudes because of this factor, essentially. Okay, so if we started off by studying the simplest possible example, which is the case of 2-to-2 massless scattering at 3 level, where we are looking at this particular kinematic configuration. So we are taking particles 1 and 2 to be incoming and 3 and 4 to be outgoing. This is the same as the kinematics I described at the beginning, that the cross ratio is a ratio of T and S. And in particular, we see that, so first of all, such amplitudes are defined in this interval for Z between 0 and 1. And in particular, as a Z, we can see that we can reach the limit as Z goes to 0 as we take particles 1 and 2 close to one another. And so it's natural to ask the question what the conformal block decomposition, or at least initially what the partial wave decomposition of such an amplitude would be in this 1, 3, 2, 4 channel. So to do this, again, we start from the general form of the celestial 4-point function I introduced at the beginning, but it turns out to be convenient to rewrite this symmetric conformally invariant prefactor in terms of a conformally invariant prefactor, which essentially for equal external weights reduces to Z13 to the 2 delta times, 1 over Z13 to the 2 delta, 1 over Z24 to the 2 delta. So this is more tuned to this particular problem of studying this kind of decomposition. And of course, these two, we know that these two prefactors have to be related by a function of Z. And you can work out what the relationship between these two factors is, and you find that the remaining Z dependence then takes this form. So, and as before, the remaining piece of the amplitude then is a Mellin transform with respect to omega and with respect to this beta parameter. Now, I should also draw attention to the fact that the Z to the beta divided by 2 here can actually be absorbed into a redefinition. I mean, you can do a change of variables basically on these arguments to actually eliminate this Z to the beta dependence. So this factor here is just purely from choosing to write the Mellin transform, the relationship between the momentum space amplitude and the celestial amplitude in this form. But we'd want to, right, so now what we want to do, of course, we want to take the simplest example and try to study this conformal block decomposition for the simplest example. Perhaps the simplest examples actually turn out to be, to correspond to amplitudes, functions of S and T, which are actually just functions of T. So here for simplicity and just taking it, so of course a constant is also just a function of T, but I could have taken something which just has a pole in T, or could have taken some sort of polynomial in T. Like any such things would actually give rise to a Z dependence, which is just given by this function here, up to some other function which could potentially depend on beta in a complicated way. So with this assumption, but again, you may complain that maybe this looks singular, but in fact, it's a lot more functions, a lot more amplitudes of scalars actually are captured by this Z dependence. Now we can go ahead and just decompose this. And okay, so I'm not going to go through all of the details, but the idea is that, okay, we take this function, and given the facts about these partial waves I mentioned before, one can write it as in this way. So this is in the form of some kind of expansion in the spaces. And these coefficients here are the crucial things, and they can be worked out using the fact that these psi's are orthogonal. So you can take the inner product of the left-hand side and the right-hand side of this function to actually compute this f, and then plug it in as I said, deform the contours in both H and H bar and pick up the poles and make sure that the poles cancel with the zeros and whatnot. Anyway, so after you do all of that, at the end of the day, you find a formula. And this formula actually, I think, takes a pretty remarkable form. I think we tried many different ways of doing this before, but generically, and I think Michael knows very well that there are some miracles which sometimes happen. In general, these functions are just generalized hypergeometric functions, but somehow in this case, they just turned out to simplify. And at the end of the day, you find something which looks very much like a conformal block decomposition, I would say. So let me explain this formula, or at least as far as we understand it, a little bit. There is one piece which you can see immediately that it corresponds to a tower of exchanges of dimension delta 1 plus n and spin 0. You also see from this that the coefficient factorizes, and you may be worried about this, n factor here, but actually once you take into account things like normalizations of 2-point functions, you find that this is exactly the inverse 2-point function, which ensures everything combines such that up to these cosines, the OP coefficient, or whatever these coefficients here, are nothing but the coefficients which appear in the 2-point function of 2 massless and 1 massive scalar. So, okay, the fact that this is a massive scalar is purely just based on the fact that we know that this 3-point function takes this form, but of course it could be that there is something we don't, that somehow, you know, this may be some massless thing, and perhaps this is telling us about some more interesting, I don't know, 3-point structure involving 3 massive scalars, for example. But in any case, this is, you can just take this decomposition as telling you that actually there is some kind of operator product expansion where in the OPE of 2 massless scalars, there is this object of dimension delta equal to 1 plus n and spin 0. And this also tells you that the 3-point function take the 3-point functions, this operator with these 2 massless scalars, then takes this form. And this form can be identified with this standard form of this 3-point function we saw before. Now, another thing which is interesting and perhaps was expected is that we see, so the dimensions of these operators appearing in this expansion differ by n, and this seems to be a signature of translations, because we know that acting with translations on an operator of dimension delta raises its dimension by 1. So there may be a way to naturally interpret this tower as a kind of building up the Poincare representation at the end of the day. Now, a term which is perhaps more intriguing and which we don't fully understand at this point is this term here. So this takes the form of a conformal block associated, you can just count dimensions. So this turns out to correspond to an operator of dimension 1 and complex spin. And it just so happens that these dimensions, these weights match exactly with what in the CFT literature has been identified as, or defined as light ray, so-called light ray operator. And there are features why, okay, you may ask, why am I not deforming the contour or whatever to find another discrete piece like this? Well, it turns out that you can actually, sorry, can you hear me?
There was a moment there where I don't know if it was my internet or yours, but
yeah, because I saw the connection was unstable. I apologize. I can repeat. So, okay, so the this light ray, so-called light ray block, we don't fully understand very well, is important because you can try to deform the contour, but the contour turns out that you can only deform it when z is different from z bar. But of course, when z is different from z bar, you'd better get 0 on the right-hand side, because otherwise you get a formula which doesn't make sense. On the left-hand side, you get 0. On the right-hand side, it has to be the case for when z is different from z bar, that you get the collection of poles here, which exactly cancel all of these terms. And can actually check that this is true. So this is a check that this formula is correct. You can also see that the contour cannot be deformed if z is equal to z bar. And in fact, this is the term which gives rise to this delta function in z minus z bar. So we really, this term seems to be important, at least in the composition of this formula. Now, here are a bunch of things we don't really understand. So Michael has described these constraints on celestial 3-point functions. Naively, one may say, looking at these cosines here, that perhaps it's natural to like just absorb them into these coefficients of these 3-point functions. But actually, they don't seem to obey these. They almost obey the periodicity condition, but they're not periodic under delta goes to delta plus 1, but rather under delta goes to delta plus 2 for some reason. So we don't fully understand this. I mean, as Michael also explained, like, these would prevent perhaps the celestial 3-point function having an interpretation in terms of a bulk 3-point function. So yeah, they may also arise, maybe there is a way to think about this whole thing as some kind of like Lorentzian conformal block, but again, we don't have at this point the full understanding of these prefactors. But nevertheless, I would say that the remarkable thing is that this by itself doesn't prevent factorization. What seems to prevent factorization, though, is the fact that we have this beta function, the beta-dependent function sitting out front of this amplitude. And I would say basically like most amplitudes we can cook up will have some kind of function of beta. And this is bad because the function of all of the sum of the external dimensions. So that clearly cannot be written as a product of things which just depend on delta 1 and delta 3 and delta 2 and delta 4, as one would like to. Now, some potential resolutions to this puzzle would be to perhaps, yes, Andy?
How does it happen that the first and the second term cancel there when the first one doesn't depend on the external weights, but the second one does?
The first
they
one
cancel
also,
when z is not equal to z bar, so that we get the delta function, right?
Yes, exactly. So by the way, this guy depends on the external weights. Like the blocks.
Oh, the case depend on external weights.
Yeah,
right,
yeah,
right.
The case depend on.
Okay, okay.
So that's important.
Just suppress the note.
Yeah,
okay,
and since we're here, also I should say that you may think like, oh, but this doesn't look like it has nice OP coefficients. But what's intriguing is that the fact that the OP coefficient here seems to be 1 in some sense is perhaps not that weird, because if you look at this light ray literature, you find that 3-point functions of 2 operators in the light ray transform, if the original 3-point function before taking a light ray transform was normalized such that its coefficient was 1, the 3-point function involving the light ray operator takes exactly the form of 1 over a beta function, which is the same as the beta function in these coefficients. So given that the 3-point functions of the unlight ray transformed operators take this nice form of a beta function, once you take a light ray transform of this exchange, you find basically 1. Given this normalization of the 3-point function, you find that the normalization of the 3-point function involving a light ray operator should be 1. It just so happens. So it's perhaps not that weird that here it looks like we don't have any OP coefficients. Okay. Now, yeah, so what we do, I would say the main problem at this point, which I guess has been bothering us for a while now, is the fact that there is this beta function, the beta-dependent function sitting out front. So how are we supposed to think about this? Andy has already told us yesterday that there may be a sense in which perhaps one could trade this basis of conformal primary wave functions written down by Sabrina and Shuhang and Andy for some other kind of basis, which may be more naturally defined in a 2-2 signature. And this so-called basis of L primaries, the wave functions then have integer weights. So of course, this is not this thing we're computing here is not a celestial amplitude in that basis. But it may be that that there is some alternate basis in which complete basis, Intrahart has also been hinting at that, and also Laura and Sabrina and Andrea, perhaps there is an alternative basis of just integer weight wave functions. Perhaps there is a reason to restrict to integer weights, in which case the problem seems less bad in a way. Although, then you could ask the question, okay, let's say we tune these 4 weights to something like, for example, a negative integer, such that they add up to some value of beta, which lands on one of these poles, which Nima will describe in a moment. So in that case, the celestial amplitude blows up. And you could say that for this particular configuration, the interesting thing one should be looking at is the residue. And so with that interpretation in mind, what I think we have some evidence for is that some particular class of residues, namely the ones which have this functional Z dependence, factorize or have a nice conformal block decomposition. Now, it would be very interesting to study, for example, all other residues. We also have, I haven't talked about them here, but we can do, using this formula I showed before, one can actually decompose any such functions where these CZs are basically powers of Z or powers of Z divided by 1 minus Z and stuff like that. However, in those more complicated, somehow just simple powers of Z or Z divided by 1 minus Z seem to be screwing up factorizability. So you're not going to get something which has this nice form, but here you're going to get a mess of generalized hypergeometric functions. But perhaps it's not unconceivable that if one restricts the weights, the external weights to be integers, that those coefficients will also factorize. And I think that would be, in particular, I think we can look at that and see if that's the case. I think that would be very interesting. And finally, I'm not sure, perhaps one should hope for more than factorization on this pose, but at this point, it's a bit hard to imagine how that could be the case, because we saw, and Nima is going to emphasize this later, that the celestial amplitudes do have this interesting pose structure in beta, so it's kind of hard to imagine how one could get rid of it. It would kill a lot of interesting physics. So just to sum up, I gave, I hope, some evidence that there is a sense in which the analytic structure in the complex beta plane and some sort of celestial 3-point functions may determine some celestial 4-point functions. Of course, this is very preliminary analysis, but I think it's an evidence for this. And one should continue studying this. I think it's an interesting question, and I think at the end of the day, as Andy also pointed out yesterday, I think would like to understand whether the constraints in the celestial theory could, for example, fix the Graviton 2-to-2 scattering amplitude, for example, in full quantum gravity. And along these lines, it would be interesting to study crossing symmetry for these formulas. And ultimately, I'm not sure if this is going to be possible, but there may be a way to kind of set up some kind of bootstrap program for celestial amplitudes. I think that would be extremely interesting. But of course, I think the first step, and this also ties back to many other talks, would be to try to figure out what the operator content that algebra is in the celestial theory, and also understand better the role of these shadow transforms, light ray transforms, and so on and so forth. So with that, I think I'm out of time. So thank you very much.
Thank you very much, Anna. Now, I noticed that there were some questions before, so let's maybe get back to them if they weren't already addressed. Shuhong, did you still have a question? Or I forget it was Shuhong and Scott were asking before. Otherwise.
Sorry, I was clapping. That was.
Oh, no, no, a long time ago when I kind of cut you guys off. I wasn't sure if there were more questions. Good. I think it sounds like you addressed all of the concerns. It's wonderful. Oh, Laurent has a question.
Hello, Anna.
Hi.
Can you hear me?
Hi, Laura.
I have a question. Can you go back to your formula about the factorization of the amplitude?
Yeah.
Yes. So, in fact, I was wondering about what you put as a question mark there, because as you mentioned, usually when you have factorization, so you need to have this factorizability, but there's an extra constraint that comes from unitarity, right? The fact that this coefficient there should be the 2-point function and it should be positive definite, which is often
which coefficient should be 2-point function? These should be
the one that's pairing the two blocks, right? So this
yeah, but that one is already taken into account. That's the reason. This n here is actually that.
The n times the cos. I'm worried about.
Yeah, so the n here should be thought of as basically the inverse 2-point function of this thing, which ties things together. But that thing doesn't have cosines in it, sadly.
Yeah. So what I'm worried about is this cos seems to have oscillating signs, right? Which would prevent unitarity to happen. So is it too early to worry about because of the problem of the factorizability of delta beta, or?
Is this more than what Michael was talking about? That it might prevent you from inverting?
But all you need is that the pairing between the left and the two blocks needs to be a positive definite matrix, and here clearly this cos n over 2 is not a positive definite matrix. So therefore,
yeah, but this is why. Yeah, this is why we don't. I mean, naively. Right, I see what you're saying. Yeah, I'm not sure how to do. I would love to know how to deal with this, basically, but I don't know. There are formulas which look like this when in these formulas for analytic continuations of Euclidean conformal blocks to Lorentzian. But I don't think we have an interpretation of this factor at this point. Yeah, sorry. But I do see what you're saying. Yeah, they're a bit weird.
Okay, if that answered Laurent's question, then I think Andy was next.
Yeah, well, I mean, we don't expect a comment. I mean, I guess we don't expect two-dimensional unitarity. We have negative conformal weights or complex conformal weights. So I don't know why we would want this to be. We have four-dimensional unitarity, but not two-dimensional unitarity. So I don't know why we would necessarily expect that to be positive. And actually now looking at it, it actually is positive. I don't actually understand. I mean, it's close to positive. I don't up to these cosines, but yeah, well, maybe it's the cosines. But a question for so I guess if we take the philosophy that we want to, at least for now, understand the integer weights, a lot of these issues disappear. But then how do we reconcile that with this continuous light ray spectrum? Yeah. And would these light ray operators, would they be defined on the celestial torus, or?
Yeah, so that's a question which I think we wanted to I definitely want to look at that. Naively, it seems like they should be defined in the celestial torus story. But
they're sort of line operators instead of point operators, so maybe they're not quantized in the same way. Is that right?
All of our operators are.
Yeah, no, that's a bit confusing. I'm not sure how to talk about it.
And is your Lorentzian square, is that the celestial torus, that Z and Z bar?
I think there is a relationship via the tangent map with coordinates on the causal diamond on the torus. Yes. I think you have to, I mean, promoting Z and Z bar to be independent variables is the first step. And then I think you have to do this conformal transformation, which then maps you to a part of to the celestial torus.
Yeah, But things are not periodic in Z and Z bar, so it's not quite the
No, yeah, that's a good point. No, they're not periodic in Z and Z bar. So I think. Yeah.
Okay, thank you.
Okay, then Scott.
Thanks for the really nice talk, Anna. So just so I understand, the starting point for this conformal block decomposition was a separate principal series decomposition in both H and H bar?
Yes, indeed.
Okay,
It's
so that's...
No, but naively, these guys who wrote this paper actually show that this prescription, once you deform the contours, they recover a lot of these results.
It's equivalent to the...
Yeah.
It's supposed to be equivalent to the conformal partial wave thing where you have quantized spins, but you decompose each dimension. And okay.
Yeah, but here, right. But the thing here is that since you're taking Z and Z bar to be independent variables, there is no quantization condition on the spin, right? And so like you're allowed to have H and H bar to be both on the principal series. And this is the reason why, as far as I understand.
Ooh.
But at the end of the day, once you deform the contour, once you deform the contour, you already see that there are these complex spin things appearing.
Yeah. It's just that's definitely not manifest from the standard conformal partial wave decomposition.
No, I agree with you, and I think to understand the relationship to the Euclidean decomposition, for the longest time we tried to do the Euclidean decomposition in this channel, and it turns out to be. I should point out this is, I think, as far as I can tell, is not related to the paper Michael, for example, worked on. That was in a different kinematic regime, I think. So, yeah, somehow we don't. I think there should be a relationship between this and the Euclidean decomposition, but we don't understand.
Yeah. I mean, they ought to be.
Do you know what changed between? Yeah.
What changed?
Oh no, just like because I think we were stuck for a while trying to do the Euclidean one, and then this one seems to have gotten you further, so that's nice.
I mean, generically, as I said, and I think this is an important thing. Like, if you don't have generically, if you just do a decomposition, you can always ask the question: what's the decomposition of a conformally invariant function into conformal blocks?
Yeah.
The thing is, these coefficients here generically are going to be a mess. You need a very special kind of 4-point functions. Very special Z dependence, which would give you this factorization. And I think this in turn would imply some kind of OP structure. And I think that's the interesting thing.
Yeah, so, I mean, every solution to crossing is a miracle in a sense.
Yeah, so I don't know. I think that on the one hand, this formula looks like a complicated, like, why would you even do this? But on the other hand, it tells you that you can build a delta function by just taking like these kind of operators and knowing their OP coefficients, and then you can sum them all up and then create this delta function in Z minus Z bar. It's
it's pretty cool. And just another small comment is it doesn't look like this thing can be decomposed into Virasoro blocks. Do you find that surprising? Just because there are only scalars here. And
this is just scalar, right? But on the other hand, this up to powers, I think, gravity amplitudes and so on, the only thing which would be different would be like a different power of Z here, which would basically indicate the spin. It's related, I think, to the Regge limit. Like, in other words, you have things going like Z to the S to the J divided by T, and then that would give extra powers of Z here. So I think if you were looking at a tree-level amplitude, then you would similarly have to just decompose something which still looks like this, but with a different power. And that part seems to be messing for generic H13 and H24, and in particular for things on the principal series, that seems to just give just hypergeometry. Basically, these coefficients are then just the F43s, which don't seem to be simplifying generically. So, yeah.
Okay, I think Atul was the next with the hand raised.
Thanks for the great talk. I was wondering, just to try to recognize what this light operator contribution might be, and also maybe to understand maybe if you get lucky, understand factorization, can we try to go back to momentum space and see how these two parts add up to the full 4-point MHV expression? we try to go to momentum space and like see what this light ray operator piece is giving you in momentum space, because we could try to see if there's some analog, something like a soft limit, but some other limit in which the amplitude just sort of limits to the light ray part or something like that.
What do you mean study, in momentum space?
If we do the inverse Mellon transform, we
yes.
can, in principle, take this expression back to momentum space, but while keeping the light ray part and the second line separate, you can try to see how they recombine into the MHV amplitude expression.
Right. Yeah, but it's a bit hard to imagine, right? Because these blocks, each of these terms in this infinite sum and everything, they all depend on all of the external dimensions. And by the way, the fact that this, yeah, it seems, in principle, it seems like something you could do. In practice, yeah, maybe that's an interesting question. I'm not sure. It just seems a bit hard. Like these conformal blocks, right? They're hypergeometric functions that depend on H1, 2, H3, 4. These guys also depend on those things. There are these costs. Yeah. I'm not sure how easy it would be to invert this term by term.
This is that, like you can sort of determine that one part is like the contribution from the collinear limit, which is basically the soft limit, which is basically the term coming from the delta tending, the delta equals 1 term or something. N equals 1 term would be the leading order term.
But you already see that. You can take the small z limit and you can see that this expression makes sense. Yes.
So maybe to understand what the light ray part is giving us, maybe to, sorry, what?
No, but the light ray part is Roden life is to generate this delta function in z minus z bar. I haven't explained like very carefully.
So it's very hard to.
No, small z expansion. I should say, okay, basically, if you take the leading piece in z, you generate delta function of z minus z bar from the leading term. The rest, okay, it's more subtle. Yeah. Yeah, sorry, yes, Sabrina?
No, Anna, definitely finish your first one first. I'm sorry.
No, I didn't have much more to say. I was just saying that we did study the small z expansion of this, and I think it's consistent with just naively taking small z limit of left-hand side as it should be, because otherwise it would be a problem. So.
I just want to add one comment to Tools, what he's pointing out, because like you don't need to do the LSD formalism if you want to scatter massless like particles. You can think of it as a correlation function of a bunch of, for each instate you prepare it with like integrals along past null infinity for each outstate as correlators like integrated along future null infinity. You can do a Mellon transform directly in the saddle point approximation, and then you have an integral over u to some power of say a of like the leading value of like the photon field say at null infinity. So you already have this natural like light ray type structure in these it's like an extrapolate dictionary for these guys.
Yeah, I don't understand what the relationship between those light rays at infinity is and these ones, because these are light ray operators on the sphere, not in space-time.
Sure. So like you're integrating though over alpha though, which is not so, or integrating over z. Like they're like the light. Where is the light direction?
The reason you can find solutions. I haven't gone into this, but you can find they're basically holomorphic and anti-holomorphic shadow transforms. Like you just.
So, but on this 2-sphere, where is the light ray for you? If you're saying it's on the 2-sphere,
it would be an integral. Oh, yes.
Sorry,
the interpretation is some integral. Oh, here you just have x plus and x minus.
Really, it's legitimately on a. Okay, that's interesting.
Yeah, so I think it's a bit different.
It's not on the cone.
I would have thought it would have been like along null infinity, not along, and that's why
it's a standard light ray. Yeah.
I don't think it's. No, it's a light ray operator. It's in the sense it's in the 2-dimensional theory. There are 4-dimensional. There are light ray solutions, I think, in space. Okay,
in space time, I would have been more. I'm actually more surprised. That's interesting. It's very cool.
Yeah, we don't. Yeah. Anyway, should stop. So maybe Nima has a question.
Yeah, I have a qualitative comment and a question. So the delta z minus z bar is interesting, funny, or whatever, because 4-point kinematics lies in a plane, and the plane intersects the celestial sphere on a great circle. And delta of z minus z bar is forcing the 4 points lie in a circle. If we go to 5-point scattering, 5-point scattering is already generic, right? 5-point scattering, the sort of directions can go generically off in any direction, and so we would expect that the Mellon transform at 5 points should have generic support everywhere. And actually, the kind of converse of this issue starts happening at 6 points, because at 6 points and higher, of course, they're all there generically. But the point is that there are more singular configurations in momentum space that actually give rise to things that are smooth on the sphere. So, for example, if you sit on a factorization channel for 3 to 3 scattering, then you're forcing the intermediate line to be on shell. And so that configuration is actually also allows the 6 things to point in generic directions. So it would be interesting to see so that there has to be something about the Z dependence beyond 5 points. So 5 is interestingly the sort of the critical point, but beyond 5 points, there should be something about the Z dependence that tells you have a generic process in space-time versus a more singular one when you sit on factorization channels and so on. And I wonder if anyone has looked at what Mellon transforms, not of full amplitudes, but actually simpler things. It's related to something I probably won't have time to talk about, but it's related to questions about on-shell diagrams and so on the celestial sphere. But it's the most very basic kinematic thing. There are much more singular configurations for amplitude sitting on factorization channels that give you smooth things on the celestial sphere. So what's more interesting about the ones that actually correspond to full amplitudes? Anyway, as I said, it's a sort of converse of the issue of the delta Z minus Z bar at 4 points. There's a converse of that at 6 and higher points.
No, I think it's very interesting. But I think Michael, perhaps he has worked out some higher point amplitudes. And I mean, unfortunately, even I think the simplest ones, like just the one you're describing, where you have just a 3 to 3 scattering with some exchange. I think if you try to put that on the celestial sphere, okay, I haven't tried recently, but I thought that you get some nasty expression in terms of generalized hypergeometric functions. But maybe someone else. So it's a bit hard.
That's I think what I'm trying to say is that full amplitudes at 6 points and higher are probably much more complicated than the simplest things that you could get that would correspond to factorization channels. Then the higher ones are, but the factorizations will already be smooth things on the sphere. So maybe those are simpler things to sort of start looking at.
Right. No, that's very interesting. Yeah. Thank you.
Yeah. I mean, I think the first thing that like you can just, at least for fun, just play with Mellon transforming just the momentum conserving delta function in there, see how many relations you have, plug them into amplitudes and go from there. That was a route that like Shu and I and Andy were.
Yeah.
And something where one of the delta functions is coming just from the overall dilation of the energy. So you have like a different number of constraints than you would have.
The Brown group has actually solved.
Probably afterwards. Yeah, probably. Yeah.
Yeah. So I think, yeah, but the expression is still in integral form. So. Yeah.
Cool. Okay, I'll stop the recording. So awesome. We're going to close out today with a cool talk by Nima about celestial amplitudes and UV and IR. Take it away.
All right. Well, I'm really delighted to be able to talk at this virtual meeting. I'll be talking about at least one of the aspects of celestial amplitudes that got me very excited in thinking about them, and the sort of first sort of preliminary work in this general direction came out last December with Monica, Anna Maria, and Andy, and that has to do with the fact that it looks like thinking about celestial amplitudes is an ideal lens in which to explore the sort of UV-IR connection and mystery in gravity. So there's a very specific sense in which thinking about celestial amplitude is anti-Wilsonian, which from the perspective of thinking about gravity is a good thing. And that's what I want to tell you about. Just a few very preliminary comments. Many people have made similar introductory remarks. We're all inspired by the sort of spectacular picture of holography in anti-de Sitter space. that gives us our sort of first working example of this miracle of space and gravity and strings and all this stuff emerging out of quantum mechanics. Of course, this is an example, as has been stressed from the very, very beginning, where space emerges and the time on the boundary is the same as the time that flows in the interior of the anti-de Sitter bulk. And as we try to get closer to the real world and talk about either scattering amplitudes in asymptotically flat space, which is not quite the real world. Of course, the real world is even cosmological, but scattering amplitudes are a pretty decent start in talking about the sort of world we see when we look outside the window. Here, the immediate challenge is that when you try to take the holographic mindset and sort of go to the boundary and think of a theory that lives on the boundary, unlike the boundary of anti-de Sitter space, the sort of boundary of Minkowski space, which we can think of in many ways, but practically speaking, it's the kinematical data that specifies the scattering process, that tells you what the scattering process you're talking about. That's a less familiar place. It doesn't have an obvious notion of time or locality, and so it's less clear what you should be doing there. And at least to me, I've had this picture in mind. It's a more speculative picture. It's a more radical picture. That instead of having a quantum mechanical system on the boundary with sort of with space emerging, that we have to be looking for different kinds of questions, principles, ideas in this in the hologram at the infinity. And out of it, we'll see both quantum mechanics and space-time emerging sort of tied together. And that's by now, it's more than a vague slogan, because we do have sort of concrete sort of toy systems where we actually see this kind of thing happen. Before getting into details, I want to just say a few things about why this whole program is hard. So why is S-matrix theory, the question of determining amplitudes, just on the boundary in terms of the data of the scattering process, without talking about the picture of virtual particles propagating in the interior of the space-time. The actual amplitude is specified by data that we measure at infinity. So the sort of, so at least naively, the sort of holography in flat space and the S-matrix program sound like the same thing. But why is the S-matrix program not a well-defined program, in the sense that there's a well-defined sort of very hard, deep math problem that you can go and try to solve, and when you've solved it, you can check if you're right or wrong. As is the case, for example, for the Euclidean conformal bootstrap. So what's different between them? And the answer is has everything to do with time and causality, and it has to do with the fact that still, I think it's an embarrassment that in the third decade of the 21st century, we still don't have the answer to the question: what property of this asymptotic observable, the S-matrix, what property of the amplitudes has the fingerprint of having a system at least approximately with the bulk locality and causality? You can check Lorentz invariance, you can check unitarity, but what precise property these functions have to have in order to encode locality causality? And we don't have an a priori understanding of what that is. So practically speaking, it means that we don't have like a basis of good functions to expand the amplitude in terms of, for example, there are many aspects of this problem. Of course, since the 1960s, it's been realized that this has something to do with the analytic structure of the amplitude thought of as a function of complex momenta. Of course, it goes back to even thinking about dispersion relations in the 1800s. But we still don't know precisely what analytic structure the amplitudes have to have in order to be compatible with causality. And this was the sort of ultimate reason for the why the sort of principled S-matrix program of the 60s didn't progress. And today we can sort of see why this was and why it had to be at the most basic level, which already is a hint that if you're going to go down this line, you have to think slightly more unconventional thoughts. At the most basic level, the problem is that if you think that the singularities of the amplitude, the analytic structure of the singularities matter and somehow determine what it is, we don't even see all the singularities of even 2-to-2 amplitudes in real 3,1 signature Lorentzian momenta. So, the sort of dream of the program back then is that, well, the amplitudes have some singularities. The singularities have to do with particle production. And therefore, if we know something about the singularities, we can, which is controlled by unitarity, we can then sort of figure out what the whole answer is. And you can't even access all the singularities from physical momenta and 3-1 signature. For example, even for something trivial like massless scalar scattering at tree level, we think that we have this pole in S and this pole in T, and these are very important things. There's on the residue of the pole in S, you get the product of 2 3-particle amplitudes on the two sides and so on. But we can't actually reach S goes to 0 and T fixed in Lorentzian signature. Okay, so this very basic fact about the amplitude is not something that we actually have access to. Relatedly, as has already been discussed, this famous fact, the 3-particle amplitudes for any particles with spin on the outside for massless particles vanishes in 3-1 signature. Again, it's the most fundamental object, but it actually vanishes in Minkowski space. And what the people really ran into in the 60s is a more technical later version of the same kind of problem. There are things when we have massive particles, they weren't interested in massless particles back then, but even when we have massless particles at loop level, ultimately you find that there are branch points, there are singularities that do not correspond to any physical process in 3-1 signature. So that kind of puts a dent in the dream that you're going to use unitarity and singularity to determine the answer, because most of the action of the amplitude doesn't even exist in Minkowski space. And it's, again, an early hint that we're not going to put in as an input. This was the sort of dream back then, is that put in as an input causality and unitarity, and that somehow responsibly learn how to impose those constraints on the amplitude and get the answer. And now today it looks like that seems hopeless. And instead, what's been going on is a kind of backwards version of this question. And that's as a person who is not temperamentally responsible, this is my own attraction to the subject. We're not looking to slavishly, responsibly derive what causality and unitarity means and determine the amplitude, which didn't work anyway. Instead, we want to find a different question that does not involve the interior evolution in space-time, and likely not some evolution in Hilbert space. A different sort of question that's naturally formulated in this sort of kinematical space that specifies the scattering process at infinity. And we find some new questions to ask there, new questions, new principles, new ideas. And we just get the amplitude as the answer to some natural question and see that it has all these properties that we can later interpret as being associated with locality and causality. So that's again, it's a speculative but more radical point of view that we want to see locality, causality, and unitarity as outputs from some new kind of question naturally living at infinity in Minkowski space. Now, sort of my own trajectory through this subject over the past 10 years or so has been in finding interesting new mathematical structures and combinatorics, geometry, some aspects of number theory. Broadly speaking, positive geometries, this notion of positive geometries in this kinematic space, which we've been seeing in more and more examples over the past decade. But this is going to be a talk about the celestial sphere, so I want to say just something about the relation between these two sort of sets of attitude about this. So again, the sort of canvas in which we're trying to paint, trying to find a theory, is just the kinematic space. And there are many ways of thinking about the kinematic space. If you're kind of in, if you think about the amplitudes a lot, you immediately sort of think practically. What kinematic space means is n null momenta, or let's say the set of Mandelstam invariants, or maybe use spinor helicity variables to describe the external particles, or momentum twistor space. And this is your space. So now you see you want a theory, you want some kind of theory at infinity. That means that your space is the space of n null momenta, or a bunch of spinor helicity variables, or momentum twistors, or Mandelstams. In this kind of very arid seeming, boring abstract space, you have to find some question to ask there whose answer will turn out to have. Sorry? Was there a question? Hello?
If someone asks a question, please raise your hand because it's hard to see who it is without them. I assume not.
Okay, all right, sorry. Anyway, okay, so that's the sort of line I've spent many of my friends and I have spent a long time thinking about. Here, the kind of space is more abstract. It's not it's far from a sort of familiar looking place. But on the other hand, it's more closely related to the sort of practical expressions that we all know and love, that the answers actually are written in terms of. And we have been seeing in this setting, as I said, over the past decade and a lot more over the past couple of years, natural questions that are ultimately combinatorial and then geometric, a sort of general area you can sort of characterize as geomplitudes. In this kinematic space, you can find some interesting questions that have as an answer an object that you can then interpret as having all the properties that we normally ascribe to being local and unitary scattering amplitude. So we really see sort of first in the context of n equals 4 super Yang-Mills and the story of the amplitahedron, more recently in the past few years for completely non-supersymmetric theories, first at tree level and then at loop level last year, and next Monday and Tuesday we have the second series of virtual meetings on the subject that any of you who are interested are invited to, where I'll be speaking about the generalization of these ideas for non-supersymmetric theories to all loop orders and all orders in the one-of-round expansion. So there's even nothing to do with planarity. And we see in these examples that there is some sort of ab initio starting point that defines what the amplitude is, or the integrand of the amplitude is, depending on what you're doing. And you can see that locality and unitary emerge as derivative facts. All right, but this is going to be a talk about the celestial sphere. And here the advantage of the first sort of obvious advantage of the celestial sphere, even without knowing about all the beautiful work that's been done over the past 5, 6, 7 years, it's much more geometric. It's a more obvious natural place to build a hologram. And there's something just sort of wonderful about thinking that you look around at the sky around you and you're really talking about a theory that lives on the sphere that surrounds you. We've already learned many surprising sort of beautiful things about how IR physics especially is encoded in terms of symmetries on the celestial sphere. But what I want to stress in this talk is that it's also a beautiful setting to explore the UV-IR mysteries of gravity. And so I want to explain why that is. And really explaining why it is a sort of walk down the past 4 or 5 years of memory lane for me for a sort of second set of questions that I'd been thinking about. So I'm going to spend the next few minutes just sort of telling you a path that sort of leads you into thinking about wanting to think about celestial amplitudes from a different point of view. So that's what I want to explain before telling you more specifically about what we've been seeing. All right. So what's the why are celestial amplitudes particularly well suited for thinking about the UV-IR connection? First, let's just remember what the UV-IR connection is in distinction to is the sort of glory of the standard Wilsonian paradigm, which is the complete decoupling of the UV and the IR. And it makes perfect sense. It's the intuition that if 2 points are close to each other in space, in order to probe them, you need a microscope. So you need a microscope to probe short distances. There are 2 aspects to this story, which are well known and sort of worth emphasizing. One is that it's fundamentally Euclidean, and 2, we should also remember that it was beautifully borne out in condensed matter physics, where there is indeed a big difference between the UV degrees of freedom and what you see in the IR. But the real world is not like that in 2 important ways. It's Lorentzian, and that means that this distinction between short and long distances is not quite as cut and dried as you might think, because we can have 2 points where the distance is very small, but they can be macroscopically separated from each other so long as they're close to the light cone. Okay, so there's some way in which you could have a sort of window into high energy physics by looking at things that are happening close to the light cone. So, and this has teeth. So one consequence is that you can learn something which maybe it was not so obvious thinking from the Euclidean point of view, but you can learn about coefficient of higher dimension operators by the fact that if you have them and you turn on a background, you can make signals travel either a little slower or a little faster than the speed of light. So that's a sort of concrete sense in which this Lorentzian aspect of the physics lets you sort of learn more about the UV properties than you would naively think that you could do in Euclidean space. Now, this is true even in quantum field theory, where we know that we can just analytically continue from Euclidean to Lorentzian signature. This is just telling you that there are facts about Euclidean field theory that are sort of more obvious from the Lorentzian point of view. That's sort of interesting when we normally think about the Euclidean formulation as fundamentally defining what the theory is. It's surprising maybe and interesting that the Lorentzian physics seems to expose more than is sort of obvious from the Euclidean starting point. But of course, more importantly, the world is gravitational. There are many, many aspects of this UV-IR connection. One of the earliest and most famous ones is just that when you scatter particles at energy much bigger than the Planck scale, quantum gravity is in some ways easier than a garden variety non-renormalizable field theory, where you don't know ahead of time what happens when you scatter particles. Before we knew about W's and Z's, we had no idea what happened if we scattered electrons and neutrinos at energies 1,000 times the Fermi scale. But ahead of time, we know something about what happens when we scatter particles at energies way above the Planck scale. We make large black holes, and the black holes evaporate. And the degrees of freedom that come back out from that evaporation are softer and softer as you go to higher and higher energies. And they reproduce IR states that we've seen already in the things that we throw together in order to make the black hole to begin with. So that's dominantly what happens. And we expect that this picture also tells us that if I talk about the exclusive 2 to 2 amplitude, that the 2 to 2 amplitude is exponentially small as we go to high energies, reflecting e to the negative the entropy of the black hole with that energy. So this is also a big distinction from the Wilsonian picture. We know what the high energy states are. They're black holes, and they get bigger and bigger. And the consistency of black hole horizons and horizon thermodynamics and so on can imply, sometimes provably, sometimes conjecturally, it can imply, again, surprising constraints on infrared physics. Like the most famous example maybe is the existence of no global symmetries that you can try to sharpen a little bit into things like the weak gravity conjecture. And there are many, many other examples of this sort. Now, I won't say anything about this slide, but as someone who spent 15 years of their life thinking about the hierarchy and the cosmological constant problems almost every day, it's worth saying that the Wilsonian picture has a third sort of spectacular failure, not a precise failure, not an actual prediction failure, but a sort of qualitative picture not working failure, that the Wilsonian notion of naturalness that works beautifully in condensed matter physics, where naturalness was born, seems to just fail for explaining the most basic coarse properties of our world, why the universe is macroscopic, and why the weak scale is small, why elementary particle masses are much smaller than the Planck scale. All right, so okay, so those are some sort of famous aspects of UV-IR. And so now, I'll say a little bit about this the road that was traveled over the period of around 4 years or so to think about celestial amplitudes as the sort of playground in which to best think about these questions. So I want to begin with a very basic question: why is gravity, which is the most obvious force of daily macroscopic life, the hardest to UV complete? While much more hidden things, fancy hidden things like the weak interactions, which were discovered, in the late 1800s, early 1900s, it only took them 50, 60, 70 years to be UV completed. But gravity that we've known about, well, forever, but we started talking about it as physicists, still Newton is still something that we're struggling with today. This is a kind of a high school level question that you could wonder about. And I like this question because it's another aspect of the UV-IR connection. So let me illustrate, let me make it more precise. by thinking about a simple example like pi-pi scattering. If you think about pi-pi scattering, well, the amplitude at low energies begins as s plus t. It grows quadratically with energy, just like gravity amplitudes grow quadratically with energy. The dimension of the couplings are the same. And yet, this is a theory we can trivially UV complete. And we don't have to, from this point of view, if we're thinking about UV completions that are quote unquote at tree level, so that means that the amplitudes only have poles, then you can just play a game. You say, oh, this amplitude is growing. I just want to fix it in such a way that it stops growing at high energies. So what am I going to do? I'll take this s, I'll multiply by 1 minus s over m squared, this t, 1 minus t over m squared. Now I'm done. Now it doesn't grow anymore at high energies. If this mass m is much smaller than f, the amplitude stays small as we go to high energies. But now I've changed the amplitude. I've clearly introduced a new state where this pole is. But because of the overall minus sign in front of this contact interaction, the residue on this pole corresponds with correct positive sign to the production of a scalar particle of positive probability. And that's, of course, the Higgs. Okay, so this is the linear sigma model completion of the nonlinear sigma model at the level of the 2 to 2 amplitude, just sort of guessed from the bottom up. All right, so here it's trivial to UV complete. You can UV complete this way, you can add many scalars, you can do all sorts of things, but it's very easy to UV complete. So why can't we do something analogous for gravity? Okay, so now in fact it has nothing, at this level it has very little to do with gravity per se. And just in order to avoid the complications for the moment of the polarizations out in front, I'm going to ask the following question. Let's say you have some low energy theory and the amplitudes grow at high energy with some power of energy. And you'd like to IR improve the theory. So you just want to sort of fix it up in the UV in such a way that the amplitudes fall off even faster. So, to take a slightly simpler example, imagine you're doing this with a phi cube theory. You know, again, I'll assume that it's massless for now. I'm doing it for a phi cube theory. The amplitudes decrease like 1 over energy squared. In 4 dimensions, that's good enough for it to be healthy in the UV. In 7 dimensions, that's not good enough for it to be healthy in the UV. There's some high enough dimensions that's not healthy. So I'd like to make the amplitude smaller than this, say. Okay, so let's try the same trick as we did before. Let me just multiply each one of these poles with a 1 minus s, 1 minus t, 1 minus u. Does this still work? And the answer is now it does not work. Now, why doesn't it work? The reason it doesn't work is that I now just check what is the residue on this pole, on this massive pole, and you see it has a minus sign. Okay, so the residue on the pole at s equals 0 has a plus sign. That's because that's the IR consistent factorization. But that forces the residue on the massive pole to have a minus sign. Okay, so this is this is actually basically the entire argument. You can actually prove quite easily that if you have any expression which is rational in ST and U with a sort of finite number of poles, polynomials upstairs and downstairs, any expression that's rational, there is no way to UV improve the amplitude without having a ghost in the spectrum, without having some of the massive states have a negative sign. And the reason is that we know something about the sign of the massless residue. So the fact that we have the sort of massless exchange already gives me a plus somewhere. And if I'm going to UV improve the amplitude, the residue theorem tells me the sum of all those things has got to add up to 0. And so some of the massive residues must be negative. Why didn't we have this issue before? We didn't have this issue before because we didn't have a massless residue before. And in fact, exactly this argument for this case of the contact interaction tells you that the sign here has to be negative. Okay, so this is one of the examples of determining the signs of higher dimension operators from UV consistency. Had the sign been positive, I also couldn't have completed it, but that's fine. I didn't have an a priori expectation for the sign either way in the case where I began with contact interactions, not the case when I actually have massless particles as well, and I know something about the massless residues. Okay, so you can actually, the ultimate origin of the problem has nothing per se to do with gravity, but it has to do with the fact that we're talking about theories which fundamentally have 3 particle amplitudes, so that in the 4-point scattering, we have IR poles. And then this argument tells you that it's impossible to tree UV complete with a finite number of particles and a finite number of poles. You need to have an infinite tower of masses, and you can easily show you also even need an infinite tower of spins in order to be able to come up with a UV improvement of these amplitudes at tree level, so amplitudes with only poles. And in fact, you can then fantasize, and Andy mentioned this in his talk, you can sort of fantasize that, well, we only know one example of a UV complete gravity amplitude. So maybe the consistency conditions just by of massless scattering are strong enough to totally determine it. And in fact, if you just play to begin with, forget about proving anything. It's quite cool that that you can trip over the string tree amplitude as this kind of simplest way of doing what we just talked about. Okay, so this is not going to prove that it's unique. I just want to show you how natural it is to discover something like strings from this point of view. You start with an amplitude. You start with what the actual gravity amplitude looks like, that has this this interesting structure with the polarization stuff upstairs and a product of ST and U downstairs. We just learned that whatever completion we have has to have an infinite tower of masses. So you just make an ansatz for the whole thing as some sort of numerator and a product over some spectrum, S minus m squared, T minus m squared, U minus m squared. But now there's a crucial thing this numerator needs to do, because if I sit on a pole in S, the residue is going to be some complicated object in T, which isn't even a polynomial in T. I want it to be a polynomial in T because at a fixed mass, I want to have some finite tower of spins, and something goes like T to the J is going to give me a spin J particle. So I definitely don't want to have this thing with T's downstairs. And therefore, this numerator should have some zeros to kill this object, which is what you get when you set on a residue at f equals mi squared. And then I won't go through the argument in detail. You then make some minimal ansatz for the numerator. Say it's a product of something with roots at r. The numerator some roots at rj, and demanding that it kills these denominators tells you that this set R should contain the mi squared and mi squared plus mj squared. And this is an interesting constraint, that the set should be such that it contains both m squared, both the m squareds and the sum of the m squareds. The simplest solution of this is a linear spectrum. And if you plug that into this expression, you get the product, infinite product formula for the Virasoro-Shapiro amplitude. So again, this is, yes, sorry, there's a question?
Yes, sorry, I'm trying to interrupt for
why would we, you start with this product of S minus m squared, T minus m squared.
Right.
Why wouldn't you consider at this point a more general thing where you had a sum of 1 over T minus m
Any
squared?
such thing, you can always put them all under a giant common denominator. So that's all of those would go into a less minimal numerator that has even more zeros. So one way of saying this is that if this numerator has got to have tons of zeros. If the only zeros that you if you ask if the only zeros are there to kill these evil residues, that basically fixes this answer. But of course, if I allowed the numerator could have many more zeros, and any expression that's a sum, I can imagine putting under a giant common denominator and just get a more complicated numerator.
So there is some precise set of things you can say. I want a function of this form in which I cancel the zeros this way, and that gets you to the string amplitude.
That's right. But again, it does not remote. I mean, it's a very special minimal thing. It's not obvious why we need this. But I just wanted to sort of point out that you could sort of it's natural to run into these expressions with the gamma functions as the kind of first thing that you would run into if you're trying to pursue this bottom-up strategy. And in fact, so if we go back to this Virasoro-Shapiro answer, you can ask, is this expression unique? Again, is it the unique expression that we can write down with only poles that gives the UV completion of gravity? And the real miracle in all of these expressions, the real miracle in the stringy answer, is the fact that these expressions with the gamma functions actually are unitary. And unitarity means that when you sit on a pole in the F channel, you have to be able to expand do a partial wave expansion of the numerator as a polynomial in cosine theta. As a sum over the Legendre polynomials, the Gegenbauer polynomials in general dimensions of cosine theta with positive coefficients. So that's an absolutely miraculous fact that all boils down to the following very simple statement. This is the expression for what you get sitting on the nth massive level in the open superstring. This simple polynomial in cosine theta. The claim is that if you expand this guy in Legendre polynomials of cosine theta, the coefficients are positive so long as the number of dimensions of space is less than or equal to 9. And it actually it can go negative when the number of dimensions is bigger than 9. So that's how you see the critical dimension. You actually see the critical dimension already in the first non-trivial example. This is actually an exercise in Polchinski's textbook. That if you look at this this residue at the n equals 3 level, you just write it as a sum of a spin 2 in d spatial dimensions, and you see there's a spin 0 that would be negative unless the number of dimensions is less than or equal to 9. So this is a really miraculous fact. There is, to this date, there is no direct proof of this fact. I mean, directly is some manipulations on these simple polynomials. There's some, of course, indirect proof through the no-ghost theorem in string theory. But this is such a big miracle that it might make you think even more that the answer is unique, because even checking that the answer that we know satisfies the rules involves this sort of huge miracle. So that's what Yutin and Jimmy Wang and I thought 4 years ago. So we thought really there's a decent chance that this answer is unique, but it turns out that the answer is no. At least only checking consistency of massless scattering, the amplitude is not unique. And here's a concrete example. There are many more examples like this, but if you just take the usual amplitude and then do this little deformation where we just shift the gamma to be gamma of 1 minus s over gamma of 2 plus s and so on, then you can prove that the unitarity of the open string and the bosonic string, actually, the positivity of both of those guys tells you, you can use that to indirectly show that if this coefficient is between 0 and 1, you continue to have this miracle. And you have all the same properties as before, the same Reggie behavior, the same soft behavior at high energies, all that stuff is the same. So that means that it's just not true that if we put in what we know anyway of the consistency conditions of 4-point scattering, that by itself is enough. You need to put in some more information. Minimally, it's not crazy that we need to consider the scattering of massive states as well. And again, that's not crazy. That's what happened to us in the story of the weak interactions, where we started from electron neutrino scattering. We got the W. But then longitudinal W scattering further needed Higgs to really come up with the full UV completion of the whole theory. Yes, Andy.
Does that counterexample obey the soft theorem?
Yeah, it obeys everything, because yeah. As far as I know. Okay, so anyway, so that's what I talked about at Strings a number of years ago through to that counterexample. And there is a consolation prize in this story, which is the structure of this EF dehedron. As a consequence of this going down this path, we learned about infinitely many constraints on the space of couplings in low energy effective field theory. And I've given many talks on this subject before, going back 3 years. The main novelty is that the paper is finally out. But I just want to say a tiny bit about it because it'll be relevant for some of our later discussion. So I just want to say that this whole subject begins by just thinking about the dispersive representation of 2-to-2 amplitudes. So when we talk about 2-to-2 amplitudes, we already said that we don't know in complete generality. We don't know what the rules of what the analytic structure has to be in order to be compatible with causality. But there are simple limits where we do know something about it. And to keep the discussion simple, there are extensions of this, but to keep the discussion simple, imagine that you've just integrated out massive particles. So you could imagine working at just a tree level where there's nothing to do. Or at loop level where you've just integrated out you've integrated out the massive states, but you have not done any of the massless loops yet. In that approximation, the analytic structure of the amplitude is very simple. To begin with, it's just the analytic around the origin. Now causality then tells us something. If we keep T fixed and make S arbitrarily large, essentially if we keep T fixed and small, we're making the 2-to-2 amplitude look more and more like a 2-point function. And we know a lot about causality for 2-point functions. And then there are some different arguments depending on whether there is a gap or there isn't a gap. You're talking about something gravitational. There's somewhat different arguments. But they all end up giving you a bound on the growth of the amplitude with S that's bounded by S squared. So it's sort of amusing that even these quite different arguments, the Fossat argument and the arguments that have to do with thinking about propagation through shock waves or the Eikonal limit, give you essentially the same practical answer, that the amplitudes are bounded by S squared. And because of that, that means that you can give this, by Cauchy's theorem, you can give this dispersive representation of the 2-to-2 amplitude, because you can go as much as S squared. In principle, I don't know the leading term of the piece proportional to S, but everything else can be written now as a partial wave expansion, as what looks effectively like a sum over propagators with exchanging particles of general spin with positive probability. So this formula is the sort of best we can do today to encode causality in 2-to-2 amplitudes. Okay, so this is telling us about the fact that the amplitudes are at fixed T large S are bounded, in this Reggie limit they're bounded, and that encodes causality. But it also has two positivities in it, that the probabilities here are positive, and the mass squareds are a positive. So these are the sort of two normal places that we encounter positivity in physics. Energies are positive and probabilities are a positive. And those two positivities end up implying a lot about the structure of the expansion of this amplitude at low energy. The sort of polynomial expansion at low energy is the effective field theory expansion. So here's the usual effective field theory expansion. I can take this expression, it's analytic around the origin, I expand it, I get these infinite power of coefficients, and they satisfy infinitely many constraints, linear and nonlinear constraints that sharpen the intuition that, if you have a dimension 6 operator suppressed by the TeV scale, the dimension 8 operators can't be suppressed by 1,000,000 TeV. They should be suppressed by roughly the same scale. Or if you have 2 operators with the same dimension, you shouldn't be able to make one 10,000 times bigger than the other. You might naively think those things would be true by naturalness, but perhaps by fine-tuning, you could make large hierarchies of that sort. And the point is, this entire set of coefficients actually has to live inside an interesting geometric space, and they're forced to satisfy an infinite number of interesting positivity conditions, inequalities that are again both linear and non-linear, and sort of the whole object is an interesting geometric object that's as a geometric object has a lot of similarities to other things that we've seen in this business, positive Grassmannians, amplitudehedra, and so on. And this all happens because of the surprise. What drives it is that there's a hidden notion of so-called total positivity associated with the propagator and with the Lejeune polynomials. And just to give you a sort of quick example of one of them, imagine we take a simple version of this problem where I have just a function of S. Imagine we've taken the forward limit, T is 0. I just have a simple function of S that's written as a sum over M squared with some positive coefficients over M squared minus S. Well, let me expand this out so that I can expand this out as a sum an f to the n. So that tells me that all these coefficients A0, A1, A2, and so on is written as a positive sum of P of M squared over M squared, M squared squared, M squared squared squared, and so on. All right, so now that's a clean mathematical problem. What do I know about the convex hull of a curve that looks like 1x, x squared, x cubed, and so on? I'm taking in general, positive linear combination of all points that look like that. And if you ask this question already in a simple case where I only keep A0, A1, and A2, then in this expansion, it's the convex hull of everything that's on this parabola. Okay, so it's everything inside this pink region. And so in this case, it's sort of easy to see the answer by I or by the Cauchy-Schwarz formula, but there are generalizations of this that are just captured by the following simple statement, that if you take all of these coefficients, you start this vector of coefficients, you make from them a matrix, and this matrix it's called the Hankel matrix. Its ij entry is the I plus j element of this vector. Then the claim is that this series here is of this form. In other words, this series is compatible with causality if and only if all of the minors of this matrix are positive. Okay? Every k by k minor of this matrix is positive. If you know more, if you know what the gap is, for example, you know more than that. It's not just the minors of this matrix, but many cousin matrices are also positive. But anyway, this is the most sort of zeroth order kind of idea, that there are nonlinear constraints, relations between the couplings that are a consequence of positivity. There's a similar story for Gegenbauers, and anyway, so this is not a talk about the EFThedron, but there are, you really can't see any of these things in detail, but if we talk about photon, graviton scattering, and so on, it's quite striking that there are really tiny regions in the space of couplings that are allowed by these positivity constraints. Yes, there was another question. Okay, so there isn't one, then I'll keep on going. So, all right, so that's nice, but a big missing ingredient in all these arguments, and this was another sort of frustration even of this consolation prize. So it's very nice that we have all these infinitely many constraints on the coefficients of higher dimension operators, positivity constraints. But when you actually look at where sensible theories end up in the allowed space, they're still not scanning everything which is allowed. And we can easily trace this to the fact that essentially the only thing that we've put in to this discussion is causality. So just the behavior in the Regge limit at large S and fixed T. And we have not, we don't know practically how to input the crucial constraints of UV completion. The standard constraint of UV completion that says that we have an amplitude that's exponentially soft at high energy. So that's large S and T with S over T fixed. Okay, and this shows up in many places. For example, in all the sensible UV examples that we know, the contribution to the imaginary part across the cut coming from higher and higher spins goes down as the spin increases. That's very important for, that's very important for UV completion. But our discussion in the setup doesn't know anything about that. Okay, so it's not reflected in our analysis. So in thinking about this, what's needed, and this is the end of the road to coming to celestial amplitudes that I'll now transition to talking about. What's needed is a setting when we can transparently see both the constraints of causality, which are large S and fixed T, the Regge limit, and UV softness, large S T with S over T fixed. And that's what we're going to easily at least start seeing in thinking about celestial amplitudes. Now, we'll see, I mean, the reason we started sort of having this conversation, even thinking about it, is that it sort of manifests ahead of time that UV softness is kind of crucial for even thinking about these celestial amplitudes. It's slightly more interesting that at least some of the constraints from causality are also turned into natural things about the celestial amplitude. Accessing the Regge limit directly from the celestial amplitude is not such an obvious thing to do, but the consequences of it, as reflected in these constraints that we just talked about, do turn out to be very natural statements about celestial amplitudes. All right, so let me switch to talking about the talking about the actual celestial amplitude. So I don't need to review this for this audience. We all here know that, but just to say that even if you're a sort of garden variety amplitudes person, it's very natural to, we're already thinking about spinor helicity variables. We already know we can write spinor helicity variables in this way, where we pull out the square root of energy in front of 1z and 1z bar. We know that zz bar gives us a point on the celestial sphere, and that zz bar transform into the SL2C of Lorentz just by Mobius transformations. So that aspect of the celestial sphere is sort of in there, you know, in everyone's formulas. But what's new from this point of view is that we're not scattering momentum eigenstates, but that it's more natural to consider boost eigenstates. That's the sort of physically, to me, the really physically fascinating thing. It's not just, I mean, of course, all these things are transforms of each other, but thinking about scattering boost eigenstates forces you into certain physical questions that are or the access physical things that we don't access in the same way by thinking about momentum eigenstates. So to get a boost eigenstate, we just integrate over the energy eigenstates by some power of the energy, and then under Lorentz general Lorentz transformations, this is how the state transforms. And of course, under transformations that preserve the null direction of motion, I just get an overall rescaling. So that's a state in which that's a sense in which its eigenstates of boosts in the direction that the null momentum is pointing. Okay, so let's think about these scattering amplitude for boost eigenstates. Again, this is just reviewing things that you've all seen many times, also in this meeting. So we're just doing this Mellin transform of ordinary amplitudes, and at 4 points we have this the momentum conservation is not manifest in this discussion, and the fact that the 4 point scattering takes place on a plane tells us that the 4 points Z1 through 4 have to lie on a great circle where the plane intersects the celestial sphere. The requirement that 4 points lie on a great circle is just that the cross ratio that you make between them Z is real, and so that's why there's this delta of Z minus Z bar sitting in front of all the formulas. So when all is said and done, the amplitude in the final amplitude in Mellin space, I apologize, that should have been a delta, is something that depends on helicities, this delta of Z minus Z bar, and then a very simple object, which is just the Mellin transform of the 2-to-2 amplitude with respect to the center of mass energy. And then there's this beta, which is the total boost weight, the sum of all the deltas in the process. Okay. Now, this is bringing coal to Newcastle, but the study of celestial amplitude has already clarified, unified, revealed many aspects of the infrared and of soft amplitudes. And we even talked about some further aspects of this in the paper with Anna Maria and Monica and Andy. But I want to here focus on the UV aspects, because boost eigenstate scattering is, just to make this point, the boost eigenstate scattering is seems to be a perfect probe of the sort of UV-IR connection. Obviously, it maximally violates Wilsonian intuition. Okay, so there's no sense in which you can ignore high energy states, because we're scattering states with arbitrarily high energy in these boost eigenstates. Another lovely fact to me is that EFT amplitudes, if you just take a low energy theory and just try to directly Mellin transform it. Of course, this has been discussed in this meeting, but there's a sense in which these amplitudes don't make sense. If we just think about the sort of simplest possibility where we have an amplitude that grows like a power of energy, omega to the p, the most naive thing to do when you do the Mellin transform of this guy would just give you some expression that looks like this, whose beta dependence is sort of totally ill-defined. Now, obviously, if you make beta equals negative p plus I times something, then you can interpret this as a delta function. But it's not something that's analytic in beta. And the sort of the most obvious problem is that when the amplitudes are growing, we don't know how to make sense of these. We don't know how to make sense of these integrals in a way that's analytic in beta. Now, I think this is good because it doesn't let us slide into the comfort of dealing with UV incomplete theories. And somehow, if we're thinking about amplitudes on the celestial sphere, it's forced on us from the get-go to be dealing with something that is UV complete. Now, so because I'm focusing on this aspect of the difference between boost eigenstates and ordinary momentum eigenstate scattering, we're going to be spending the rest of this talk mostly thinking about the analytic structure in the beta plane. Okay, so let's start because beta is the total boost wave. Okay, so let's start with a very simple example. Let's say I have a massive particle, capital M, exchanged between two massless scalars. So this is what the amplitude would look like just at tree level, where lambda is g squared over m squared. And if I take this expression and Mellin transform it, and do it trivially with contours, and you get this nice expression that goes like m to the beta over 1 minus e to the I pi beta. So this expression has an infinitely many poles. Okay, so here we got this expression just explicitly, but we can also sort of easily see why it has these infinitely many poles. So first of all, where can this expression get poles? It can get poles from the behavior near omega equals 0 and omega goes to infinity. And we'll talk about this in more detail. I mean, it's a simple point, but I'll say it again in a moment. But just to say it quickly here, we can also see in this example. If I look at the behavior of this near omega goes to 0, then the amplitude has an expansion in powers of omega squared, s, or powers of omega squared. So if I put a power of omega squared in this Mellin transform, I get 1 over beta plus 2n. Okay, so clearly I can't have beta be too negative because then the amplitude would have a divergence. And so that's where these poles come from. So you see that the poles on the negative beta axis at negative 2n are reflecting, the residues on those poles are reflecting the effective field theory expansion, low energy effective field theory expansion of the amplitude. Conversely, at large, in the positive beta axis, I get the behavior going at infinite omega. This is a typical field theoretic amplitude that dies as a power of energy at large energy. So it has an expansion as powers of 1 over frequency at large energy, and that gives me poles at positive two integer values of beta. Okay, so the poles on the negative beta axis reflect the infrared effective field theory expansion. The poles on the positive axis refer to the power law fall off that's characteristic of field theory. And already this simple example illustrates sort of more precisely this anti-Wilsonian character of celestial amplitudes. Let's just contrast what the formulas look like for momentum space versus Mellin space. If I take momentum space, here's the full expression. As I take the mass to infinity, the full expression just goes to lambda, which reflects exactly the sort of contact expression that you would expect in the low energy effective theory. But what about here? If I start with the 5-4 interaction at low energies, the beta dependence that I would get would just be this delta function that we talked about before, just delta of beta. And there isn't the sort of, there's some, on the other hand, if I take the full answer, all of the mass dependence in this is in this m to the beta factor out in front. And there is no sort of obvious sense in which the m goes to infinity limit of this expression turns into that one. Of course, there's some formal sense in which it's true because it's true before the Mellin transform. But if you just look at the answer, the actual answer at any finite mass at any m is analytic and it has infinitely many poles, whereas the effective field theory answer, what you get by Mellin transforming the amplitude of low energy effective field theory, is simply not analytic. Okay? So they're not smoothly connected to each other. Anyway, so this illustrates the sense in which decoupling does not work in the same way at all for the ordinary amplitudes, for celestial amplitudes as compared to ordinary amplitudes. So let's just review again this discussion about where the poles come from. I said it already, but any behavior that we have near 0 frequency, we imagine that we have some power expansion in powers of omega that would give me 1 over beta plus 2n. I'll come back in a moment to correct this to include all the effects that we have. But at the simplest level, if we just imagine we had an amplitude with that was analytic around the origin, then we get these poles at negative beta, and similarly, the power law fall off at high energy gives me the UV poles. Okay, now that discussion already tells us that there is a radical difference between quantum gravity and field theory in their behavior, just the structure of the amplitude in Mellon space. Typically in field theory, we just saw we have these infinitely many poles on both sides of the axis, but in quantum gravity, we expect that the 2-to-2 amplitude is exponentially soft at high energies. And that means that there's just no poles at all at positive beta. Okay, so that's it's a clean distinction between field theory and quantum gravity. This difference is the analog for celestial amplitudes of the absence of the bulk point singularity in ADS. And there too, you could imagine a sort of a bulk ADS theory without gravity, where you would have the bulk point singularity that corresponds to scattering at points in the interior of ADS, but gravity removes those poles for a very similar reason that has to do with the exponential softness of the high energy amplitudes. Okay, so that's already an interesting qualitative difference, and again, it reflects the non-decoupling nature. So if I have any G Newton at all, poof, there's this big difference. All the poles are gone. Okay, so now in a little bit more detail, in complete generality, and now we'll talk about gravity, which will actually makes our life a little bit easier. The low energy amplitudes not only have powers of frequency, but we also have loops from massless gravitons and photons and other particles. And those loops generate logarithms. Okay? So we have the sort of log running or the log inducement of higher dimension operators in the low energy theory. And so that means that the low energy amplitude is not just an expansion in powers of omega, but it's expansion in powers of omega modulated by G Newton omega squared, which is the dimensionless strength of the coupling in gravity to powers, and logarithms of energy divided by the UV cutoff. Okay, so these logarithms, for example, at one loop, these are famously calculable quantum gravity effects. You can calculate the coefficients of these logs. They're associated with the running in the IR theory. Their discontinuities are associated with particle production in the low energy theory. These are sort of famous facts about effective field theory. The logs are calculated. Okay, and those logs have a very, very pretty imprint on the Mellon transform celestial amplitudes. All we have to do is look at what we get from the low energy contribution to the amplitude, not just from omega, powers of omega, but also powers of the logarithm. But it's very easy to see that we can get powers of the logarithm simply by differentiating with respect to this exponent. Okay, so that tells us that as beta goes to -2n, we not only have simple poles in beta, that's what we talked about with just powers of omega, but because they're modulated by logs, we get double poles, triple poles, and higher. At any given pole, there are a finite number of double, triple, there's a finite order at which you go to. The fact that that's a finite order is reflecting the fact that as you go to more and more loops, you add more and more powers of omega. Okay, so that's another difference between gravity and a theory like QED or something that would have a dimensionless coupling. That wouldn't be the case there. But in gravity, because the coupling itself is dimensionful, then at any fixed negative beta, there's a finite number of simple, double, triple, etc. poles up to a given order, up to n-1 order there. And the residue of those poles is giving us the running coupling constant of the corresponding logarithmically induced higher dimension operators. Okay, so the summary then, and now this is the complete summary of the analytic structure, is that there are poles in beta. In the simplest case, the residues of the simple poles are the coefficients of the higher dimension operators, but we can have multiple poles, and their residues reflect the IR running, the logarithmic running of the higher dimension operators from massless loops in the low energy theory. Now, if you're a sort of card-carrying effective field theorist, you will find this exciting because these are things, of course, we care about a lot in effective field theory, but ordinarily we use a slightly loose language in talking about the distinction between the contact piece that's sitting there already from the ultraviolet versus what you get by log running in the low energy theory, we say words like, well, the log running pieces are logarithmically enhanced. So if you give them long enough, they get big. There are these slightly loose words about it. On the celestial sphere, it's very precise. All of those things are reflected in sort of canonical facts about the Mellon amplitude, the residues on the poles, higher poles, and so on. Okay, so much for the analytic structure, and that's it. We only have poles in the beta plane. Okay, so we only have these simple poles in simple and higher poles in the beta plane. So the final set of questions that you would ask is, what do we know about the large beta behavior? The large beta is sort of clearly probing something about the ultraviolet in the ordinary in ordinary momentum space. Let's think about large beta, where the real part of beta is positive. Then, in looking at this Mellon integral, clearly we're dominated by large omega, and we know something about what the amplitude looks like at large omega. Roughly, it dies exponentially. And so that lets you make a simple estimate for what A mod squared looks like. Because it dies exponentially as we go to larger and larger beta, it grows more and more before it ultimately gets cut off. And so A mod squared, as you go to large beta, grows exponentially, factorially, grows like gamma of beta. So that's kind of cool. The actual 2-to-2 amplitude dies as we go to high energy, but the 2-to-2 amplitude in the Mellon space grows exponentially as we go to large positive beta. There's another difference, which I think is interesting, which is that the amplitude in momentum space, its function of energy, not only dies exponentially as we go to high energies, but is also sort of chaotic. So we expect it to fluctuate a lot, even though it's very small, but we expect it to fluctuate a lot. There's a very simple toy model for sort of thinking about the amplitude for 2-to-2 scattering, as well as just for black hole production, where you imagine that there is an amplitude for an in state to make a black hole, or the black hole to go out to the out state. You imagine there's a bunch of microstates for the black hole sub j of order e to the s black hole of these guys. And I'm just going to make a sort of simple model where this basic amplitude goes like e to the minus s black hole over 2 times some sort of random phase, some phase that depends on in and out. Now, why do I put the e to the minus s black hole over 2? Well, if I look at the total cross-section for producing a black hole, that would just be summing over all j of the sum over n of this thing mod squared. And so the phases go away, and I get the e to the plus states multiplied by this e to the minus s over 2 squared. So that gives me a production cross-section of order 1, which is correct. But if I look at the exclusive amplitude for in to out, now I sum over the same e to the s phases, but I'm averaging over these random phases now of order e to the plus random phases. And so that tells me that if I look at the mod squared of the 2-to-2 amplitude, it's of order e to the minus s, but it's coming from averaging e to the s random phases. And so if you really imagine sort of plotting it as a function of the energy, it would have some kind of wild, chaotic fluctuations. Now, this is always a sort of qualitative thing that bugged me or worried me about a possible theory of the S matrix, in momentum space, say, is that somehow whatever the theory is, when it gets really exciting, when you're going to talking about trans-Planckian scattering, somehow it has to have something very difficult to predict in it. But notice that when we go to Mellon space, we're averaging over energies. And the average over energies gives us something smooth. So if I go back to this expression, we expect that the large beta growth is something like this and smooth. It does not have these wild oscillations in it. And you can see it very simply in sort of, on the computer with toy examples of summing over random phases that doing the Mellon transform to see, but it's obvious that you're averaging over energy, so the sort of chaotic thing becomes smooth. All right, so at large positive beta then, summarizing, the amplitude grows exponentially, really factorially with beta, and is smooth, whereas the momentum amplitude dies exponentially and is chaotic. What about in the opposite limit? And the limit as beta goes to minus infinity. Well, we can go back to our simple expression to get some intuition to begin with. So when we do the Mellin transform of this simple example, integrating out a particle of mass m, we get this m to the beta. And so as you go to large negative beta, it goes like, well, it goes like m to the beta. Now, let's say I had two masses, m1 and m2. Then at large negative beta, I would be dominated by whichever one of the two of them was lighter. Okay, and that there's a sort of simple general argument for that, which I won't go through, but it's basically that intuition is that the leading behavior at large negative beta is m star to the beta, where m star is the, if it was something at tree level, it would be the gap to the massive state, but more generally, if the momentum amplitude had a branch cut as a function of energy, it would be the location of the closest sort of branch point to the origin. And in slightly more detail, if in this case, where we have a branch point, if the sort of cross section for producing the new particles at threshold goes like s minus m to a power q near threshold, that power is reflected in a subleading behavior as beta goes to minus infinity. You get beta to the minus 1 plus q. Anyway, there's a essentially trivial contour argument that gives you this result. Okay, so good. So after all this, so we've done nothing in this discussion other than translate things back and forth. Okay, so we know things about the amplitude as a function of energies, and now we're sort of translating what they look like in the Mellin space, and there's a nice dictionary developing between them. But of course, the sort of big question is, the big question, even to begin with, was what are the rules that determine the amplitude? Okay, so what, so we can repose the question here. What determines that the amplitude is a function of beta and z? As we already said, we know that the analytic structure of the function of beta is very simple. There's only poles. The poles reflect effective field theory couplings, and they're running. And notice that those are exactly the objects that are constrained by positivity from the story of the EF dihedron. So I didn't need explicitly at the moment to talk about how we see the Reggie limit in Mellin space. The transform to Mellin space was natural about fixed angle scattering. So as I said, we're sort of hardwiring in good UV behavior, but everything about the low energy expansion, which remember that low energy expansion is sort of is coming from the assumption of having something which is it's coming from the dispersive representation that's putting in causality. Okay, so we're also seeing so good UV behavior at fixed angle scattering is hardwired, but the constraints from being at least some first set of constraints to being compatible with causality are also there, and they're there as sort of an infinite number of positivity constraints on very natural canonical objects. You know, the residues of the poles of in the beta plane. Okay. Okay. So the pole structure is interesting, and it reflects, and the positivity constraints on the residues of the poles is an important reflection of causality. The large beta behavior is prescribed by black hole physics. The leading behavior as beta goes to minus infinity is controlled by the gap. So we know something about the poles and the leading behavior at infinity. What else is needed? Is this, what else do we need to do to figure out, to determine the answer? And it seems like more is needed. So we have not quite gotten a complete free lunch. In order to see why more is needed, let's just do a little example. So imagine you take some sensible Mellin amplitude, A of beta, and I'm just going to shift it by adding some mu to the beta. Okay, where mu is bigger than this than the gap m star. Okay, if I take this expression, this mu to the beta is subleading. It doesn't change the poles, It's subleading as beta both goes to plus infinity, where it's subleading to the gamma of beta from black hole physics, and it's also subleading as beta goes to minus infinity. So it looks like I can add this thing without changing anything about the residues and poles of the object in Mellon space. But if I transform back to momentum space, this is a horror. This would give me a delta function at S equals mu squared. So it's horribly non-analytic in S. And so this is highlighting that while we've put in a lot of information about causality as reflected in these positivity constraints on the poles in Mellon space, we still haven't understood a very basic thing, which is how is the fact that the amplitudes are just, simply analytic in or approximately analytic in momentum space reflected in Mellon space. So here's an example of something that seems perfectly fine in Mellon space, but comes from something horribly non-analytic in momentum space. And so we still need to understand the celestial avatar of causality more fully. Okay, so that's, I think, a nice open problem. So I'd say that there were sort of, we've taken 1.5 steps. So from the usual way of doing things, we have analytic amplitudes to begin with. We put in the Reggie behavior. We don't know how to put in UV softness. In the celestial way, UV softness is guaranteed. A lot of the constraints of causality are present in terms of positivity, but we still need more to take a full 1 step further rather than a sort of a half step further, which is, I think, what we've gotten to so far. Let me just make one last comment, I think, an interesting physical open question about celestial amplitudes, going all the way back to this motivation of whether we can uniquely determine that the string amplitude, that maybe is our strings the unique UV completion or unique family of UV completions of gravity and so on. I already said that they don't seem to satisfy. We seem to have deformations, and so it's important to also consider the consistency of the massive scattering amplitudes as well. And this opens up a sort of a very general question, which is another kind of 0th order annoyance about thinking about amplitudes in momentum space, which is exactly this. How are we supposed to think about the whole sort of tower of UV states that we think are there in order to make decent UV complete theories of gravity, at least in 4 dimensions and higher. For example, if we're thinking about strings, those string modes are very, very important for the UV completion, no doubt about it. And yet officially in the S matrix, they're not, we don't see them. And that's because they're unstable. Almost all of them are unstable. And so we have this sort of very 0th order problem that we're interested in the scattering of photons and gravitons. We know we have to introduce all these modes at weak string coupling. They're even there as sort of legit particles. But officially in the S matrix, the only things that we get to see at infinity are the stable massless particles. And sure, you can go and hunt around for the massive particles by looking at appropriate analytic continuations of the amplitudes. Even in the most simple case where we have E plus E minus goes to a Z, goes back to muons or something, then we know in that amplitude at 1 loop, the presence of the Z resonance is just gone. We just see a branch cut. And if we look at the discontinuity across a branch cut, of course, it's small, 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 then big right in the neighborhood of the Z mass, and then small, small, small again. So it's there. We see the resonance there. And we can also see the pole, the bright Wigner pole, but we see it by analytically continuing under that branch cut. It's annoying that to see all these states that we care about in the UV completion, they're not there officially in the initial and final states, and they're harder and harder to access in the actual structure of the amplitude. So it's a question. I don't know the answer to this question, but could it be that celestial amplitudes for massive unstable particles? And by the way, this issue is there. As we go to super high energies, we're talking about black hole production, it's not true that we see the individual black hole microstates as little poles or something like that, right? The actual amplitude just has this boring cut. But wouldn't it be great if there's some way of sort of seeing the individual microstates as some feature of the amplitude? But it's definitely not obvious how we'd see it in ordinary for ordinary amplitudes. But could it be that celestial amplitudes for massive unstable particles sort of make more sense than in momentum space? And I think this is not unrelated to the fact that that the kind of soft-hard separation is more natural in scattering boost eigenstates. The sort of physical picture is, why doesn't it make sense to talk about scattering massive unstable particles? Well, I mean, if I have the particle here, you might think that I should scatter it or its decay products. You know, one goes into the other. But if it's just sort of sitting here, its decay products go in every possible direction, and they're not really scattering against each other. Okay? And that's true for ordinary, that's true for scattering ordinary momentum eigenstates. We can always go to a frame where one of them is just sitting there and the particles are decaying in every possible direction. But it's not true for boost eigenstates, because you're taking this picture and then boosting it, and actually weighting over arbitrarily high boosts. So most of these configurations have the particle and all of their decay products all going together in the ZZ bar direction. So could it be that that there is some more sensible way of talking about the S matrix even for massive unstable particles? I think this is an interesting question to explore. It's a qualitative question, and if there is something nicer about massive unstable particles, I think that would be another big boost, pun intended, to a thinking about celestial amplitudes as a sort of natural home for thinking about UV completion. Okay, I think I've gone on already a lot. Actually, I thought I would cover all of this in roughly half the time. And I wanted to speak about a second topic, which I was using this workshop, a coming workshop, as an excuse to start thinking about, which has to do with questions about a very natural connection between the thinking about the celestial sphere and the Grassmannian representation of amplitudes that goes to the heart of the issue about translational invariance. In the informal spirit of this workshop, I did some small computations last night, so I thought I would talk about them. But anyway, I should stop here. But if anyone wants to talk about that over discussion or at any other point, I'll be very happy to do so. All right, thanks a lot.
Okay, yeah, I mean, you're free to definitely just keep going if you want. I mean, it's really cool stuff. But maybe in the interest of, I guess, let's take some now for whoever's here, and then I'll stop recording, and then we can keep going with it. So any questions? I think that the questions that you asked are very, very interesting, and we're all gonna think more about them. So let's give a round of applause to Nima. Thank you so much. I'm gonna stop recording. And take it away, Alok.
Okay, thanks. Thanks a lot, Sabrina, first of all, for inviting me to the workshop and also giving me a chance to speak here. I should also apologize to you a little bit because even though we discussed that I should talk about the flat space holography, but after the discussion we had on the logs of theorem, I sort of thought of focusing on the issue of the asymptotic symmetries in the context of loop amplitudes. So that I hope that's okay. So this is basically the title of my talk: infrared triangles, asymptotic symmetries, and soft radiation. Most of what I'm going to talk about is the work which was done with Miguel, and also currently being some of it is now being completed with Miguel, and it will appear soon on arXiv. So let me start with some motivation. Quantum gravity S matrix in asymptotically flat spacetime is constrained by what we now understand as the infrared triangle, which was discovered by Sabrina and Strominger a few years ago. And this is the sort of the rough sketch of the infrared triangle. So as you will see, I call this the infrared triangle 1 because we will discover a few others in the talk. So on the tip of the triangle is the super translation charge, which I just denote here as ST. And there is a quantum version of it that I denote as ST hat, which, as we know, is from the work of Strominger, Prahar, and others, that it's equal to the Weinberg's of graviton theorem. And the classical super translation charge is basically gives us the classical memory effect. And there's a rather kind of a trivial way to go from the Weinberg's of theorem, take the classical limit and obtain the memory. So there is a nice closed triangle that we have. Now, the reason this triangle is extremely non-trivial is because of the universality. So we know that in the classical general relativity that the memory is non-perturbative. So it's a exact result pertaining to gravitational radiation, and you could have any, the scattering could involve colliding bodies or whatever, but if you look at the leading order soft radiation, then it has this universal feature. And the same is true for Weinberg's of theorem, which is an exact state-bending scattering amplitudes. In fact, it's even true for superstring amplitudes, as was shown by Ashok Sen in 2017. And the things are not so clear for super translation till 2013, where Andrew Strominger proposed and then showed that it really is a symmetry of a large class of asymptotically flat spacetimes, which are called Klister-Delau-Kleinemann spacetimes. So this is the sort of three universal aspects of the three corners of the triangle. Sorry. So so in this talk, what we're going to do is to try to classify other infrared triangles that constrain the S matrix, particularly in D equal to 4 dimensions. And as an offshoot of this, we will also see maybe how to parameterize the space of vacua in 4 dimensions of quantum gravity beyond super translations. So let me give a setup. I mean, this setup, I guess most of you are already bored with because we saw them in many talks this week. So I'm just going to be very brief here. So our setup is we have asymptotically flat spacetime with 2 boundaries, which are very important for us, which we call scry plus and scry minus, which are also called future and past null infinity. And one interesting structure at these infinities is that the covariant phase space of classical general relativity can be parameterized in terms of data at scry plus or scry minus. So this gamma naught is just the covariant phase space of classical gravity, and it's coordinatized in terms of what are called the shear fields, which are just tensors on the 2 sphere on scry. And the classical GR boundary conditions tell us that this shear have the following fall-off conditions at large U. So they have some constant modes and then they have some fall-off behavior. And just like the content about the radiation is contained in the what is usually called the News tensor, which I denote here as NAB, which is just the time change of the shear field. And these are the asymptotic symmetries that we have understood quite a lot in last few years. So there is the super translation vector field, which I denote as F x hat. X hat by x hat, whenever I use x hat or xa, I just mean coordinates on the sphere. And then there are the super rotation vector fields. And on the phase space gamma naught, the super translation vector fields give rise to charges, which we just denote as Q of F. And the super rotation vector fields give rise to some charges, which I will just denote them as J of Y, sorry, where Y is the vector field on the sphere. And at this level, this Y could be either Virasoro or smooth diffeomorphism. So I would not distinguish between them right now. Okay, and the conservation of super translation charge, as probably most of you are familiar with, is this nice little equality between the what is called the mass aspect at U equal to minus infinity and the mass aspect at V equal to plus infinity. And this conservation law was proposed in 2014 by Strominger, and it was proved with quite a precision by Prabhu in 2019, quite fairly recently. Similarly, conservation of super rotation charges, I mean, it's a little bit more subtle. So the super rotation charges can be thought of as angular momentum aspect at U equal to minus infinity being equal to the angular momentum aspect at U equal to plus infinity. And one can prove these conservation laws in classical theory, but we have to assume slightly stronger fall off on the gravitational field. In other words, the shear should go not as as 1 over U to the delta, which was in gap, which was the fall off we had to assume for the covariant phase space, but slightly faster as 1 over U square. And this point will become important later. So this is the status of classical conservation laws. But there is a problem with this covariant phase space, which was already noticed by Hay, Lysov, Prahar, and Strominger in 2014. That the action of the supertranslation charges, even though they are well defined on this covariant phase space gamma naught, it's not faithful. In other words, from the space-time perspective, we know that the action of supertranslation is given by this red equation here, where there is this extra term, which is like adding a zero mode to the shear. But on this covariant phase space, all we get is the action of the supertranslation on the News tensor, and there's no way to compute from the Poisson bracket the space-time action on the shear. And this problem was fixed by these authors, where they proposed an extension of the covariant phase space of general relativity. And this was the extension that they proposed. So they added to the covariant phase space 2 extra fields on the sphere. The first field, which I just denoted as C0, was a potential for the zero mode of the shear field. So you could understand the C0 as defined in the first equation. So you take your shear and look at it at early time, and that gives you the that gives this extra constant mode. And the conjugate to this constant shear was the zero mode of the News tensor. So you take the News and just average it over the entire Scri plus and in the zero mode. And this one, oops. Sabrina, sorry, the participant list appeared in the middle of the screen. Hello?
You're muted, Sabrina. Oh, it's just mute it, like exit out, or it should be fine.
No, actually, the participant list, Sabrina, is appearing in the middle of my screen, so I can't see my own slides.
Can you move it? Can you move it?
Yeah, I might cut it.
Okay, thank you. Thanks. Sorry.
Is it still full screen? Yeah.
We can see your slides fine. Sorry.
Okay. So this was the extension proposed by these authors, and then these were the brackets that they got in this extended phase space. So there was a bracket between the two shears, which effectively went like a step function. I am suppressing the sphere coordinates here just for simplicity, and effectively the zero mode of the shear and the zero mode of the News were conjugate to each other on the sphere. And this extension did two things for them, which was quite interesting. Is that the Hamiltonian action of the supertranslation charge faithfully produced the space-time action, and the Ward identity of the quantized supertranslation charge on the phase space was shown to be equivalent to the Weinbergs of Graviton theorem. In fact, there was an offshoot of this, which was realized a few years later by Strominger and others, is that you could actually use these extra modes to also parameterize all the soft, what we call soft vacua now. So basically, we start with, say, for example, the Fock vacuum, and then we just apply the zero mode of the shear, and it can be easily checked that the supertranslation, these new states are eigenstates of the supertranslation charge. So this is the story so far for the infrared triangle 1, and we want to see how the story is changed by the super rotations. Now, super rotations, already at the level of space-time action, there is the issue that one can immediately see. If the action of the super rotation on the shear has an extra term which I have written which is underlined in the red, which clearly violates the fall off of the covariant phase space, because we know we don't want the shear to grow at large U linearly with U in the gamma naught. So there's already an issue here, and which needs addressing. Just for now, I will just focus on the Virasoro symmetries, although a lot of what I will say will be valid for this phase too. Now, there was another issue which was at the quantum level shown by in a very interesting paper by Distler, Flauger, and Hahn, that if you look at if you quantize the super translation and super rotation charge on either the covariant phase space or even on the extended phase space, it doesn't close into a super translation as you would expect from the space-time symmetry, but you get an extra term which is non-central. So it's this k hat is what is called a 2 co-cycle extension. It's a linear operator on the Hilbert space. So this is potentially a problem because of the following reason. that it's really in conflict with the word identities which are known to be associated to consecutive doubles of graviton theorems for tree-level amplitude. So let me just explain why. So if you for example take, I mean these theorems are well known. You take like one graviton soft, then the other graviton soft, and if you take the subleading projection in the first soft graviton and the leading projection in the second soft graviton, then it was shown that this double soft theorem is equivalent to sort of a nested word identity between super translation and super rotation, which is written in the red bracket. And similarly, if you take the other limit, which is you take first the leading soft limit and then the subleading soft limit, then that is equivalent to the nested word identity, which is kind of reverse between super rotation and super translation. Now, if you take these two equations and you apply Jacobi, then it will tell you that the commutator of the super rotation and super translation charge should commute with the S matrix. But that doesn't happen because of the fact that the 2 co-cycle one obtains is actually not a C number but an operator, and it doesn't commute with the S matrix. In fact, it's linear in the soft mode. So this was another tension. So there were kind of two tensions, one at a classical level and quantum level, that we want to resolve. So let me just recall these two issues, that the action of super rotation classically does not preserve the fall-off condition of the sphere, and the quantized algebra does not close. And this actually appears to be in conflict also with the extended BMS algebra on the celestial sphere, which has been derived by Steibergen and Taylor recently. And it turns out that the classical issue was already resolved in two very nice papers by Geoffrey Compere and his collaborators and Miguel Campiglia et al. In these two papers. So I will just first tell you what they did slightly and then go to the resolution in the quantum theory. So first thing to notice is that the spacetime action of super rotation requires a slightly closer examination of the asymptotically flat spacetime, in the sense that you don't parameterize the shear just using a function which we defined above, which was going as a constant mode, but add an extra term which is like a tensor on the sphere, which is linear in U. I mean, naively you may think that this is not asymptotically flat, but just computation of wild tensor easily shows that these are also asymptotically flat spacetimes. And this TAB can really be understood in the following way. So you start with this shear, which now I denote as C tilde AB because this is more general than the one that we have from the classical GR, older classical GR perspective. And then this is the limit in which we can understand TAB. And it turns out that if you look at the soft term in the super rotation charge, then that is just equal to the effectively integral of the shear, over Scri, and that I just denote as N1 AB. Now, so it turns out that using these two extra modes, one can actually propose an extension of the phase space of Strominger et al. And this is something that is a work in progress with Miguel. So this is the extension that is possible. So this extension is where you basically add these two modes, the mode which is this linear in U mode in the shear, and the integral of the shear on Scri. And again, using these two sort of continuity conditions, the definition of TAB and N1, one can show that these are effectively conjugate to each other. And the subleading soft news actually commutes with the shear, which is the old shear in which is CAB, which is apart from the linear. Now, just one caveat I would like to mention is that this is not a unique, of course, extension of this either the covariant phase space or the phase space of Strominger, Lysov, Hay, and Prahar. But it is a phase space which does two interesting things. One is that the action of the super rotation charge on the news correctly captures the spacetime action, and the action of the super rotation charge on this tensor T correctly catches the action that we expect from spacetime. So now the question we want to ask is, does it lead to the consistent word identity? But before I tell you that, let me just tell you that this charge is, so this is the work that was done by Compere and his collaborators in 2018 and Miguel and his collaborators in 2020, where they showed that actually the super rotation charge is not the one that, if you carefully compute it, it's not the one that was computed before, but there was an extra term. So the JV hard is the term that people already knew before. It's like this hard term which kind of rotates the shear. Then the soft term is a term which is linear in this N1 AB. So that's the one that in the quantum theory gives rise to the subleading subgraviton insertion. But there was an extra term that they derived from phase space perspective, which was really linear in which was really a functional of the leading news and the constant shear mode, which was part of the phase space of Strominger et al. So now, classically, they showed that using this, there's a new definition of superrotation charge, the algebra closed. And what we wanted to understand was that if we quantize them on this new extended phase space, what do we get? So initially, it looks like there is a problem, because if there's an extra term in the superrotation charge, then why would its word identity give us the subreadings of Graviton theorem? But luckily, it turns out that's not the case, and this can be easily seen here. So if you just take this extra term and you just apply it on single particle state, then it turns out that the action is actually trivial. So it's an action which requires taking some soft limit, but a soft limit which involves no pole, and so it vanishes. So because of this reason, the single word identity is still equivalent to the subreadings of Graviton theorem for T-double amplitude. But it turns out that its operator itself is not actually trivial, and it has a non-trivial action on the super translated vacua as opposed to the canonical fork vacuum. And so here is the final commutators that we obtain. I'm sorry about this. This is the most dense slide I have in my talk. So the commutator between the hard charges, the super rotation and super translation, it closes in the super translation hard charge. And this is expected. This was already known even before this new extended phase space. And interestingly enough, and this was a really nice computation done by Distler et al., for the Virasoro symmetries, the soft charges, the super rotation and super translation soft charges also commute. And now, because of this new phase space that Miguel and I have proposed, one can show that all the remaining commutators combine to give you a super translation soft charge, so that in the end, you have a closed algebra with no two-core cycle. And this, so this is the quantized extended BMS algebra, which is now we can see that it's consistent with the consecutive double soft theorem, because it satisfies the Jacobi that we obtain. So okay, so before I proceed, is there any question at this stage?
I think that there's an interesting, or there's a way to interpret these in terms of the Goldstone and memory modes that I might raise at the end, so that you can just keep going with the talk. But it sounds like the stuff that you're doing with it is very interesting. So.
Okay, thanks. Yes. Just, so now, yeah, okay, maybe this is slightly related to what Sabrina is saying. So now we can, now that we have this closed algebra, we can ask if is there any way to enhance the space of soft vacua in our theory. And this I'm going to do only at the level of kinematics, because dynamically we know that the maximal commuting set of conserved charges is just the super translation charges. So I'm just going to just look at it at the level of either scri plus or scri minus, and not think in terms of conserved charges. So there we know, due to this nice computation of Distler et al., that the super rotation and super translation soft charges commute. And so we can diagonalize them simultaneously. And now I just want you to recall that in this new extended phase space, the subreadings of news N1AB, which is really the JV soft is linear in N1AB, is conjugate to this tensor TMN on the sphere. So we can again define a class of sort of super rotated vacua, which are super rotated as well as super translated, which I denote as F and G, which is obtained by applying on a super translated vacuum this exponential of the T operator. And then due to canonical, this commutation between the subleadings of news and the T, one can show that these are really eigenstates of the soft super rotations of charge. So here's a small, a quick summary of what we have so far. That the Hamiltonian action on the new extended phase space is the same as the space-time action of super rotations. And both the single and consecutive double soft theorems can be obtained from word identities. And these requirements really lead us to this new phase space, which has the the constant shear mode, the soft news, which already was there in the extended phase space, and the subleadings of news and the tensor T. And then a class of soft vacua, which at least kinematically can be parameterized both in terms of the constant shear and this new tensor T. And now in the case of non-abelian gauge theory, actually there's a far more rigorous construction of this extended phase space, and also the relationship with consecutive double soft theorem, which was proved by Prahar and Temple very recently. Now I come to exactly what Sabrina was saying, that now that we have a handle on the sort of the correct classical and quantum charge, in the sense that satisfies the right algebra, like we can ask what is the infrared triangle that we get. So the tip of this triangle is the super rotated charges, And then the on the quantum side, the superrotation charge is obtained. I mean, it's related to the subleadings of Graviton theorem for the T-level amplitudes. And then it was shown in a paper with Ashok a year back that if you do not consider the Coulombic effects in 4 dimensions, so you just ignore the 1/r effects and think that all the particles are free at large distances, then the classical limit of this subleadings of theorem really produces what is called the spin memory, which I will just explain in a minute. So this kind of closes the, if you do not worry about these 1/r effects in the classical theory, or as we will see the loop effects in quantum amplitude, then this really closes this infrared triangle for superrotation. And one nice corollary, or I mean some connection with the recent literature, is that these super rotated vacua that I discussed, which are obtained by applying this exponential of the T operator, we can understand them as follows. So basically, if you take, for example, a holomorphic vector field and you compute this tensor T, then it turns out to be the Schwarzian. And then this is, I mean, nicely consistent with the recent analysis of super rotation vacua by Nguyen and Salzar recently in 2020. And also some older work of Barnich in 2015. So now, so far I kind of focus on the Virasoro symmetries. We can ask what changes if we had the smooth diffeomorphisms. So it's interesting to note that actually the action of the superrotation charge on this extended phase space is structurally the same, whether these are meromorphic or smooth. But this tensor T, since it's a function of Q, the behavior of the, the change in T under action of superrotation changes depending on whether we use Virasoro or smooth diffeomorphisms. And so it turns out that if we include smooth diffeomorphism, then we really have to parameterize our Hilbert space also with the metric on the sphere. Now, this is a little bit puzzling in the sense that smooth deformations of the boundary metric would imply that boundary 3 is gravitational, and that's kind of, at least from ADS-CFT perspective, it looks a bit strange. But perhaps some insight should come from work of Laura Donnet, Sabrina, and on characterization of these soft modes associated with diffeomorphisms. And there is also some work by Compare on looking at asymptotic symmetric groups in ADS, which also have this property that the boundary metric gets deformed. So now I want to revisit Now I want to revisit this second infrared triangle. So it turns out that there is a nice, if you don't focus on the top vertex and only focus on the bottom 2 vertices, the subleadings of theorem and spin memory, then there is a nice universality of this construction in D greater than 4 dimensions. So it turns out that if you look at the radiative data in any dimension higher than 4, where the metric falls off as as a power written here, then it can be shown just from classical equations of motion that the subleading radiation. So if you do just Fourier transform in time and don't just keep the spatial position the same, then the subleadings of radiation has the following structure. So it depends on the classical momenta. So if you suppose say n particle scattering classically with momenta pi and some angular momenta j's, then this is the structure of the subleadings of radiation in D greater than 4 dimension. And this is really universal because in D greater than 4 dimension, there are no Coulombic effects. So, the particles really become free. So at this J mu nu is the angular momentum. So, it can be just the orbital angular momentum if you have a point particle, but it can also have some intrinsic spin if you have a black hole or something. And this is as I mentioned above, this is a universal feature of and independent of the details of the scattering. So you can have particles colliding, merging, etc. But in D equal to 4, this is subtle because this form of the spin memory is only valid modulo the Coulombic effects. So we can ask, okay, what happens in D equal to 4 if we do include Coulombic effects? And it turns out that once again, if you look at classical soft radiation, then it's universal up to subleading order than frequency, but the subleading order is not order omega to the 0, but log omega. And so if you study radiation now and you do expansion in frequency, then the leading term is what we expected from before, which is the memory term. But there is a new term which we call the tail, which is proportional to log omega. And one physical way to understand the log omega behavior is as follows. So if you, for example, look at scattering of, say, n particles, this is just classical scattering into m particles, then there are Coulombic effects, like long-range effects between the scattering particles. And there is also the Coulombic, 1/r Coulombic drag on the radiation itself from the particles. So the long-range effects between the scattering particles and sort of ensure that particles are never free. If you look at their trajectories, then they have a logarithmic in time behavior. And the Coulombic effects of the particles on the outgoing radiation gives you these extra phases in the gravitational field, which I've just denoted here, which as you can see that if you expand in capital G, Newton's constant, then it has a log omega term. So roughly speaking, these are the two reasons why we get this log omega behavior in the classical radiation in 4 dimension. But it's interesting that it's non-perturbative, that is, it's exact. So if you compute it, it's valid to any order in perturbation theory in the Newton's coupling, and it only depends on the asymptotic linear momenta. The explicit form is a bit complicated, so I won't write it, but it doesn't even depend on the angular momenta. It just depends on the linear momenta of the scattering particles. And this was proved as a completely general theorem in 4 dimensions in 2019 by Saha, Sahu, and Sen. So then it looks like then we have, there's a possibility at least of a new triangle where we so far know one vertex, which is this log omega tail term. But then you can ask, okay, what is the second bottom vertex, which is supposed to be the quantum soft theorem, whose classical limit should give us this tail term. And it turns out indeed this is true, that there is a quantum, if you look at the soft theorem for loop amplitude, then there is an exact theorem which was derived by Vishwajit Sahu and Ashok Sen, which they call log soft theorem. So this theorem, precisely like Weinberg soft theorem, is universal. It's valid it's valid to any order in perturbation theory, and it's one loop exact. So I just explained a little bit what this log soft theorem is in quantum theory. Of course, naively you may think that this would not make sense because the amplitudes are divergent. But really what we do in soft theorems are look at ratios of amplitude. So what we want to do is to look at the ratio of an n+1 amplitude with some momentum P1 to Pn and a graviton momentum K and n amplitude. And it turns out that if you compute this ratio, it turns out to be IR finite and independent of any IR cutoff. And this IR finite ratio has the following form. So there's a 1/r Weinberg soft factor, which we know. And there is a log omega term, which is really composed of two pieces. So there is, these log soft factors are always, like each term in the log soft factor is obtained by summing over pairs of particles, which you can intuitively understand because it comes from these Coulombic drags. But there are really two terms. There is one term, which is the classical tail term that we looked earlier. But there's also an extra term, which is usually what is called the quantum log soft factor. So this is a theorem. It's really at the same level as Weinberg's of graviton theorem in the sense that it doesn't get affected by further loop corrections. Okay, so we have now two vertices of this new, we have two vertices of this new conjectured triangle, and the idea that, so now we want to ask if there is any, are there any asymptotic symmetries associated to this tail term or the log soft theorem. So I should mention that even the classical limit of the quantum log soft theorem and how it gives the tail is not completely clear. There is only a partial proof in perturbation theory that some of us did earlier, but in general, it's a little bit complicated in the sense that the full log soft factor has these two terms, which I call here as classical as quantum. They're of the same order in H bar, but when we compute the classical radiation, then this SQ term seems to be absent, and it's not entirely clear why. So yeah, this is what I explained here, that for the Weinberg soft factor or for the spin memory, the classical limit is kind of relatively trivial in the sense that structurally they look the same. They have the same form, but for this log soft factor, it's not true, and there is a subtlety that still needs to be understood. And the reason that happens is really because of the difference between the Feynman and retarded propagator. But how to take the how at the level of the quantum soft theorem, the classical limit produces the tail is still not completely understood. Okay, so maybe I stop here and ask if there is any question so far.
Feel free to raise your hand anytime and I'll moderate any questions. I don't see any right now.
Okay. Okay, so now, so we would like to understand if there are any asymptotic symmetries associated to the logs of theorem, but in doing it in gravity is a little bit complicated. So what we do is try to do it in a simpler case of massive scalar QED. And this is something that we did with Miguel in 2019. And so here also, it turns out that there is a, exactly like in gravity, there is a one loop exact soft photon theorem at the which goes as log omega. So the idea is the same, that that you look at the ratio of the one loop amplitudes and you get the Weinberg soft photon theorem, and then the extra term which goes as log omega. And rather remarkably, I mean, this soft photon theorem is also universal. I mean, which was not true for the tree-level subleading soft photon theorem. So if you add some higher derivative correction in the Lagrangian, it was known that the tree-level subleading soft photon theorem changes, but this the one loop theorem is actually exact. And again, this was derived by Vishwajit and Ashok in 2018. And the reason, I mean, okay, one reason the soft photon theorem is simpler is because there is no Coulombic drag on the outgoing radiation from the particle. So there is only long range effect we have to worry about is the 1/r potential between the scattering particles. But the radiation in itself is free, and this is the reason that we look at QED before doing gravity, because the theorem, I mean, the theorem is technically simpler. So this is the setup. I mean, we would like to understand if there are any conservation laws and asymptotic symmetries associated to these new theorems. So the setup is that we look at massive particles. So they scatter from I minus past time like infinity, and then they go to I plus, and we are looking at the single soft photon theorem. So we have one photon which is being emitted. Now, there is one thing that we already know from the universality of the leading soft photon theorem, or from the first infrared triangle, that strictly speaking, the asymptotic states are dressed, and they're dressed by what is known as the Coolidge-Faddeev dressing. So just schematically, the scattering states are not the free Fock states, but they have a dressing which depends on the momentum of the particles and the sort of soft photons. So I just schematically write as ETIO. There's another nice way to understand this dressing, which is that instead of dressing the states, we can dress the operators. And it turns out that if you look at the creation annihilation operators for the scalar field, then the dressing can be written in the following form. So if you look at the mode operator at momentum p, then there's a dressing which depends on the momentum and the cloud of soft photons. And this actually implies that if you look at the scalar field operator at late time at future at I plus, then that is dressed. So that is dressed by this factor e to the I alpha 1 plus alpha 2 times the, I mean, the dress field is related to the undressed field by this exponential factor. So this is a quantum picture, but it turns out that even classically you would have expected this. So if you look at charge Klein-Gordon equation, you solve it and go to future time infinity, then it turns out that the scalar field is not really free, but it has this logarithmic time tail, which has this following form, where eta is the gauge field, the tau component of the gauge field. So if you compare these two equations, then you immediately see that the current that you obtain in the matter current that you would obtain actually has a logarithmic behavior. So I mean it has this it has a locked out explicit locked out term, but the free field, the field which is not dressed, which I call phi f, which one can easily check that goes as 1 by tau to the 3/2 at late time. So the overall current has a fall-off behavior which goes as follows: is really log t by t cube, where this A tau is this related to the Coolidge-Faddeev dressing, which I just denote as alpha 1 plus alpha 2 here. Now there's something interesting that you can verify. That now if you look at this current fall-off, which is log tau by tau cube, and you just compute this radiative field, like array component of the radiative field at future null infinity, like at the future point of future null infinity, which we usually call scribe plus plus. Then it has a new so there is this mode that we already have from the tree-level equations, which goes as u times what I just call f0 array. But there is a new mode which sits there, which goes as log u. So so this is potentially interesting, and we can ask if it's related to any conservation law. And indeed, it was shown classically in this paper, as I showed in 2019, that if you look at the same log u mode, but not at scribe plus plus, but at scribe plus minus, then using equation of motion, you can show that it's related to a log r mode at scribe minus plus. So there is a these equality at every point on the sphere. So there is there's an infinity of conservation law that you get once you once you work with these dressed fields. Or basically, once you take the loop effects into account. Now we know that once we have these conservation laws written, between at spatial infinity, really, between scribe plus minus and scribe minus plus, we can write them in terms of fluxes. So we can use some equations of motion and write them as an integral over So I write here the full charge as a flux, but instead of writing integral over u, I write it in terms of some frequency projections. So there is one term which you can see, which will be familiar from the leading and subleading charges, but it has a slightly different projection, which is the second derivative thingy. And then there is an extra term, which is this FRA log mode, which is sitting as u equal to plus infinity. The first term is what I just call the soft charge, because it's linear in the field, and the second term is the hard charge because it's sourced by the current. And as you can see that these charges are really naturally parameterized by vector fields on the sphere, although we are in the context of QED. And this is familiar from the tree level studies in QED, in the sense that already it was shown by Lindelof, Pasterski, and Fromminger in, I think, 2014, that if we ignore dressing, then you get these charges which are really, tree level charges. So the analog of the charges that I wrote above were already derived before for tree level amplitudes, where the soft charge was like a subleading projection in the soft photon, and there was a hard charge which looked very similar, except that it was obtained by looking at the leading mode, the U mode, as opposed to the log U mode. So both these charges, the Q3, which was known for tree level amplitudes, and the new one we are getting from the dressed amplitude or from the are parameterized by a vector field. And now, so in the dressed case, we can study this charge a little bit more seriously in the dressed case. So if you look at this charge, which is really obtained by integrating this FRA log mode over the sphere at future null infinity, scribe plus plus, we can write them in terms of time like infinity, in terms of these currents, etc. So it turns out there's a really nice compact expression in terms of this gauge field, which we obtained from the dressing earlier. And so now, if you just look at the word identity of this, this should be the not Q hard, but total Q. With respect to the dressed S matrix, then it gives you the logs of photon theorem. We can also see why this theorem is universal, because the leading order Coolidge-Faddeev dressing is known to be universal. So just that because this charge really came from the dressing, it's kind of expected that word identity also will be universal. So this is the way that we have some more information about the infrared triangle 3, that we have this infinity of conservation laws which give us these logs of photon theorems. And this was really in the context of QED, which is much simpler than the case of gravity. And there's been a substantial progress made by Sayali in the last few years in this for the gravitational sector. But now, okay, so far we only have the conservation laws, and we can ask, okay, is there a symmetry associated to these conservation laws? And the structure of charge actually sort of hints that the symmetry really is the same as the one that was discovered by Lindelof, Sabrina, and Fromminger for the tree level subleading soft photon theorem. But the charges are loop corrected. So, it's the same symmetry, which is parameterized by vector field on the sphere, but with charges which have H-bar corrections. But there is an interesting puzzle here, that if you look at this logs of mode, which has this following projection in frequency, then it has a trivial action on the covariant phase space of electrodynamics. So it doesn't do anything. It looks like it's just a mode which has a pure gauge mode in some sense. So now we can ask the question: is there any extended phase space we may have in which this soft mode is a non-trivial action, and then the symmetry is kind of explicitly realized as via this action. So sort of continuity. We don't really have any answer to this right now, but I just offer some speculation. So if you follow the same logic that Prahar and others had followed before, that you look at the continuity conditions of the field, then it turns out that the mode which is conjugate to the soft mode should be a mode which should go as log u at large u. But it's not really clear if you add such log u modes, you get a consistent extension of the covariant phase space. So this still kind of remains an open question. So we do have conservation laws which give us these soft theorems, and they are very. I mean, it looks like the symmetries are the same as what we had at tree level, but they don't seem to have any natural action on the phase space. I mean, the soft charges don't seem to have any natural action on the phase space. So this is the status so far for the new sort of universal infrared triangle, that we have a quantum soft charge, which I just called Q hat B, and it's equal, the Watt entities of this quantum soft charge in infrared finite S matrix are equivalent to the log soft theorem. And then there's a classical soft, there's a classical charge QB, which is equivalent to the tail term, but neither are the classical limits completely understood, neither is the symmetry really very well understood. And there is a very similar structure, but much more complicated in the context of gravity. So let me, Sabrina, how much time do I have?
Depending on how many questions at the end, I feel like I've given everybody the full hour to use as they see fit. So just keep.
So I have like how many?
Like if you took 15 more minutes, I think that'd be fine. 10 more minutes would be more ideal, so there's time for questions. But
okay, yeah. So I will be done sooner than that. So there is really so let me just give you some final remarks of is this the I mean, how many more infrared triangles do we expect really in this theory? So Bishwajit Sahu proved that in fact there is an infinite hierarchy of classical soft theorems which are sort of tails of memory, etc. that are really universal, which is quite remarkable. So if you look at, for example, the gravitational radiation in 4 dimensions, then the leading term is the memory term, and there is a log omega tail term that we just saw. But then at every order in the but there are further universal terms. So for example, if you look at the omega log square omega, which is a sort of tail of tail, then that is also universal, only depends on the asymptotic momenta and is independent of the details of the scattering. And you can go on and on. So I think you look at omega to the n log n to the log omega to the n plus 1, then there's yet another universal term that just sits there. And in quantum, I mean, this is really classical radiation analysis. This was not a quantum statement, but in quantum theory, there is a conjecture by Bishwajit, Arnab Saha, and Ashok Sen that at every loop order there is a universal soft theorem. So, for example, at one loop order there is a log omega soft theorem that we discover, which is loop exact. So it's not corrected by further loop corrections. And similarly, at 2 loop order there is a omega log square omega soft theorem, which should be 2 loop exact. And in scalar QED, Bishwajit Sahu proved it that there is really a universal soft photon theorem which has this behavior. So then this is maybe the final puzzle, that how many infrared triangles really are out there, or is it possible that beyond subleading order in gravity we only have a infrared line but no infrared triangle, in the sense that there are these universal soft theorems, sub to the n logs of theorems, and there are universal classical radiation tails, but perhaps there is no symmetry in the theory. So okay, maybe I end here. Thanks for listening.
Thank you. Look for that fun talk. First, I'll take any questions from anyone. Because I have a couple of my own, because actually this is let's Laurent first. I think you might be muted, Laurent, but feel free to ask your question.
Sorry, I was muted. Hello, Alok. Very nice.
Hi.
I have a couple of questions. One question is the relationship between the second part of your talk and the first part of your talk. So when you look at this log, log soft theorems, it's suggestive of some kind of anomaly in the algebra. So can you go back to the first calculation of the commutator, and does it interfere with that calculation and creates some kind of anomaly in the algebra? Or can you say more about that? The relationship, how does that modify the?
So I think the 2
You see what I'm saying? Once you activate the logs, then you're kind of having a scaling.
Maybe you're asking about the.
No, I'm asking about, so yeah, here you did a calculation of this
this one,
algebra, right, by the subleading, but without taking into account the logarithmic tail. Now, suppose you take into account the logarithmic tail. Does that mean that you're going to shift the structure constants of that algebra with an anomaly term?
Yeah. That's a really good point. I don't know if this is of course done in the tree level at the level of tree level amplitudes. Yeah. So the for pure gravity, these log charges they are not really known yet. So we don't really know what the commutators of the super transition with the log charges would be, but I would not,
But from the amplitude analysis, if you redo the Distler analysis, and maybe. Anyway.
Yeah, but from the amplitude analysis, the Distler analysis involved consecutive double soft theorem, and I don't know if that has been derived for once you take loop corrections into account. So okay. I agree. That's a really nice question actually that is to be looked at in more detail.
I have another question. You mentioned at the end that, which was very surprising to me, that there are charges in QED which are labeled by vector fields. So yes. What is the algebra of these charges? Is it the diff S2 algebra? What algebra do they satisfy?
It's still abelian in the sense that these are parameterized by vector fields, but they're really parameterized by gauge parameters in the sense that you can just write these vector fields as gradients of the gradient of a scalar function, and then you get these charges.
Okay, so, but this is still, so a vector field which is a gradient of a function is an area preserving vector field, but it still satisfies a non-trivial algebra usually.
Yeah, but at the level of for the T-level charges, I think the algebra was still abelian. So
okay. And even in QCD, it would still be abelian.
But QCD, I don't know. QCD actually even the leadings of Bluan theorem is loop corrected. So in fact, you get even. I think that once you take loop corrections into account, you get terms which are more soft than 1 by omega. You get a term which is log omega by omega, and I'm not sure what the status of that is right now. Okay. Yeah.
Laura has a question.
Yes, no, it was just to come back to this extended phase space that you presented. Was a bit fast for me to. Yeah. So you added this mode that was 1 over UCAB.
Yes.
So that to me that looks a lot like that's the Goldstone mode for the super rotation. No, like all the computations you're doing are definitely like something we haven't it's very interesting, but just as far as trying to translate into the language, because there's a lot of times these log views are appearing in when we're in this conformal basis, and like it helps us to know that what's the same and what's not. So Laura and I are from the same point of view, so I might be interrupting her, but I can let Laura ask the question, but if we both had this question.
No, it was more to discuss indeed how is it this related.
Yeah. So naively, like when I see this equation, I see it and I think that, okay, what you're adding to the phase space is you have this Goldstone mode and the soft charge. So like there's basically two 2-0 currents that, like, for instance, we were trying to point out only from the, like, not from the point of view of how like it made this algebra nicer, but just from the point of view of well, I guess in one sense trying to identify like a off diagonal central charge site. So to me, this looks like, especially I think if you take U to plus infinity or minus infinity, it's going to be the same value because you don't actually have like a,
right. Yeah. I just made the choice. It's insensitive, I think, of that whether you go to plus or minus. I agree.
Yeah. So
yeah, you're talking about these primaries for that have weight 2, which are actually R2 the mode of delta equal 2 and the shadow of the 0 and
so like so this would be like there's two soft modes, like there's the H2 mode and the H tilde 2 mode, which one of them is like pure gauge, which I think would be this guy. And so like you're, I guess, adding it to the, like what I think when I'm saying, I think there might be a way to reinterpret this proposal in terms of that.
Yeah, yeah. So I think that in your case, I think this T was it just delta function on the? I mean, was it? I mean, you do get it. I mean, you do get it in the paper you wrote.
So the first example I think you'd see it is in the one with like Adam Ball and Andy. Like there's this proposal for the second stress tensor. Not saying, I mean, like obviously like what you're doing with it is different. I just want to make sure that we can maybe translate the language so that we can benefit from each other's. Yeah. So the one there is that it's just literally the Goldstone mode. If you do a super rotation, like you've shifted the metric by whatever u dz cubed yz. Yeah. And that is literally this 1/u thing you're extracting out.
Yeah.
So.
Exactly right. I agree. Yeah. I agree. Yeah. Yeah. One difficulty was that already classically, I mean, the new charges which gave whose kind of Hamiltonian vector field gave the right algebra was derived by Geoffrey and Miguel. But the point was that what was the right phase space on which you could quantize them so that you get a closed quantized algebra. I mean, that was the that was a subtlety. I mean,
but they are canonically paired, and there was a sense in which that was appreciated then, but obviously not like there are epsilons and stuff like, I mean, like that. I just want to make sure that we can translate the language.
No, yeah, I agree. I think that from that perspective, I think the complicated term that is if you look at the new charge that classically one obtains, then there is this new term which is just called JVE here. That that's a little bit complicated term. I mean, it's a really like a boundary term, but it's not linear. It's like quadratic. I mean, it's the N0 and C0 are paired with some complicated sphere derivatives. And,
but the pairing between TAB and at one point you write down the inner product is a delta function. Like that doesn't surprise.
It's not surprising.
Yeah, I agree. Surprising. Yeah.
No, so that's good actually. I mean, in the sense that it's compatible at least with the.
Yeah. Now, one thing we were running into, which was slightly funny, and this was with Laura, and I'm sorry, I think we're asking the same question. That's why I'm saying more, but I'm going to let Laura say her version of it. Is that when we tried to literally augment this phase space with these two, that's where we were running into issues, and that's what the paper with Laura and Andrea we're trying to address. Is that like naively, you're still constructing everything on the principal series, and somehow there are these, as if they're partnered modes off the principal series that can still be written in terms of the ones on. So we were like, I think I'm excited to see the rest of like the paper version of this to understand how that gels with what we were saying there. Right. Laura, do you want to?
Yeah. Can you comment on this bracket story that that Geoffrey and company, they had different prescription for this prescription for the basically I guess the news and the fact that you have sometimes zero central extension or sometimes this cocycle that can.
Yeah. So I think that the original perspective classically was that there was a two cocycle between these charges. I mean, the super rotation and the super translation charges. But I think from quantum theory, at least it and the result of Flauger, Distler, and Horn, I mean, I think it looked a little bit problematic in the sense that you have two symmetries of the S matrix, but the commutator is not only a symmetry, but not even a central extension, and that seemed to be in conflict with the consecutive doubles of theorem. So in that sense, I think that the resolution that you have an algebra which is closed and doesn't have a two cocycle is probably I don't know, more physically preferable. I think also from the celestial sphere perspective, the extended BMS algebra is without a two cocycle, right? I mean the one that Steinberger and Taylor, for example, have derived. So. Is that what you asked?
Yeah. I mean, I have a different. I had slightly different thing in mind, but I understand what you're saying. So yeah, thanks.
I have a comment about that, which is the fact that in the covariant phase space, in fact, it's related to a well-known issue, which we know how to resolve now, which is the fact that when you have flux, when the system is open, there seems to be an ambiguity of how you parameterize the flux. And most of the parameterization, the one which are not associated with the proper Noetherian construction, have this cocycle. But when you do the proper Noetherian construction, you can always kill this cocycle. So I think there's a limitation in the usual analysis of Barney et al. That doesn't really take into account the. But it's related to that. There's always a proper way to kind of fix what you call the charge and what you call the flux in such a way that it's completely clean. And,
I see.
And I think,
into account, but it's everything in the same, yeah.
Yeah, there's a general, and in some sense, it's an evolution of the Noetherian analysis if you do it correctly. So it's very nice that it appears at the quantum level.
Thank you. Any more questions? I think, as you can tell, the talk touched on some things that we care about a lot, so I'm very grateful to see it. If there are no more questions, then I think we'll start transitioning to the next talk, and then hopefully we can. There's a lot of things that Alok's worked on that we can debate with him, or not debate, of course, talk about and learn about in the discussion session. Take it away, Lionel.
Well, thank you so much, Sabrina, for inviting me to come and talk at this fascinating, very interesting conference. I'm feeling a little bit guilty because Sabrina asked me to talk about this paper here, the 1905.09. Well, anyway, this one with Tim Adamo and Atul Sharma. So these are my co-workers, and I kind of only after I sent her my abstract did I kind of realize that he had actually asked me to do that, and then well, okay, so so I'll try and give a nod towards that at the end, but I felt on the other hand it'd be quite nice to, well, first of all, Tim and Atul and I are very excited about our current project. And so we were enthusiastic to sort of, at least I was enthusiastic to talk about that rather than the one from a year or so ago, a couple of years ago. But also I thought it'd be quite nice just to do some prehistory. I think some of the things I want to talk about today happened while I was still at school, and I think it's, well, I just thought it'd be quite nice to be able to sort of make people aware of all of this. But in fact, the main focus is not so much then the celestial story and the infrared triangle. Well, as I say, I'll give some brief discussion of that at the end. Was really more a paper that David Skinner and I wrote back in, well, we wrote it in 2008, it appears in 2010. And this was meant to be an ab initio derivation of the gravity MHV amplitude from first principles. But various things, a lot more was understood about this in the subsequent period, and furthermore, our new derivation is coming via null infinity, and it involves a lot of the ideas that this conference is interested in. So I wanted to really talk about some of the background to that, and maybe how it might link into the topics that everyone has been discussing this week. So just to go back, really probably to a certain extent to the 1960s or 70s, so quite a long time ago. I first of all want to sort of just mention the fact that sort of Twistor theory from its very conceptions was had a kind of holographic or an interaction with holography. I mean, so in Rogers' first definition and conception of it, twistors were intended to be non-local. One of his ideas was that that it would provide a description of space-time from which space-time events emerge, and that the non-locality of the twistors would somehow give some insights into the non-locality of quantum mechanics. And from the beginning, twistor theory was always a three-dimensional space that was constructed in such ways to describe four-dimensional physics. So it had that holographic element, and also from which space-time events themselves emerge. You know, your space-time itself emerges from the twistor theory. And so although he was inventing scry at the time, that he was inventing twistors, I'm not sure that he originally thought about them directly in relation to null infinity. But Ted Newman, who he was working with, was very much an enthusiast for working at null infinity. And he had introduced a program to try to reconstruct space-time from the, actually I haven't drawn a cut-in on this picture of null infinity here, but he had a program of trying to reconstruct space-times from null infinity. And I'll talk about this in a bit more detail in a moment, but the idea was to sort of try and identify where the light cone of an event in the interior of space-time intersects scry. And in order to do that, he introduced a concept of a good cut, which is a cut that's asymptotically shear-free, at least with one of its shears. You can't make both the shears vanish, but you can make one of them vanish. And because it was chiral, he only got self-dual spaces. And these were called H spaces. And I think with his sort of corny jokes, H space was for heaven or something. And that was where the good cones go to. Or the good cuts. And anyway, so Penrose abstracted the nonlinear graviton for self-dual spacetimes from this picture from null infinity. Maybe of more relevance recent years, we've understood how to extend these things beyond the self-dual sector using twistor strings, ambitwistor strings, and all these related ideas, CHY, and so we're now able to do some bottom-up physics, as Andy was asking for in his lecture, to actually deduce some of these things, not via, deduce facts about amplitudes, to actually construct formally directly from first principles, albeit stringy ones, rather than from bootstrap ideas or sort of symmetry considerations and so on. So and so what we can do now quite systematically is the world sheet construction of amplitudes. So so just to go back to the other motivation for this, 10 years ago, David Skinner and I were trying to give a first principles derivation of the gravity MHV amplitude. And so this is something that's nicely written out in terms of spinor-helicity notation. And I guess people are sort of happy with that, are they? You kind of factorize your null momentum into a product of spinors, anti-self-dual undotted and self-dual dotted, and you have the angle brackets and the square brackets of spinor contractions. And that allows you to put down a whole mass of Lorentz invariants into sort of simple angle brackets and square bracket formulae, which, and this is the formulae for the gravity MHV amplitude that we were working with sort of 12 years ago, or 13 years ago. This is after Berenskiel and Quiff. But since then, Andrew Hodges had a much more beautiful formula, which you could express just in the terms of a determinant. So this here, you sum over permutations. It's a mess. It's a lot of terms. Whereas this one here, the determinant is simple to construct object, and it gives you manifest permutation invariance directly that you're expecting. So this is an amplitude, of course, where you have two minus helicity. I've taken to be particles 1 and 2. And then the rest plus. And so you get the manifest permutation symmetry that you expect coming from this. But there was another sort of ingredient that I'm hoping to explain today as well, which is that, in fact, an earlier piece of work, which very few of us were aware of, from Byrne, Dixon and friends, gave a formula for this tree amplitude as for this MHV amplitude as a sum over some tree diagrams. And this was something that, as I say, Vernon Dixon and friends did in the 90s, and is rediscovered by Spradlin and Volovich and friends a bit after our paper. And this is very suggestive, having a sum of tree diagrams. That suggests there's a theory there that allows you to construct this amplitude sort of rather directly. So, and this was related to this determinant by a very neat argument involving the so-called matrix tree theorem, where you do a sum over trees. These are the propagators of the tree in the tree diagram. The HIJs are the propagators, and the diagonal elements are designed to make the rows add up to 0. And you get a reduced determinant here as the sum of all these tree diagrams. So it's a bit of a mystery. Is there a theory that gives rise to all of those tree diagrams? And certainly the approach that David and I had 12 years ago didn't really work for that. It worked to produce this formula out of a Twistor construction. So I want to try and sort of resolve some of those puzzles then. And I want to start off with null infinity, just to at least introduce you to some of the kind of, well, sorry, you all know null infinity, sorry. I want to introduce Newman's Twistor theory via Newman's H space, via this good cut theory. And as part of that, actually, one of the things I did want to do was to introduce a kind of formulation at Scry, because one of the things that I find hard to cope with is constantly breaking Lorentz invariants. If you're an amplitudes person, it's a nightmare if you do that. You just can't tell what you're doing with an amplitude if you're constantly breaking Lorentz invariants. And a formalism for studying Scry that allows you to maintain explicit Lorentz invariants is this homogeneous Scry formulation that I'd like to talk about. Anyway, so the idea then is to introduce Twistor theory via null infinity to show, just to illustrate the extent to which it's a kind of asymptotic concept, or can be expressed as an asymptotic concept. And then I want to go back to space-time. So I'm actually going to generate the gravity MHV tree amplitude from the space-time action, but then take it out to null infinity and introduce a Twistor sigma model for the representation that we get, which will be after Blavatsky's treatment of subdual spacetimes. And then we can do an extension to the full gravity tree S matrix, and then finally see how this formulation gives you a way to talk about celestial amplitudes and soft theorems. Okay, so that's the plan. So okay, so this is a slide that I almost really just don't need in this talk, in this conference. I mean, here's meant to be a picture of null infinity. And I've done both Scry plus and Scry minus here, and I've introduced Bondi coordinates, which are retarded time coordinates, and we use the complex coordinate Z as a complex stereographic coordinate on the sphere. But one of the things I want to draw your attention to is the extent to which this sort of rather irritatingly makes breaks invariances. So you have the inexplicit Lorentz invariance, and then in fact, this 1 plus mod ZZ bar squared thing. I mean, this metric on the sphere, that's choosing a time-like vector as far as Lorentz symmetry is concerned. So the whole thing is, this whole presentation is sort of awkward from that perspective. So this is something that George Sparling sort of found a nice formulation for in the 70s, which was, he never wrote it up, but Eastwood and Todd wrote a nice paper on this in the beginning of the 80s. So sort of, and what you do, if you want to express the action of the Lorentz group, you can introduce homogeneous coordinates on the celestial sphere. So I'll do that. I'll have lambda alpha equals 0 and 1 on the celestial sphere, where Z is just the ratio of the two coordinates. And of course, if you rescale lambda, then this ratio doesn't change. So you have to work homogeneously in this Riemann sphere coordinate. And then when you do that, then lambda alpha is a spinor index for the Lorentz group. So if you think of the Lorentz group as being SL2C, then you act on lambda alpha with SL2C. Well, this is the spinor double cover. But in fact, you have to go on. You have to sort of, if you want to make everything Lorentz invariant, you have to take U to have weight 1, 1. And if R is the radial function that we were dealing with before, then 1 over R should also have weight 1, 1 as well. And so that means that when you rescale lambda by A, then you have to rescale these two by AA bar. So A is a complex parameter here when you do the rescaling, and so you have a weight in A and its complex conjugate. And with that, then, when you expand the metric out, if you do a conformal rescaling of the metric, and you get with R squared, and you get a finite metric now, but in homogeneous coordinates. So you really have to. So dz then gets traded for what I'm going to call capital D lambda, and read that all the way through, and that is the homogeneous volume form. And as you see, it has weight 2 in this scaling. So straight off, then we can see that. If you want to follow Ted Newman and study light cone cuts, then we get a nice Lorentz invariant formula here with U equals X contracted with lambda and lambda bar as the location of the intersection of the light cone of X with null infinity. Okay, now we need one more ingredient here to work. If you want to work invariantly, Lorentz, and here I'm just talking about Lorentz invariance, so there's nothing too fancy. You have to work with a conformally invariant version of this so-called ETH operator. So Ted Newman's ETH operator, or the Newman-Penrose ETH operator, was always just the spin connection on the round sphere. So it has a life that's not conformally invariant on the sphere. But if you want to have Lorentz invariance manifest, you have to think about it as a conformally invariant thing. And I'm just going to need a second derivative here. So Z, we're going to want to characterize cuts of null infinity. And so we're going to put U equals capital Z of X lambda and lambda bar. And this is going to have weight 1, 1, as I was saying. And so you just learn by homogeneity that if you take the first derivative with respect to lambda bar, then it has weight 0 in the complex conjugate lambda. And so then if you hit it with the homogeneity operator, you get 0. And that means that this second derivative must be proportional to 2 copies of lambda bar. And that gives you a conformally invariant way of talking about the second derivative with respect to the complex conjugate coordinate. And so what Ted observed was that you can characterize good cuts in Minkowski space by asking that the ETH bar squared should vanish, the second derivative with respect to lambda bar. So that's pretty obvious, I guess. And this actually has a geometric interpretation. So the geometric interpretation is that as the cone goes out to infinity, as it intersects infinity, it's shear free. So that Ted Newman's then question was, what can you do in curved space? So in this conformally rescaled metric, we can move to curved space now, and the leading order contribution in this rescaled metric then is going to be some, so the order R part is going to be sigma naught times d lambda bar. So this is meant to be squared, and the complex conjugate. So this is what you guys, I guess, have been calling C bar, Z bar, Z bar, this sigma. And I guess that follows from the original Bondi paper. And I guess I was brought up by Newman and Penrose, so I guess I call it sigma for the shear. But so I hope you don't mind me shifting that notation. So, and of course, this d lambda is, as I said before, that's the d little z for the complex coordinate on the sphere. So, so Newman, so why is this sigma the shear? Well, I mean, really what, so this is the asymptotic shear. And so if you want to kill the asymptotic shear of a cut that looks like u equals z of x and lambda lambda bar, then you have to solve this equation, eth bar squared of z, I suppose it'd be z if you're Ted and American, eth bar squared of z has to agree with this, and then that kills the shear of the cut. But this sigma is complex, and so this is a complex equation, and so for solutions, this z must be complex. So this is but anyway, so Ted proved that there exists a 4-parameter family of solutions to these solutions. It forms a 4-dimensional space-time, and this has a natural holomorphic self-dual Ricci flat metric, and its light cone cuts are given precisely by this capital Z. So that was Newman's H-space construction. So okay, I want to take you now to asymptotic twistor space. So sorry, I should just maybe stop and see if anybody has any questions about this. This is a remarkable thing. You can you can take the data. So sigma is the of course the data, asymptotic data of the gravitational field, and you can reconstruct a space-time. It's not the one you first thought of, but it has the same asymptotic shear. And you know, maybe you can use this to analyze the space-time. Maybe it can contain some key information. Okay, well, this talk is more focused on the twistor theory. So what I want to do is, now what I did was I introduced W for twistors because that capital Z was the cut function, and I'm slightly worried I didn't do this all the way through, but anyway, okay. So what does this have to do with twistor space? Well, Roger Penrose had already thought about an asymptotic twistor space, and basically the asymptotic twistors are light rays at lie in null infinity, and we can parameterize them again projectively. So this is although it's really a projective space, it's complex projective 3 space. We will follow this tradition of maintaining explicit invariances by working with the homogeneous coordinates. And so twistor space has two spinor coordinates. We have the lambda alpha that we have already seen as being the homogeneous coordinates on scry, on the celestial sphere at scry, but we also have a mu alpha dot. And so first of all, if you contract mu alpha dot with the lambda bar, we get a projection down onto scry. That will give you the u coordinate up null infinity. And we can think of this twistor space as really being a subset of the cotangent moment of the scry, because what you're doing is you're picking up the anti-holomorphic derivative of the cut. So this so if you have a cut, then there is a twistor that's sort of, so to speak, tangent to it in the anti-holomorphic direction. And what Penrose observed was that you can reformulate this good cut equation as a d-bar equation for holomorphic curves in twistor space. So that was his insight, and so I'm going to introduce this quantity h, which will be the main actor all the way through for the gravitational field. So it's obtained from the asymptotic shear sigma by just by integration up the generators of scry. So it's just the potential for the asymptotic shear, and so Penrose's construction then was to interpret the good cuts then as actually holomorphic curves in twistor space satisfying this d-bar equation, And so the lambda was already going to be holomorphic, but the mu gets deformed in curved space by this term. Okay, and so you can think of this as providing a finite deformation of the complex structure of this complex projective space, or a region in that complex projective space, that's given by, in fact, a Hamiltonian vector field associated to this H as a Hamiltonian. And there's this Poisson bracket that you can define on Twistor space that determines this. Okay, and once Penrose had done that, he could throw away scribe. He just had his Twistor space. He had this construction. You could look for holomorphic curves in the Twistor space. There are some wonderful, powerful mathematical theorems by Kadar and Spencer, which told you that the moduli space of these curves was a four-dimensional complex manifold, and he was able to reconstruct the self-geometric on that manifold to give you Ted Newman's H space. Okay, so that's my potted introduction to Twistor theory via scribe, and well, we'll come back to that. So what I want to do is come in from infinity and talk now about how it is that we can construct amplitudes on space-time. But before I do that, maybe I should pause for questions. Does anybody have any?
So if anyone wants to ask questions, I'll be looking out for raised hands. I know that I actually have personally, Rolando and I have a lot of questions for you, Lionel, but I think they're too technical for this thing. So I really am happy to be hearing about this stuff.
Okay, well, anyway, I'll carry on. So in fact, today I've got two stories about Plebanski. Again, this is all sort of, we're revisiting the 70s now, you know, before I started thinking about these sorts of things. So Plebanski had a gravity action where you start off with a tetrad of one forms. So this is a normal tetrad, but I've written it out with spinor indices. So this you can think of constructing this with a normal frame with a two, which you arrange in a 2x2 matrix with t plus z, t minus z, x plus iy, x minus iy in that 2x2 matrix there. Then gamma is going to be the spin connection. And so you use this Palatini variation with a tetrad and a connection, but you only use a self-dual spin connection in this Plebanski form. And in fact, you only really need to know about these self-dual 2 forms, where you, so you have Hodge duality, two forms split up into self-dual and anti-self-dual 2 forms. These are the self-dual ones and the dotted versions of the anti-self-dual ones. I'm slightly worried I've got that the wrong way around, so I'll move on rapidly. And then he writes down this version of the Einstein action. So Einstein-Hilbert action. So you recognize d gamma plus gamma wedge gamma as the curvature. Well, I'm putting the coupling constants in the gamma wedge gamma part. And so this is just the Einstein-Hilbert action, but you can write it out in this form. And here, of course, kappa squared then has to be the self-dual spin connection. And so the field equations tell you then that you have the Einstein, well, you could throw in some matter, you'd have the Einstein equations, and that gamma is the self-dual spin connection form. And you can use this as a nice formalism for constructing MHV amplitudes, because so this is something that Abu Zaid and Hal pointed out, is that you can use this Plebanski action to perturb around the self-dual sector, because if you put the coupling, that was why I put the coupling constant here with that kappa squared there. If you put it there, then at kappa equals 0, you get this action here, and this gives you the self-dual vacuum equations. And so it gives you the field equation that d sigma equals 0, and if these forms are closed, then you can learn quite rapidly that the metric is self-dual. And also that the and then the gamma, yeah. So I was wrong when I said that gamma was self-dual spin connection. It's the anti-self-dual spin connection. The gamma is then has the status of a linear field on that background, and so it's associated with a linearized anti-self-dual vase spinor on that background. And so what you deduce from that then is that this second term in the action is the perturbation around the self-dual sector. And you can see that, in fact, this is the generating function for the MHV amplitudes. If you replace the gamma by a pair of on-shell anti-self-dual fields, this is what the MHV amplitude is. And you can interpret it as the probability of flipping a positive helicity particle on an anti-self-dual background, well, a minus helicity particle into a positive helicity one on the background. Okay, so this was something that David and I were using 12 years ago. The big thing that we managed to do now was to use a different branch of Pasterski's work, and so we're going to choose those gamma 1 and gamma 2 to be momentum eigenstates. So these can have these momenta here, factorized into these spinors. And if you have a choice of a pair of spinors, kappa 1, kappa 2, that are constant, what Pasterski showed was you could think of, you could break up the space-time coordinates into z and tilde z, and think about the space-time metric as being determined by a Kähler scalar. And so these sigmas then, which determine the metric, can be constructed out of just this one Kähler scalar here. And so what Tim, Atul and I have observed then is that we can take this MHV generating function here, and we can do some integration by parts. And if you do that, we end up with this simple formula here. And that simple formula now gives you a generating function for the MHV amplitude, where 1 minus and 2 minus are the anti-self-dual particles. And then the self-dual particles are all really, the omega is a fully nonlinear object. It satisfies a Monch-Ampere type equation, a Kähler. It's a standard sort of equation you get for reaching that Kähler in 4 dimensions, and so you can think of this as a collective field for all of those plus particles that you have in an MHV amplitude. Okay, now so what's this got to do with twistors then? Well, how am I going to construct this omega out of twistor space? And so so somehow we're going to need to use these holomorphic curves in twistor space. And so for the good cuts, then we can sort of write down a cut function, which is its flat space part. So these parts are kind of linear in z and z tilde, but then there's a nonlinear part, which is going to come in from the fact that we have some self-dual background, which could be arbitrary. And that arbitrary background is encoded in the asymptotic shear, sigma. And we can write down an action for, so the business part in the cut function is then going to be this little m. The rest of this is what you'd have expected from flat space. So it's a finite perturbation around the flat space answer. And you can write down an action for the good cut equation. And that's where we need this integral of the asymptotic shear, which we've been calling h. And okay, so this gives you an action for Newman's good cut equation, but we can lift this to lift this to twistor space, doing the very similar thing here now. We're going to sort of just take the lambda bar derivative of this cut function as we did before to find mu. And this gives us then an action for the corresponding holomorphic curves in twistor space. So these are Penrose's holomorphic curves in twistor space. So one of the key things that we've managed to prove is that the Pasterski scalar, capital omega, is computed by these actions. So these actions, it's easy to see that these two are in some sense the same. And so what do you do? Well, you differentiate the action with respect to the these coordinates z and z tilde, and you show that they satisfy the right equations essentially to be the to be the Pasterski scalar. So what that tells you then is that there's something sort of quite deep then about this omega here. It wasn't just some random scalar, kludgy scalar that you cooked up in sort of reducing the vacuum equations. Sorry, the self-dual vacuum equations. This is telling you about the action of these good cuts or the action of these twistor curves in twistor space. So okay, so this gives us then our generating function for MHV amplitudes. We've already encoded the two negative anti-self-dual particles in the kappa 1 and the kappa 2 here that are sort of just got their standard exponential. These are meant to be e to the I k dot x's here for the two anti-self-dual particles, and then this h here now is how we're encoding, instead of having the omega that I had before, this h now is encoding all of the plus helicity particles. And this is a fully nonlinear formula. Okay, so now we can sort of just do some elementary quantum field theory, or at least classical field theory really, to perturbatively expand in h. So we can say that h is going to be a sum of momentum eigenstates. So this is what a momentum eigenstate looks like for this integrated asymptotic shear, HI. And you can just use your elementary quantum field theory that tells you that the on-shell action can be computed as a sum of trees. And so here I've written it as a sum of tree as a correlation function, but it's a tree correlation function. We're only going to allow connected trees here, which connect these. Well, I'm calling them now vertex operators here. These are just the these perturbations in the action that are coming from each of these individual HIs. We only want them to occur once because we're doing we're now expanding in these HIs, and but we know from elementary quantum field theory that comes out as a sum over trees. And if you look at the form, sorry, I have to go back up to the action. If you look at the form of the kinetic term for this action, then the propagator builds in this Poisson structure that Penrose had identified in the fibers of this twistor space. And so we have the kind of Riemann sphere propagator, and it acts on the H's via this Poisson structure. So when you put in these momentum eigenstates here, this Poisson structure is just going to pull down these kappas, and it was d by d mu times d by d mu, and so you get this ij square bracket ij over angle bracket ij for the propagators. And so what you can see is that this tree propagator, this tree formula now will yield the tree diagram formalism of Byrne et al. Of 1998. So just doing this tree correlator is going to give you this det prime of H then by the matrix tree theorem, which was originally pointed out by Boufeng and Songhe. And when you integrate out all of the z's, as you have to do here, z's and z tildes here, we'll get the momentum conserving delta functions, and we get some standard factor for the anti-self-dual spinors. So this gives an on-the-nose derivation now of Hodge's reduced determinant formula, and indeed the Byrne et al. Tree diagram formalism for the MHV amplitude. Okay, so maybe I should kind of pause a moment there. see if there's any questions. Okay, so anyway, I myself was quite pleased with this because there was something definitely wrong with the formulation that David and I had way back because we hadn't done that extra integration by parts. We had some extra gauge dependence in the description of the potentials, and that really infected the whole formalism. And just as a kind of extra bit of background, as far as Tim and Atul and I were concerned, we were also looking at doing some expansions around strong fields, and it messed up that too. We had this gauge dependence in that, which became complicated, and we were finding it hard to get rid of it. So this gets rid of that, and so this for us was a big deal. Okay, so your next question is perhaps going to be, is this just the MHV amplitude, or does it go beyond this? Well, maybe it is, maybe it isn't. That's where I'm going next. Well, I guess we know from twistor string theory that well, okay. So we want to go up to higher MHV degree, and I'm not sure that I should expect people here to know anything about twistor string theory. But one of the things that we kind of knew from twistor string theory is that to go to higher MHV degree, we were perhaps going to need to look at rational curves of higher degree in twistor space. So, if we go up to n to the k minus 2 MHV, then we're going to need k anti-self-dual particles instead of just 2 of them. We had 2 of them for the MHV. And so these, well, we could put any eigenstate we like. I'm just drawing here the what the standard twistor momentum eigenstate looks like for an anti-self-dual wave function. Happens to have homogeneity degree -6, which seems quite a lot, and it just depends on the momentum spinors again as before. And I have this integral here. You can of course integrate against this delta function, but then it's one of these things where you need a reference spinor in order to do that integration. So we don't always like to do that. Okay, so what's the idea? So we're going to look at a curve of higher degree, so that we're going to insert these anti-self-dual wave functions at points ZR in the twistor space. Sorry, this is where I embarrassingly failed to adapt my notation. You've probably all forgotten that I'd called a twistor W earlier on. So now a twistor is called Z, as is the cut function, as is the coordinate on the Riemann sphere, and everything else. Okay, but let's, my apologies for not being systematic. Anyway, so we're going to insert anti-self-dual particles at k points in twistor space, the ZRs, and we're going to make our holomorphic curve now go through these k points. And so if you do that in flat space, then you need to have a degree k minus 1 curve. So you can just see that by the number of poles here. And putting in these poles here, it's just, we're working in projective space. So we could get rid of the poles and have lots of other clunky terms in here. So so it's easier to put them in as poles, but it's really just a way of saying that Z of sigma at sigma equals sigma r is going through the twistor ZR in homogeneous coordinates. And so this gives you a map to twistor space that goes through those k points. And then this M here is going to be sort of an off-shell bit, or the bit, so that's the flat version, but we're going to need to have a non-flat version in case the, on a curved background. So this is a deviation from the flat background. And so now the action is pretty much exactly as we had before. In fact, we don't need the awkward weight factors that we had before now with this way of presenting it, because Z and M have weight -1, and so this is now weight -1 on the Riemann sphere. And but this is, what you have to note is that this is no longer the celestial sphere. This is the celestial sphere is the coordinate lambda. Lambda 2 has degree d in the curve here. So this is now wrapping round the celestial sphere k-1 times. And this is rigid, so M is uniquely determined given the ZRs from this. Okay, so my claim now is going to be that this action here generates the gravity tree level n to the k-2 MHV amplitudes. We only actually need one extra ingredient, which is a fudge factor, another det prime, but this is det prime of H tilde. It's not the one we were looking at before. This is what you might call a conjugate Hodge matrix. And this det prime of H tilde, it's got angle brackets in the numerator instead of the square brackets we had before. So it's the conjugate. But this is now going to be our generating function for the higher MHV degree amplitudes. And I've just put in arbitrary wave functions here. We can put in momentum eigenstates, or we could just peel off these things and just say that we've got a function of these k twistors here and put in wave functions later. Okay, so we need this additional reduced determinant. And again, as we did before, we can do our elementary expansion of little h into n minus k positive helicity self-dual particles, and so then, as before, we'll get a correlation function. Well, these were meant to be vertex operators here with the h's, not the naked h's. But this is a tree correlator of these h's here, integrated. And then you need to integrate over everything in sight. You need to integrate over the insertion points and over the twistors, and then that gives you the formula for the full n to the k MHV, well, n to the k minus 2 MHV amplitude. How do we know that? Well, you can, there's a formula which is not too far off from this called the Casazo-Skinner formula that was discovered 8 years ago, which gives you the full tree level amplitudes for Einstein gravity in 4 dimensions. So a precursor to the CHY formula, I guess. Okay. So in that vein, in fact, what that Casazo-Skinner formula immediately led to was a string, but not this one. So I just wanted to say a few words about the comparison here. I mean, the Skinner n equals 8 twistor string is a beautiful thing. It's but it is very different. It has twice as many bosonic fields. It has a whole bunch of fermions as well. It has world sheet supersymmetry. It has a whole bunch of gauge symmetries. And so you're putting in a twister and a dual twister. So it's not really in twistor space alone. This lives in twistor space cross dual twistor space, at least off shell. And we have some fermions and everything's gauged, and it's beautifully balanced and it works. Skinner's formula is actually a full quantum correlator on the world sheet. This model here, we're just using on-shell actions. We're just using trees. One of the things that you can see from this, so an advantage of the new model is that you really are just getting the honest Einstein-Hilbert action. You're evaluating that on the asymptotic field, so that you can just see that directly, at least at MHV. One thing I quite like is that the new sigma model has an honest dimensionful coupling. It's as you would expect, but it is incomplete. So this det prime H tilde will be inserted by hand. I fully confess to that. So I better get on because I've got to at least do some of my duty to Sabrina and talk about infrared triangles and soft theorems and such like. So sorry, but I should pause for a moment in case anybody wants to discuss this earlier stuff.
Great, there's a question from Andrea. I think we were looking at the end of your slide deck, so go Andrea.
Oh, sorry, okay.
No, because you were kind enough to put it up.
No, I just have a question on this, this determinant prime. So you said you inserted as a touch factor, because before in the MHV amplitude, you didn't seem to need that. Do you have some sort of interpretation, or is it really trying to find something to make it match?
Well, it's the H tilde, right? So the det H prime, we get it by a tree expansion of an on-shell action, sort of a very normal sort of thing to do. This one here, well, we've been struggling. By the time the paper's published, we'll have an interpretation, but not yet, I guess.
Okay, fair enough.
I should have confessed this is work in progress. So Atul maybe sort of change his gong show talk to something to how to interpret det prime H tilde. I don't know.
Thanks.
Okay.
I'll just say that in the MHV case, we have proven this thing, that the correct det prime H tilde comes from directly from the Lubansky action, directly from that term that we discussed earlier, produces the amplitude. In that
it's
case,
one in the
MHV
case. It's det prime H tilde is equal to 1 in the MHV case.
Yeah. Or maybe it's our 1, 2 to the power or whatever it is. I think I must, yeah. That's right.
It's really just 1.
I mean, I guess it would be nice to have a space-time origin for this, or a sigma model origin for this, and that there was a point in which our notes had a palatial twistor string for Roger's new palatial twistors, but it didn't work. So anyway, BMS symmetries and soft theorem. So this is a story which actually is common to a whole family of models that you can define: twistor strings, ambi-twistor strings, 4D ambi-twistor strings. I think the first version of this argument, so I've misspelt Tim's name, is in a paper by Adamo, Casali, and Skinner, and then Yvonne Geyer and Arthur Ipstein and I picked up on it in greater generality. And there's just a general principle here, and this is true in all of these cases, that so all of these have vertex operators. I mean the sigma models do, the strings do, and so on. And the key observation is that the soft limit of the vertex operator is d bar. So these vertex operators are all really kind of these are all things that you integrate on the world sheet, so they're kind of 1-1 forms, and on the world sheet, but they're d bar of a singular symmetry generator as you go onto the world sheet. So what do I mean by that? Well, so for all of these models, the target space can be thought of as having something to do with the cotangent bundle of Scry. So because it's the target space is a space of light rays, all of those light rays can be taken out to infinity and land represented at the cotangent bundle of Scry. And so at Scry, the BMS group is a subset of the symmetries of this cotangent bundle. And so in terms of the various sigma models in question, the symmetries are all represented by sigma model currents. So those are sort of 1-0 forms on the world sheet. And what happens is that when you set the soft limit of a vertex operator, it's d bar of one of these sigma model currents for one of these BMS symmetries. And so just to give an example in the kind of framework of this talk then, so a super translation is just shifting u by some function on the celestial sphere. Here in our language then, the shift of u is some weight 1-1 function on the celestial sphere. On the twistor space, it shifts the mu coordinate by df by d lambda bar. And that's generated by a current then, which is mu df by d lambda bar, and that is actually naturally a 1 form. It has weights to be a 1 form in the models that we're talking about. This I haven't put the 1 form part in there. And so in the case, for example, of a soft graviton vertex operator then, And I'm letting this S here be the soft parameter, so S is tending towards 0. So it has momentum K, but S is tending towards 0. And so the leading term of this then is precisely, so if you just take that momentum eigenstate I showed you before, you just very naively let K equals S times K and let S tend towards 0, and you just pick up this as the leading order term. And so this is the this is what the graviton vertex operator is in terms of a super translation, and this is a super translation with a pole. So it's sort of non-trivial. It's d bar if it has a delta function, and it is a genuine sort of graviton. It has curvature. It's a plane wave with whose exponential has tended towards 1, but it's non-trivial. And in fact, I always had an interpretation. So on the one hand, sort of Adamo, Casali, and Skinner had a nice interpretation as a Ward identity on the world sheet. Because you got the d bar of this singular symmetry generator, you can flip the d bar, and you can pick up the action of that symmetry generator on all of the other particles. So you can see that the and this is where having a bottom-up approach really pays. You can just use the Ward identity in that elementary way that one would expect to use it. But I always also one can then go, if you go back 50 years, you find that these kinds of Hamiltonians were introduced by Roger Penrose back in the end of the 60s, the beginning of the 70s, of the last millennium, or last century at least. And he had an interpretation of precisely these Hamiltonians as the action of a graviton on the light rays as they scatter from scry minus to scry plus. And so actually, I rather like this as a kind of rather different. So this isn't sort of what you get by gluing up scry minus to scry plus and making the super translation move them both in tandem and say, aha, that's a symmetry. This is a Ward identity following from that symmetry. This is shifting scry plus relative to scry minus across I0. And that's how we're seeing this. So anyway, I think it makes a kind of different interaction with the infrared triangle than I think I've seen from the way that other people talk about it. Okay, so that's my slide on BMS symmetries and soft theorems. Anyone? Any questions? No?
Andy, is there a question?
Okay. Okay, I just have 2 more slides.
Oh, Andy has one question.
Oh, sorry.
What did you mean by the statement it has curvature?
Well, I mean, if you write it down on space-time, a soft graviton, you've just let the ECI k.x tend towards 1, but it's still got curvature 1. So it's multiple of all those kappas or something. So it's still sort of deforming. Light rays are still curved by it. I mean, in a singular way, of course, but yeah. Okay, my comments on celestial wave functions. This is really just my nods.
I don't understand what that means. If you do a super translation, a light ray leaving scry plus, a light ray on scry plus will be at least one that's properly antiptally identified. A light ray leaves later on scry plus, leaves later on scry minus, and will arrive later on scry plus.
Right. So I guess what I'm saying is that if you look at the scattering of a null geodesic from scry minus to scry plus on a space-time with that just constant bar spinner, then well, I guess what I'm really referring to probably is more of the calculation that Roger Penrose is doing, because that's more of an infinitesimal. But this is an infinitesimal calculation. So I guess you have to just say, what is the infinitesimal kick to a light ray once it leaves scry minus and lands up at scry plus? That's the question you're asking. And the claim is that it is this this super translation is the infinitesimal kick that graviton gives to first order to the null geodesic.
Which sounds like
but if it leaves 5 minutes later from scry minus, I don't understand in what sense they're kicked.
Well, this is compared to the back version. I mean, this is
a
perturbative. It's a perturbative statement. So if you have a light ray leaving scry minus, and then you've got this single graviton there, you're only allowed to interact with it once, then the claim is that this is the formula that you would get for the interaction with that light ray as you cross space-time. It's the shift. So if you take a light ray on scry minus in flat space, it will land up at the same point on scry plus. There's a canonical identification via some antibodal map, which I'm sure you're very familiar with in flat space. And then this is the difference from that you'd get from the soft graviton. Okay, okay, so just for the second last slide, the celestial wave functions. So this was really agnostic as to what wave functions you use, but we can do the Mellin transform of the momentum eigenstates that we had before here, and we can get a celestial state here. And again, you can play, so really the game we were playing in this paper was to say, well, if you look at the poles, then that corresponds to soft limits. And so the pole at delta equals 1 is a super translation generator, delta equals 0 is super rotation. And again, in this sense that I had on the previous slide of being d bar of the generator. Okay, so just to finish off then, so I just want to say gravity tree amplitudes are generated by on-shell actions of the sigma model for the curves and cuts of scry. At least at MHV, we can prove directly that this is the evaluation of the Einstein. We get it as the evaluation of the Einstein-Hilbert action on the solutions via a generating function. But we can go beyond MHV, in which case it all becomes a little bit more mysterious, and we get these degree k k-1 mapped. But these are wrapping around k-1 times. So I'd love to be able to sort of boast at the end of this that these sigma models are the celestial theories that you've all been looking for, but I'm not sure that they are. I mean, they provide a powerful tool, and I think they're interesting. But just the fact that you get this wrapping means that it's not the same thing. And I mean, I think you have that same problem with conventional strings as well. There's no reason why the conventional string world sheet should wrap around scry or have any nice relation with the conformal structure of scry. Here it is locally conformal. So in progress, extension to non-zero cosmological constants, hopefully that'll work. And you can do similar things for Yang-Mills. I just talked about gravity. And I want to at least give some boost for Attal's talk in some ways. He'll tell us about all sorts of lovely things to do with multi-collinear limits or something. I can't remember. You'll find out later. And I feel now that we've got a closer grip connection with the space-time action, we can maybe make more precise connection with Ashtakar's gravitational phase space and so on, how that actually works and so on. But we're not there yet. So I'll just say thank you and yeah. That's it. And then you get the deafening silence from
No. What you're hearing is silence, but like you're not saying is all of like the Skype conversations back and forth, trying to figure out if what you're saying is connected to the. So no. So the downside, I think I intentionally tried to end with your talk because I think that like especially so with you and with Alok's right now, the questions that were being asked were like if you know they're more like trying to interpret what you guys are doing in terms of what we know. So I think like a year from now, the next version of this conference will like be more questions on the technical details and less on the like, can we connect this to what you're doing? Which I think is something maybe that like for each of the individual technical things is a more of an offline type of question. But thank you again. I'm very happy that you gave this talk.
Oh, thank you. Okay, I wouldn't be in your bad books by not talking about what you'd asked me to.
Oh no, that's fine. I mean, I think the thing is that like at least for a couple of us, like we're just trying to make the baby steps of like the first like just going to that language. And then obviously the body of your talk was like what you can do with it, which is a better reason even to do it. So it's very appreciated. Thank you.
Thank you.
Any questions?
Actually, before there are questions, I could just, given that I'm the last speaker and the conversations may peter out at some point, I do just want to, at least I'm the last formal speaker, but I just want to say, you know, this has been a fantastic meeting. I've really enjoyed all of the talks. And thank you so much for organising it all. And I don't know who was doing it, so I just said et al, but I'm sure there's lots of people to be thanked as well as you, but you've done a great job.
I mean, the wonderful thing about a conference like this is you invite the people and then all of the content that makes it wonderful is all the people who attend and all the people who talk. So like that all is all of you. So thank you.
Okay, so while there were no questions, I thought I could at least slip that in case people would start to peel off.
Thank you. I think I'll stop recording on that point.